Ladies and gentlemen, please rise to welcome Air Marshal Praveen Keshav Vora, Uttam Yudh Seva Medal, Ati Vishesh Seva Medal, Vayu Medal, Deputy Chief of Integrated Defence Staff for Policy Making, for Policy Planning and Force Development. A very warm welcome to you, sir. On behalf of the Center for Joint Warfare Studies, I, Vaibhavi Katil, a research assistant at CENJOWS, warmly welcome you all to this seminar on Energizing Semiconductor Ecosystem for Defense Applications. Energizing the semiconductor ecosystem for defense applications is indispensable to securing strategic autonomy and sustaining technological preeminence. In an era defined by electronic warfare, AI-enabled systems, and precision-guided capabilities, the need for secure, indigenous chip design and fabrication systems has never been more pronounced. Building such an ecosystem requires sustained investment in research and development and the establishment of trusted supply chains and deep institutional synergy among industry, academia, and defense establishments. Fostering fabless innovation alongside advanced manufacturing will be key to reducing external dependencies. Moreover, coherent policy frameworks and targeted incentives can catalyze capacity creation. Ultimately, a resilient semiconductor base will not only strengthen national security but also elevate India's stature in the frontier domains of defense technology. With this context, we now formally begin with the proceedings of the day. We will now move on to the welcome address by Major General Dr. Ashok Kumar, retired, Vishesh Seva Medal, Director General, Center for Joint Warfare Studies. He is a distinguished Kargil veteran and an accomplished author with over 300 published articles across 30 platforms. He has commanded an infantry formation in Arunachal Pradesh, overseeing the very terrain where pivotal battles of 1962 war took place. A former MD of ECHS and later a principal staff officer at Headquarters Eastern Command, he brings decades of strategic and operational experience. May I invite Major General Dr. Ashok Kumar, Director General CENJOWS, to deliver the welcome address.
Respected Air Marshal Vora, General Jubin, Dr. Parimal, who is the brain behind this event, distinguished leaders of the Indian Armed Forces, paramilitary forces, pioneering scientists from Defense Research Development Organization, captains of the semiconductor industry, who are going to be the main players for whom we have planned this event, especially esteemed guests, colleagues, and our friends from media. It is my privilege to welcome each one of you for this event. And I must say at the beginning that once you spare some time for some organization, you are actually giving that part of your life to that organization. So thank you very much for sparing a part of your life for CENJOWS. Now, we convened this first workshop in December 24. As against having these stand-alone events with no continuous feedback and progress, Headquarter IDS has commenced a series of activities focusing on certain domains so that we not only initiate the dialogue, but we continue that dialogue for times to come, give the feedback to the participants, take their points, and go to the decision makers so that we create an ecosystem which is much better and resilient, which is need of the hour. Now, for the defense sector, you all are well aware that semiconductors are no longer just components. They are the strategic high ground. Whether you take the guidance system of BrahMos missiles, the shooter sensor links, the secure communication networks, both in the forward battlefield and in the strategic domain, there is no field where the chips are not required today. And everything is actually built on the foundation of silicon. We have been really a kind of different kind of country. We started, pretty early in certain domains where the DRDO-led lab was created a long time back. But then thereafter, there was some slow movement in this particular field. But the nation has realized that this is something which has to be given the highest priority of the day, and that's why Indian Semiconductor Mission has been launched. Its first version came, and in the latest budget, the ISM 2.0 has come. So now it is the focused ecosystem which is being attempted to be developed so that we all are able to meet our requirements from the indigenously designed and developed chips rather than being dependent on the foreign OEMs and foreign countries where you are not sure about the integrity of that chip which you are going to use in your products. There can be number of backdoors and other disruptions which need to be taken care of. They are much more pronounced today as against their earlier susceptibility in earlier years. India has also now decided to involve all the stakeholders in a new model of the national development. The earlier differentiation between the public sector undertakings and the private sector has really diminished. Today, the Indian government believes and practices that whether there is a growth of a public sector, a defense public sector undertaking, a private sector in terms of the large organizations, MSMEs or startups, if any Indian grows, the India grows. And therefore, all kind of effort is being made to support this ecosystem. And I'm sure while there may be certain aspirations of the industry which not would have been fully met, but if you bring to our notice, we shall go back to them, and I can assure you with my experience that the approach of the government is very, very positive in this particular direction. There is another change which I wanted to share with you all. Initially, the defense forces were basically making GSQRs, PSQRs, and going for the purchase of the equipment. But now we are not limited only to that. We know that what are the critical components and the challenges in those equipments getting produced, irrespective of the agency which is producing, and we have become as stakeholders. So we do the hand holding of the industry to provide them the user inputs, the try to handle their challenges, and bring the entire government machinery of the defense forces at their beck and call to support. The kind of support we are providing and we are willing to provide in today's time was something which we couldn't dream in our service even 3 to 4 to 5 years back. The recently launched Indian Semiconductor Mission 2.0, besides giving an outlay of dedicated 8,000 crores, has also focused on development of the indigenous IP system. And therefore, in today's one of the talks, we have focused on the IP domain also, so that the intellectual wealth in the technology domain which is available can be harnessed by all developers, and we do not reinvent the wheel in that direction which is already invented and is freely and legally available for its use. You will find a booth also displaying these kind of capabilities in the lower portico. And in fact, during your tea break, we have more than 20 industry partners, DRDOs and other partners who have been working with semiconductors in some way or the other. They have established their booth. You must go and visit them, know what they are doing and whatever experience you have had and what would be your expectations in that particular field. Share with them so that jointly we can create a better India. India already contributes roughly 20% of the world's design in the chip design field. But sadly, our scientists and the intellectual wealth is being utilized by the foreign countries. We hardly have been using the design capability of our intellectual wealth of our countrymen for the growth of our own country. So design-based focus, design-led R&D is something which is to be, given more prudence in the times to come. And the work being done by DRDO's Solid State Physical Laboratory SSPL and the Semiconductor Laboratory SCL Mohali will be another cornerstone which you must see, and also see as to how they are changing or reorienting themselves to the current emerging national need. So you must visit them and take care of that. The fab alone does not actually meet the entire requirement of the semiconductor ecosystem. There are a number of other initiatives which have been launched by the government, including the launch of 40,000 crore worth of the electronics mission, where these kind of ecosystems are being developed. It is not only the chips, but the gases, the design. There are a whole number of things which go into making a chip. And we have to not look at only 28 nanometer and beyond. We have to go down, and so that each and everything of our country, especially in the defense, can be sourced in our own country. As you will move into the technical sessions, I shall request each one of you participants to look at not only trying to get the low hanging fruit, but also look at three critical things: identify the niche requirements, focus on the talent development, and strengthen global partnership. Because it is a stated policy of the government of the day that we do not only have to make the defense equipment for our own defense forces and paramilitary forces, we have to make it for the all friendly foreign countries of the world. And therefore all kind of support is being provided. This defense attaches have been given a mandate to support our industry in their country of posting, to support the private sector as much as is the public sector. So with that note, I will close my brief welcome address, but I will fail in my duty if I do not mention the presence of Mr. Abe-san from Embassy of Japan, whose presence indicates that we are valuing our strategic partnership. And you are well aware that Japan has got the leading role not only in their own country but for the world, and they are the ones who are willing to travel together with us. So you'll be able to hear his special address. So thank you, Mr. Abe, for taking your time and being with us. So with that note, I look forward to promising, deliberate, and frank deliberations. And it's Chatham House rules. Whatever issues you have, you must bring out. Because of the time being little tight, you may not have adequate time here, but use the time of tea break, lunch break, and otherwise peer-to-peer interaction to make most of it. Thank you very much.
Thank you, sir. We'll now move on to the inaugural address by Dr. Parimal Kumar, who is an outstanding scientist and scientific advisor to the Chief of Integrated Defense Staff to Chairman Chief of Staff Committee. He's a computer scientist with more than 33 years of experience serving in various scientific and techno-managerial positions in DRDO, Headquarters IDS, and Services Headquarters. As a scientific advisor, he has been advising on technology assessment and niche technology areas like civil-military fusion, facilitating joint capabilities, fostering jointness among stakeholders, and promoting self-reliance and modernization of Indian armed forces. Dr. Kumar realized the semiconductor-focused approach is critical for the country, and more so for defense applications. He organized the first workshop on the subject in December 2024, and to ensure the continuity and progress, the second workshop is being conducted today. May I request Dr. Parimal Kumar to deliver the inaugural address.
Hind, Honorable Air Marshal Vora, this is PP and FD, General Juvin Minwala, this is Ops, DG CENJOWS, Principal IFA, distinguished military leaders, invited speakers, senior officers, scientific advisors, scientists from various labs, academicians, representatives of industries, think tanks, media representatives, esteemed colleagues, honored guests, and participants. It is my proud privilege as well as responsibility to deliver this inaugural address. This audience doesn't need any introduction to the strategic as well as commercial importance and relevance of semiconductors. And DG CENJOWS has already covered a lot of things. So at the cost of repetition of some of the things I'll speak. Today we say data is the new oil, but behind the data, there are computational devices. And if you go a little deeper, so there are ICs, chips, and in fact semiconductors. In the current geopolitical scenario, we have witnessed the weaponization of availability of oil. And similarly, the availability of semiconductors can be also weaponized or has been already weaponized. Therefore, it is very important to energize the semiconductor ecosystem to become self-reliant in availability of semiconductors for defense applications, and I'll be particular to be precise, for military applications. Since the objective is to energize the semiconductor ecosystem, so let us see what does the Indian semiconductor ecosystem comprises of. To my mind, broadly, the Indian defense ecosystem comprises of the DRDO labs, SSPL, and the facilities under it, such as GATEC and STAR-C, that is under Ministry of Defense. Then we have Semiconductor Complex Limited at Chandigarh, and India Semiconductor Mission under MeitY, Ministry of Electronics and Information Technology. Then we have Ministry of Mining, Ministry of Mines, and Department of Atomic Energy, which are relevant for self-reliance in semiconductors. Further, there is one more segment of urban recyclers who are striving their best to make up for a considerable part, with a ballpark estimate that the recycling has the potential to make up for around 20 to 25% of the rare earth minerals for strategic applications. I'm limiting to strategic limitations. Then in addition, foremost users are there, because the entire effort is for users. Then scientists are there, academicians are there, IP attorneys are there, and there are many other industries in addition to recyclers who are providing chemicals and different kind of ecosystem, the lithographic machines, the machinery which is required for setting up a foundry. So it is a complex interplay of many players which comprises of the Indian semiconductor ecosystem. And to meet the national goal of self-reliance in semiconductors for military applications with an objective of self-sufficiency and immunity from supply chain disruptions due to geopolitical or commercial considerations, we need to synergize the efforts of involve all stakeholders. And today, through this workshop, we have made our best efforts to bring representatives of all players at one platform. However, in spite of our best efforts, some representatives we could not bring together today due to their other pressing commitments. But we are hopeful that we'll be able to bring them together in our subsequent efforts. While one may argue that military is not the direct buyer of IC chips, but as DG CENJOWS also mentioned, that there is no military system, modern military system or platform which is not dependent on availability of chips which meet the requirements of armed forces in field deployable conditions. In this regard, in today's workshop, we have relevant talks on these topics from senior military leadership as well as all stakeholders on these topics. We have 3 technical sessions. The technical sessions have been designed to foster candid dialogue and knowledge exchange on several critical fronts. The session 1, the first session, brings out the challenges and efforts made in strengthening self-reliance in semiconductor for military applications. In this session, we have speakers from India Semiconductor Mission, users, DRDO, academia, and industries. In session 2, the second session is focused specifically on building semiconductor ecosystem through Indian industries and R&D institutions. And the third session is focused on policy interventions required for self-reliance in semiconductors for military applications. At this juncture, let me mention that we had our first workshop, as mentioned earlier also, on 13 December 2024. And after the workshop, we brought out the policy recommendations report with approval from the competent authority. This time again, we are going to bring out the policy recommendations report. Therefore, I encourage each of you to engage fully, share your insights, and challenge the assumptions. I also request you to visit the exhibition and interact with the exhibitors. This will not only encourage the exhibitors, but will also come to know that what is our readiness level in the field of semiconductors, what is available on the ground. I must mention that our ability to secure our borders and maintain operational advantage depends on our collective resolve to innovate, collaborate using whole of the nation approach, and adapt at speed while maintaining the principle of better, faster, and cheaper. Normally in commercial world we say cheaper, faster, and better, but for military applications it is, in my opinion, other way around. It should be better, faster, and cheaper. With this, I wish all the best to all participants and wish for a very productive and outcome-oriented workshop. With these words, I close my address. Jai Hind.
Thank you, sir. We'll now move on to the keynote address by Air Marshal Praveen Keshav Vora, Uttam Yudh Seva Medal, Ati Vishish Seva Medal, Vayu Medal, Deputy Chief of Integrated Defense Staff for Policy Planning and Force Development. He was commissioned into the fighter stream of the Indian Air Force on 19 December 1987. He's an alumnus of the National Defense Academy. The air officer has a rich experience of operational flying and has flown over 3,400 hours on various aircrafts, which include MiG-29, all variants of MiG-21, and Sukhoi 30. He's a graduate of Defence Services Staff College, Wellington, and the Centre of Defence and Strategic Studies, Australia. The air officer commanded number 47 Squadron, the Black Archers. He has been the air officer commanding of Air Force Station Halwara and air officer commanding Jammu and Kashmir and Ladakh. May I request Air Marshal Praveen Keshav Vora to deliver the keynote address.
Jai Hind, and a very good morning to all of you, the industry leaders, the scientists, DRDO community, the IFA, our distinguished guests. A lot has already been said about semiconductors, the industry, the supply chain, and where we stand today. In this address, what I'm going to speak about is from the user point of view, which is the defense application and how is it so important to us. We are living in a volatile world. Needless to say, we've already seen we're almost into 40 days of the war of US-Israel against Iran. Why are semiconductors so important to us? And I would like to take you back to one poem which says that for the want of a nail, the battle was lost. I think most of us have read this when we were younger. And for those of us who can understand and are familiar with Hindi, हाथी के सूंड में अगर चींटी भी घुस जाती है, so that is the end of the elephant and he can do nothing. And that is where I would like to pitch this and explain what is the importance and the use of semiconductors. To take the analogy, in military parlance, we have something known as centers of gravity, the center of gravity. We keep talking about oil, power, infrastructure. Today's center of gravity, as we see it, is the semiconductor. If we do not have the technology of semiconductor and we are not making it, we are going to lay ourselves extremely vulnerable. The reason why we as the government and as the armed forces are focused on creating Atmanirbharta is to break foreign dependency on critical components. It is not going to happen within the next 1 year or 2 years, but over a period of time, gradually, maybe about 3 to 5 years, we should be totally independent. And the reason for being independent is supply chain security, removing foreign dependency, and being able to put the logic and the algos that we want on the semiconductors. I know I'm speaking to, or trying to preach to the learned. You're all from the same industry and you're all well read and aware of what I'm talking about. But to just put the basic facts on the ground, this is important. The financial outlay has already been covered by the esteemed speakers, Major Ashok and Parimal. The importance has already been given. Headquarter IDS has been nominated as the lead for taking forward semiconductor industry and its defense application, and to drive it, which has not been done earlier. It has started off in 2024 when we had the first workshop, to get everybody from across the country together, sit down and see how we can work it out. It starts from, of course, the rare earth elements. How do we get them? Where do we get them from? The experts are here. Start from the machinery, lithographs like you covered. The experts are here, the industry is here. How are we going to set it up? The factories to produce it. And where we come in is what are we going to use it for? And the final word, or rather the final imprint that we want to put on the chip, and what we want the chip to read and how to behave, is where the defense applications will step in. And I hope that this workshop gives you a fair, not understanding, a fair understanding of the requirement, not of the understanding of semiconductors. We are all very well aware of what semiconductors do and how they operate. In the workshop, in the 3 sessions that we are going to have, as covered by Parimal, we will work towards making out how we are going to become Atmanirbhar. Any questions which come up, any doubt, any queries which come up, this is the forum to clarify it, because we are all aware. We have enough people in uniform from different subjects and different subject matter experts. They'll be able to talk about what exactly is our requirement. We have Major General Maan, who will, in the due course of the workshop, cover what exactly is going to be our requirements. I would like to conclude by saying we are at an inflection point today. We have spoken about semiconductors. The next step is towards AI and quantum. Unless we get into 2-3 nanometer capability, production of 2-3 nanometer, less than 5 nanometer capability of semiconductors in our country, we are going to miss the bus as and when that changeover takes place. And it is going to be an inflection point. You can look back in history. I do not think that there is any other development which is going to change the way we defend our nation than this particular jump which will happen, likely to happen within the next couple of years. And we have to be ahead of the curve. And that is what makes this most critical. I'm not trying to paint a doomsday picture, but I think we are fairly good. Our technology is good. Our DRDO labs, RCI have worked out, and we have reached a certain stage already. Now we have to transfer it into production. That means the civil-military fusion or the civil-government fusion, where it has to be transported into mass production for utilization in the services. With that, I would like to wish this workshop all the very best, and can go ahead and commence the activities. Thank you. Yeah.
Thank you, sir, for setting the tone. We will now move on to the special international address by Mr. Abe Noriaki, Minister of Political Affairs, Embassy of Japan. He has worked extensively on Indo-Pacific regional issues, engaging vigorously in bilateral relations with Southeast Asia, consolidating Japan-United States security arrangements, enhancing multifaceted relationship with the Republic of Korea, and working on North Korea's nuclear, missile, and abduction issues. In his capacity of policy coordination, he dealt with such complex and sensitive matters as creating as war-related history, shaping stable and constructive relations with People's Republic of China, and promoting UN Security Council reforms. He was assigned successively to the Embassy of Beijing and the Delegation of Organization of Economic Cooperation and Development in Paris. Japan's distinct lead in the semiconductor domain is known all over the world. India and Japan share a special relation both historically as well as in current times. I would also request Mr. Noriaki to stay back after his address.
Dr. Parmal Kumar, Major General Ashok Kumar, Air Marshal Aravind Keshava Vora, distinguished officers, preeminent scholars, Dr. Ulpi Bora, especially, and the organization team of the CENJOWS who make this happen today. Good morning, namaste. I'd like to express my sincere respect and gratitude for hosting an important and timely workshop today. I am very much honored to speak to you on the subject of semiconductor industrial cooperation between Japan and India. At the Embassy of Japan, I am in charge of political and defense cooperation affairs. The fact that I am privileged to speak on this particular subject today is a clear testament how deeply national sovereignty and economy associated, and how much converge deeply the national security. The pessimist sees difficulties in every opportunity, and optimist sees opportunity in every difficulty. I believe that optimism is a recipe for success, and optimism is infectious. This is what I've been learning from my Indian friends and Indian society. It is indeed true that COVID-19 was a wake-up call. As a matter of fact, Japan depends 80% of its semiconductor needs on the import, so it's 90% for India. And then both governments embarked on the policies to enhance its self-reliances. And now, I think there's unprecedentedly favorable conditions for both countries to collaborate in the field of semiconductor and defense. Under such uncertain and volatile international configurations, geopolitics and geoeconomics are the name of the game. Various policy measures related to economic security are completely justifiable as an exception against free trade principle. This gives us a golden opportunity to think twice about our strategic positioning in the international business and international security. Not despite, but all the more for the deteriorating international security configuration, there is no bilateral relationship that is blessed with the opportunities and potentials than our bilateral partnership. There are 4 reasons for me to be an optimist. First, Japan and India are natural strategic partners given its geographic location. We share such fundamental values of democracy, rule of law, and we are pursuing to realize the free and open Indo-Pacific. And secondly, our policy environments are favorable to forge the industry. Japan studies and keenly follow the development of Digital India, Startup India, Atmanirbhar Bharat, and India Semiconductor missions, all the robust initiatives promoted by the Honorable Prime Minister Modi and his cabinet. In Japan, Prime Minister Sanae Takaichi took office last year, and no sooner than she took the office, she specified 17 priority areas for the strategic investment, including material, digital cybersecurity, and defense. So Prime Minister Takaichi herself sees more opportunities in those risks and crises. And third reason for me to be optimistic is that the mutual commitment of our political leadership. Last year was a watershed year for our strategic partnership. Just please be kindly reminded of such a fruitful visit of your Honorable Prime Minister Modi to Japan last August. We witnessed the defining moment of the bilateral relationship with a special focus on economic security. They concluded the fact sheet, which is such a visionary and specific roadmap to guide our industrial efforts in the field of emerging technology, critical minerals, and they concluded Economic Security Cooperation Initiative, and METI and MEITI concluded the digital partnership on that particular occasion. And fourth reason is that Japan and India can play complementary role with each other in favor of those proactive policies taken by both governments. Private sector are very vibrant in terms of the investment and research and development from Japan to India. Let me take a few examples. Tokyo Electron, which Prime Minister Modi visited while he was in Japan, is the now leading the Japan's engagement in the semiconductor in India. In 2024, Tokyo Electron inaugurated the front-end wafer process fabrication in Dorela, Gujarat, and it opened operation at the assembly and testing process in Jagi Road in the state of Assam. Another example is another Japanese company. In 2024, Renesas opened the back-end process in Gujarat in cooperation with Tata Electronics and CG Power and Industrial Solutions. Renesas took another extra mile to open the academic and industrial partnership at the IIT Hyderabad. So there are four major reasons that I am optimistic of our bilateral cooperation. Having said that, there is also a saying, quote, "The pessimist complains about the wind. The optimist expects it to change. And the realist adjusts the sails," unquote. So building upon the optimism, I'd like to point out eight reflection points for our consideration from the realistic point of view. I should apologize for my brunt in pointing out those eight reflection points, but those are a sort of a testimony and request as well as constructive proposal. And I like to stress that every single effort should be mutual. So the first reflection point is the necessity to improve the business environment on both countries. I find it necessary. I don't think it necessary to dwell on this point, dwell at length on this point. There are still many Japanese companies which complain about the procedural difficulties and some impediments in tariff, taxation, indigenous content, and quality control order. And they strongly believe that as far as semiconductor is concerned, and at this initial stage of the absorbing manufacturing technologies and know-how from abroad, it is essential for the Indian government and Indian market to remain open for import and investment from overseas. And second point, I'd like to stress the importance of cultivating and forging industrial bases in more extensive areas of industry. This means we should develop our collaborative areas, not only manufacturing, but also in the stable supply of water and electricity, infrastructure such as roads and airports, as well as transportation logistics. We need to develop our human resources, young and promising talents, talented Indian people, Indian engineers, as Renaissance provides in various parts of this country. We can enhance our cooperation in training, skill development, and research and development. So we need to build the more comprehensive ecosystem to make our collaboration substantive. And third reflection point is effective application of our information protection, technological safeguard, as well as export control. It is essential to facilitate our technological and equipment transfer based on trust. And fourth, we need to specify our comparative advantages. What are the complementarity between Japan and India? In which field and on what product, for example, automobile or mobile phones? There are various applications in this field, and we need to be more specific about our complementarities. On top of that, Japan-India partnership should have a competitive edge in the international competition. And in this regard, we need to deepen our analysis and studies what Japan-India joint venture can occupy the competitive edge in the international competition. And third, we need more enhanced and substantial government intervention. Both governments may have to bear risks of enterprises and facilitate and guarantee projects. More financial assistance to the initial capital investment and operational cost should be considered. And sixth, review of regulatory frameworks on both sides are very important. Defense industry is a case in point. Semiconductor is integral to the components of jet fighters, unmanned systems, submarines, missiles, and communication networks. And in the Operation Sindhu, the drones were extensively used. In this regard, I'd like to draw your attention about Japan's proactive defense posture In 2023, Japan reviewed its operational guidelines under 3 principles of defense equipment export. That means Japan is now better positioned to export our equipment and technologies overseas. And on top of that, Prime Minister Takaichi pledged to expand the permission scope of the Japan's technology and equipment to overseas market, including India, by abolishing the conventional 5 categories. This will, I hope, pave the way for more vibrant technological transfer from Japan to India and co-development by both countries. And the seventh reflection point is matching of business interest and business enterprises. In this regard, Japan Chamber of Commerce in India has a semiconductor committee hosted by embassy, JBIC, JICA. About 150 Japanese companies and Indian companies get together every 3 months at the Embassy of Japan. Finally, the 8th reflection point is building up multilateral or minilateral, plurilateral partnership beyond our bilateral partnership. Watt and Tax Silica are a very useful vehicle to promote the tangible projects to benefit participating countries as well as the neighboring regions. By doing so, we can be more resilient to economic coercion posed by any entity or any country, and engagement with industries are necessary component. So those 8 reflection points are the proposals, as I mentioned earlier, for an optimist to become a realist. I hope those points will be conducive to your active discussion which follow this for the rest of today. Thank you for your attention.
Thank you, sir. May I now request Air Marshal Praveen Keshavora to present a special memento to Mr. Abe Noriaki. Thank you, sir. May I now request everyone to join us for high tea. We also have an exhibition displayed. Kindly grace it with your presence and interact with the exhibitors. Please be back by 10:20 a.m. sharp for timely conduct of events. Thank you.
ऐसे दिखा देखो लाइव में India 150 1 to 3 good morning
Ladies and gentlemen, you're requested to take your seats and put your devices on silent mode. We now move forward to session 1 on the journey of strengthening self-reliance in semiconductor for military applications. It is my privilege to introduce the chair of this session, Air Marshal Praveen Keshav Vora, Deputy Chief of Integrated Defense Staff for Policy Planning and Force Development. The co-chair for this session is Professor Mridula Gupta from Department of Electronic Science, University of Delhi. Professor Gupta has an illustrious academic career with over 250 publications in international journals, more than 360 papers presented at national and international conferences, over 30 invited keynote talks, and the mentorship of 32 PhD scholars. May I request the chair and co-chair to come on the stage. This session will be conducted in 2 parts. For the first part of the session, we honor to have with us a distinguished panel of experts. May I now request our esteemed panelists to join us on the stage. Ms. Sunita Verma, who is the Group Coordinator for R&D in Electronics at the Ministry of Electronics and IT, looking after the entirety of R&D operations, including National Supercomputing Mission. Dr. D.S. Raval, who is presently serving as the Officiating Director and Outstanding Scientist H at the Solid State Physics Laboratory, DRDO. He's heading the Advanced Semiconductor Technology Development and activities in the critical areas of RF, photonics, MEMS, quantum devices, and has a vast experience of more than 30 years in semiconductor process technology. Major General C.S. Maan, Param Vishish Seva Medal, Ati Vishish Seva Medal, Vishish Seva Medal, was commissioned into the Armored Corps in 1990. The officer has varied experience both in tank warfare as also in counterinsurgency and counter-terrorist operations. In his last appointment as Brigadier Capability Development, he was handling the big budget capital procurements of the Indian Army. Dr. P. Balasubramanian, Scientist G at DRDO, has made significant contributions towards the design, development, validation, and qualification of airborne and ground systems for various projects and programs of defense and space applications. May I request the panelists to please take their seats on the stage. Before we proceed, a small note for our audience. There will be no formal question and answer round during the session. However, you are encouraged to engage with the esteemed panelists during the networking break. And now, sensing the enthusiasm and anticipation of our delegates, I'm delighted to hand over the conduct to our esteemed panel chair.
Thank you. Okay, once again, a very good morning to the distinguished guests who have gathered here. And it is my honor to chair this session today. We've already covered everything that we needed to speak about the semiconductors. I would just like to make one more addition to this whole aspect which I had covered earlier, is that I have been involved with technology my whole life. Being a pilot, I have flown fighters all my life, as you heard, and relied on the heart, which was the semiconductors, which have always come from outside. And it is time we change that. And this is the first step, or rather second step. First step has already been taken in 2024, and now we come on for the second step. We would the panel and the speakers have all been introduced, and there is without any further delay, I would like to request the first speaker, that is focused development of semiconductors for military domain, to please. Wherever you are comfortable with. Yeah, okay. I think your mic is off.
So I stand here representing our CEO ISM, Shri Amitesh Kumar Sinha. He couldn't be there due to some other engagements. And I'll briefly tell you about the Semicon India program and how India is progressing towards the building the complete ecosystem and strengthening it in the country. With the vision of our Honorable Prime Minister, METI is looking at creating and developing the ecosystem for semiconductor and becoming a trusted partner in the global supply chain. As it was realized during COVID also, there was a huge shortage of semiconductor chips, especially it was felt in automotive and also in various other areas. And now if we look at the global scenario, the war or the challenges, the competition is not on the weapons anymore, it is more on the technology. It's more of technology warfare which is happening. And it is very important for us to be competitive, to be abreast with the technology, and have a robust supply chain becoming Atmanirbhar in this area so that the dependencies reduce. It is not that we can completely forego the dependencies, have a complete supply chain. Semiconductor is such an area where the global dependencies will be there, be it raw material, be it some fab or design or for ATMP or any other aspects. But the critical technologies or the ecosystem should be within our control. So that is the main, I'll say, crux of the whole initiative. If we look at the semiconductor value chain and the various elements in it, design or IP is one of the most important aspect, where we say that 70% of the chip cost is in the IP. And if we look at various companies which have risen up based on their IPs, we say Intel, Qualcomm, Nokia, and others. It is that IP is the main or the focus of the chip or the semiconductor systems. The IPs are created or developed using the EDA tools or the EDA design automation tools, and the IP, several other IP cores which form the system on chip, SoCs or the simple IPs. The design then goes into the fabrication or the foundry, where we get the actual chip, and the R&D and the effort goes towards the equipment and tools. So the wafer fabs are basically the capex of it is basically the tools and the equipment that is coming from the various suppliers. And then comes the ATMP, where we have the feed from the raw materials. Looking at the semiconductor supply chain share, 3% of the global sales value, 50% of value addition, and 60% of BOM cost is what contributes in the supply chain. Looking at it, so the ministry has been supporting various schemes. The PLI scheme for mobile and components, I think most of you must be aware about the production linked incentive. Which is mainly focusing on the manufacturing, bringing the supply chain for manufacturing within the country. The focus has been by this ministry, by METI, on the mobiles and the components, the PLI for IT hardware, and also now we have come out latest with the electronics components and manufacturing scheme and electronics manufacturing cluster. There are various PLI schemes by other ministries which are also looking at other system and incentives for the various other sectors like automotive, advanced chemistry cells, telecom, drones and components, etc. The growth of electronics manufacturing has been rapidly increasing exponentially. And if we look at the various, the impact of it, with the various schemes that the ministry, the METI has come out, while the production has increased 6 times and the exports 8 times, the focus which has been on the mobiles, we see an exponential growth of 28 times, and mobile phones export 127 times. So this is the impact of the various schemes of the ministry with respect to the PLI. Now, after the manufacturing supply chain has been brought into the country, there is a requirement or a need for having a complete semiconductor ecosystem within the country, nurturing it, strengthening it, and see to it that in certain areas we are self-reliant. The India Semiconductor Mission, it started in 2022, and since then we have had a good success. There have been 4 components of the ISM. One was the semiconductor display and silicon fabs, the compound semiconductor fabs, and the packaging. On the side, on the fabless chip design, that is the semiconductor design, and also upgrading the semiconductor lab of SCL Chandigarh. After coming out with the scheme, the various states also have come out with some various incentives for them for setting up the manufacturing units within the country, within the different states. So various states have different capex incentives which are complementing the ISM, so that the various units can be set up. And as far as the ISM 1.0 is concerned, we have had 10 approved projects, and across the country you can see the various engagements and the collaborations which have happened with the Indian companies to come out with one fab which is at in Gujarat, Tata Fab at Dholera, then the Micron ATMP, Keynes OSAT at CDIL, which is already existing in the in SCL for the devices and components, which has been strengthened. An OSAT Fab. Then recent one is HCL Foxconn at in UP, in Assam, and also in Odisha will have a compound semiconductor fab, compound fab, and ATMP. In Andhra also we have one OSAT. So this is the status of the approved projects. The Tata Fab at Dholera is proposed to come out with the production somewhere in around 2029-30, and Micron has already started the production. You must have heard about the production facility which has been launched recently. And also there are other 8 OSATs, ATMPs, which are currently under various creations and setup. So that was with respect to the fabs which are coming up, and it will take some time for the fabs to be established, for the OSAT and packaging to be established in the country. While that ecosystem is being established, what has been the strength of this country has been the design, the IP creation. There has been a conscious effort by our ministry in nurturing or in developing the chip designers or the I'll say manpower development in chip design. With the resources, with the young demography of the students which are available, we have had various MNCs and some of the major R&D houses of the MNCs in the country, and with that the ecosystem was ripe for the design linked incentive, which is a scheme for supporting the fabless chip design to the startups and for the domestic companies. The design linked incentive, which is basically for the fabless design, it has 3 components. One is the design infrastructure support, as I said in the previous slide, whenever a company or a startup looks for design, they need IPs and EDA tools. There is a free access to these EDA tools and IP codes, which are I'll say a considerable cost of EDA tools and IPs is there when a startup or a company starts designing, and that infrastructure support is given by under the DLI scheme. And there is a free access of the EDA tools to all the companies. There are about 130 companies which have access to the to the EDA tools through this scheme to come out with their designs. So there is so the initial investment in the chip design for the EDA tools is not to be worried about by the companies. Other is the deployment linked incentive, which is when the companies are ready with their design, they can go and deploy, and any offset which is there with respect to the design volumes, that is taken care of by the deployment linked incentive of 6 to 4%. And also there is a funding support for right from ideation up to the design stage or to the fabrication of 15 crore, capping of 15 crore or 50% of the project cost, whichever is lesser. There are 24 approved financial startups for the chip design and 105 applications from EDA tools which have been given the EDA tool support. So some of the important chips or SOCs which have been taken up by these 24 are in the area of CCTV chips or microprocessor, in the communication area, and also in the strategic area. So these are some of the companies which have been approved and the type of chips that they are developing. So so they are for commercial sector basically, but some of the chips are like the satellite communication or the chip for the broadband applications. These are basically the chips which have both dual use. Some of the so 15 of the companies out of 24 companies have also bagged VC funding, looking at the investment which has been made by the government. So radar RF chip for edge application, which is used for drone detection, is one of the applications which is very apt from the strategic point of view. The chip to startup program is a program for manpower development or skilling in the area of chip design. This is basically for giving the students or of various institutions experience right from ideation to the fabrication stage. When the chip comes back, they also test the chip, and so we say that we are building industry ready manpower. There are about 67,000 students who have already been trained. They have been given EDA tool access, the IP access, and also rigorous trainings on the various aspects of design by the Chip-in, which is at CDAC Bangalore, and the EDA tool vendors and the other industry people are giving online and offline training to the students for chip design. The chips which are developed by the students, they are sent to the Chip-in, and from there they are sent for fabrication to the various foundries. So mainly it is sent to SCL and also to the outside foundries. About 65 such chips have already been developed, and they have been fabricated at SCL. So this is the spread of the C2S program, and if you look at it, none of the, I think we have covered all the states in the country where the trainings are conducted and the access is given. So these are some of the details of the chips. So although these are all okay. So these are all basically the chips which have been fabricated, and these are, I'll say, capacity building exercise. It's not something which can be used on a commercial basis, but when the students come out, they can be they are taken by the industry for their they get very good I'll say jobs. So these are the recent global semiconductor MOUs and the supply chain resilience which have been done under ISM. And the intent is that we need to work in partnership, global partnership with all the multinational companies and build on their strength and try to build our strength based on the experience and the expertise that is available. So these are some of these partnerships which are recently announced. And I'll just take you through because the topic was on the military. I'll just try to rush up now. The topic was on the military applications. So these are few. So we also have an R&D scheme in the ministry where. So I was just talking to Professor Iyer. Professor Iyer told me, why don't you talk about the R&D initiatives also? So some of the R&D initiatives which METI has been supporting. One of them is on development of NAVIC and GPS receiver, and based on the NAVIC satellite, the receiver we had given an RFP, and the receiver which has been developed can not only look at NAVIC but also is compatible with GPS and the other constellations. Microprocessor Shakti and Vega are two microprocessors which have been developed with using the open source RISC-V ISA, and these we have different variants of these both the microprocessors which can be used by the various companies, and any systems also can be formed based on these processors. So you can visit the website and see the processor and the family of processors which has been developed. Some of them are so this is design development within the country, and the tape out also some of one or two variants is at SCL. So it is a totally trusted design which can be taken up for strategic applications. So I'm just giving you a brief idea on whenever we look at the systems, it is not a single company or a system, one country, which based on which a system is made. If I look at a Samsung mobile, it's not that everything is made by Samsung. There are chips which are made by Qualcomm, by Micron, by any other companies. The ATMP is happening somewhere else. The packaging is happening somewhere else. Fab and design in other countries. So this gives a fair idea of that we need to work with other companies and countries also when we look at the concept of a system. So this is the breakdown of the ICs. I will just rush through this. So I have taken some examples, and these are the various processor IPs. If we say processor is required for military application of a strategic, it is just not one. There are many family of processors depending on the requirement, depending on the application in mind. The processor or a controller needs to be different. So now as we speak, we are also looking at the next phase of Semica, and in this we have a separate sector for strategic requirements, where we'll be looking at the strategic needs. Although the 1.0 was basically looking at building the ecosystem and strength in the domestic in the semiconductor area for the domestic companies. Here we are looking at the strategic requirement, very focused on what is the requirement, and we have had some few stakeholder consultations also on that. And the requirement would be with respect to the systems, and in the systems what can be done to develop chips, looking at the critical systems and the critical chips to be developed. Although it is not possible for us to develop all the chips, it is that sometimes the requirement is critical but the volume is very low, and those chips also need to be identified, and we are looking forward to that requirement coming from our various strategic sectors, from our defense, from power, from railway, from telecom. So those critical chips will be identified, and in this sector we'll be identifying and going for the development of the chips. So under ISM will be, there are 6 categories which we have identified: memories, RF, processor, then networking, and sensors. So power, 6 of them. So under each of these categories, we'll be identifying certain chips which need to be taken up for development. So thank you. I'm sorry I've overshot the time. So
thank you very much. And you had the liberty of overshooting because we had started a bit early. But I will request the other speakers to please stay with the time, otherwise we won't be able to finish on time.
Okay.
Would you like to add something before we cover what you?
So thank you, madam, for giving us an insight of an overview of what is MITI is doing, and it is impressive to see that so many schemes have been started, like the especially ones that EDA tools for the academy, like since I'm from the academia, and I'm sure that ISM2 will be very useful in future also. Thank you.
Thank you very much, ma'am, for very insightful information on the MITI, what we are doing, and tying it up in the end to the defense sector. Since we are talking about defense, the translation of what we are developing for civil use into use for the military sector has to, I think we should focus on a little faster and in numbers. That we are not being able to translate into right now. And I'm sure that as we discuss further and we hear further, we'll get to know more. May I now request the second speaker, that is on current profiling and a brief look at the future. I request you to please cover that. Thank you.
Good morning to all. I am very happy and privileged to be among you, and thanks to the organizer of this workshop for giving us opportunity to present the work which we are doing. And as you see that I belong to a DRDO laboratory, that is solid state physics laboratory, and we are mainly focused towards developing semiconductor based technologies, and mainly for defense applications. So it is one of the premier laboratory and working towards self-reliance in semiconductors, and we are looking for a complete solution right from material to devices to products and systems. And we are supported by 2 pilot production plants because we are developing the technologies, but once you develop a technology, you need to scale it up, and scaling up or validation can only happen through a limited production series or a limited production facility. So we have 2 pilot production plants. One is called GATEC, Gallium Arsenide Enabling Technology Center, and other is STAR-C. So GATEC is mainly focused on 3-5 technologies or 3 nitride technologies for RF applications, whereas Semiconductor Technology Applied Research Center is mainly focused on MEMS-based sensors. And we are also interacting with academia and various DRDO labs. And through these 2 foundries, we are developing several technologies, mainly based on compound semiconductors. And we are then extending it for production support to various industries also. And the main domain of work, as I said, the compound semiconductors, and we are mainly focused on 4 verticals. First is this 3,5 technology or gallium nitride based technology for IR applications, and we are developing here HAMT based MMICs up to carbon. And then we are also working towards photonic devices, mainly laser diodes based on gallium arsenide and gallium nitride. And we have laser diodes for near IR application up to 10 watt single emitter. And we are working for VCSEL diodes also. And then recently we have developed gallium nitride based blue-green lasers for underwater communication. And then another flagship program of SSPL is the infrared detector devices. They are mainly based on mercury cadmium telluride and T2SL semiconductors. And we are working on both the categories, the cooled and uncooled, and covering complete spectrum of IR, that is from short wave to mid wave to long wave. And then another area where we are focused in the sensors, they are mainly based on MEMS, acoustic or surface acoustic wave sensors. So I'll briefly give you the introduction of those technologies also. And we have a very good infrastructure for developing these materials in-house, and supported by bulk growth techniques and epitaxial growth techniques. And then we have a very good material characterization and device characterization facility. And recently we have been given the mandate to looking at the advancement in terahertz technology and quantum technology. So we have recently added to our charter a development of quantum devices as well as terahertz source and detectors. So if you look at this slide, silicon is considered to be the material of 20th century, and there is no material which is coming up and going to replace silicon till our lifetime. It is so important, but still you can see there are many functions which cannot be done by silicon. So for that you need other compound semiconductors, so very high speed electronics, light emitting devices, then infrared detectors, ultraviolet detectors. All these needs compound semiconductor, and they are mainly used for defense and space applications. And in recently, many wide bandgap semiconductor devices are coming up, like gallium nitride, silicon carbide, gallium oxide, diamond for power electronics, and complete RF sector is dominated by gallium arsenide, indium phosphide, gallium nitride. So at SSPL we are working on all these materials. And if you see the advancement in technology, what is the major difference between silicon and this compound semiconductor? Silicon technology advancement have taken place because of the process innovations. Material remains the same, process innovations have come, and today we are talking about 1 nanometer or 2 nanometer technology. Whereas in compound semiconductors, advancement has taken place because of the material innovation. So material becomes very, very critical for compound semiconductor technology. So the development of material is one of the very, very critical part of this technology. So if you look at a landscape, compound semiconductors are everywhere, whether it is RF, power, lighting, display, photonics. So we just cannot imagine our life, day-to-day life, without compound semiconductors. They have become so important. And if you look at the market growth, normal semiconductor industry is growing at 7 to 8% CAGR, whereas compound semiconductor, because of their wider applications, they are growing at 13%. These are the projections up to 2030. So they have become very, very important for our critical applications. So at SSPL, we have initially worked on gallium arsenide based devices, and recently we have now, because of the better properties of gallium nitride for RF applications, we are also upgrading our technology to gallium nitride. And initially we have developed gallium arsenide based RF technology, implemented it in our foundry, which is in Hyderabad, and there is a detailed talk in one of the session where my friend Dr. Sai is presenting all the activities with respect to GATEC. So he will be covering all the product portfolio there. But now we have upgraded this technology to gallium nitride. So why gallium nitride? Because of the better electronic properties, and you can see that gallium nitride can cover complete spectrum from wide low frequency to highest frequency with highest power. So for all high power, high frequency application, gallium nitride is the material. And one of the beauty of gallium nitride is that in a TR module, you can compress front end chip in 3 chips into single chip. That is called TR chip. And then I would request all of you to visit the stall where we have displayed this TR module, where normal TR module contains 8 to 9 MMIC chips, whereas these are now replaced by only 3 chips, and we have demonstrated that in the stall what we have developed. And another important functionality of the gallium nitride waste being a direct band gap material, we can get emission in blue-green region. So blue wavelength or green wavelength has got a low attenuation in underwater communication. So it is very, very critical and useful for underwater applications. And this is just a slide which shows that we have presently developed the X-band complete GaN technology, where the low noise amplifier, power amplifiers, and SPDT switches are available. And this technology is completely implemented at GATEC. And the good thing is that now we have opened this technology for private partners also. Expression of interest is already floated, available on DRDO portal, and we are inviting applications from private industries also. Then this is the comparison of the technology. So very few players are there for gallium nitride technology. You can see that the 3 figure of merits are generally used for comparing the technology, that is breakdown voltage, cutoff frequency, and power density. So we are at par with the best in the world. Then we have extended this technology, now X-band technology, in fabless mode to Ka-band, and developed several products which are IPR of SSPL, where we have a Ka-band power amplifier, Ka-band TR modules, and many of those devices are already in display in our that exhibition stall. So you can visit that. And then as I told you that gallium arsenide and gallium nitride being the direct band gap semiconductors, we have developed the laser diodes also. So gallium arsenide based laser diodes are required for directed energy weapon for pumping source of fiber lasers. So we have developed up to 10 watt at 9676 nanometer, and then blue-green laser diode for 450 nanometer and 480 nanometer for proximity fuse and underwater communication. So these are the directed energy weapon, optical communication, and one more category of laser diode, which is called vertical emitting surface lasers. They are VCSELs. So they are used for quantum applications because of their higher spectral purity. So we are working towards development of those also. And these are some of the diodes which we have developed, and presently we have gallium arsenide based diodes with the single emission up to 10 watt, and we are extending that power levels now to 25 watt. And then FCLD fiber coupled laser diodes we have developed up to 100 watt and extending it to 250 to 500 watts. So these are the 3 categories where we have a complete process technology, and this technology is again established at GATEC Hyderabad for pilot production. So chip fabrication now happens at GATEC. And you can see that fiber coupled laser diodes, now we are extending for directed energy weapon 250 watt to 500 watt. So for that, single emission emitter is required to have 25 watt or more than that. So we are working towards that. And in gallium nitride based laser, we have already established a technology for 3 watt, and we are using it for underwater applications. And this complete technology is established at GATEC, and all chip fabrication happens there. And then this is a VCSEL diode which we are developing for our quantum applications, and then distributed feedback laser diode, because of their higher spectral purity, are used for seed lasers or spectroscopic applications. So we have recently taken up a project, and we are working towards developing this also. And then there are various bulk semiconductors which are very critical. So one of them is the silicon carbide. Silicon carbide being wide bandgap material and very strategically controlled. So this complete ingot and wafer fabrication technology has been established at GATEC, and we have already floated the EOI, and we are inviting the private partners to take this technology and scale up it for the production. Presently, we have 4-inch silicon carbide technology, and we are now upgrading into 6-inch also. And recently, we have started working on developing the power devices based on pin diode, Schottky diode, and MOSFET on silicon carbide also. And then there is another category of zinc telluride crystals. They are non-linear crystals, and used for terahertz application. So we have developed this, given it to some of the users, and now user is one of the user is TIFR, and they have certified that these are better than what they have imported from outside. And we have already floated the EOI. This technology is also available. And then cadmium zinc telluride single crystals are used as a substrate for mercury cadmium telluride for IR detector. So this technology we have developed, and it is now transferred to CELS Hyderabad, and they are producing it for all the users. Then another recent achievement is PMN PT single crystals, because they have a very high D33 component, almost 4 to 5 times of the normal PZT materials. So they are very good for your sonar applications. So this material recently developed and given to the user lab with the as per their requirement, and the D33 is of the order of 1800 to 2000, which is 4 to 5 times than a normal PZT crystal. Then infrared technologies, as I told you, that we are working on complete spectrum, where we are working for cooled, uncooled, and recently we have achieved very good success in MWIR detectors, where mainly the target is to have it for the missile seeker application, and the imaging has been tested up to 5 kilometers, and then bolometer room temperature images have been seen, and now we are scaling up these technologies by bridging the gaps and making them user ready. Then this is the complete technology steps where we require, these are the technologies where we have completely 95% all these indigenous technologies have been established. Another important technology in this is a cooler, which is Joule Thomson cooler, and all our detector applications for IR were importing this, but now we have developed this technology, and I am very happy to share with you that we have developed it in one private industry, that is Technocraft, and recently we have got orders from SCD Israel, who is the supplier of these detectors worldwide. So they are taking these detectors from our industry partner. And these are some of the sensor technologies which we have already developed. They are SAW-based, MEMS-based, PZT, and these detectors are already sensors are already available with technology. Then futuristic technologies, we have recently, as I told you, for terahertz application, we have developed PCA technology, photoconductive antenna-based technology based on low temperature gallium arsenide, and we have demonstrated the power levels up to 160 microwatt with the bandwidth of 1 to 4 terahertz. Then indium phosphide based HEMT device technology is also taken up for terahertz application, and we are working towards developing these devices with 70 nanometer gate with a cutoff frequency of 300 gigahertz. Then one of the very, very critical technologies, photonic integrated circuits, where we are combining electronic as well as photonic devices to extend the present performance of all electronics. So those initiatives have also started, and this is the future technology. This is going to take over all electronic applications in future. So this we have also initiated at our laboratory. And last, I will end my talk with the quantum sensors. As I told you that we have ventured into quantum technology also, and we are working towards developing atomic clock and atomic magnetometer. And for that, we are developing the components. The first component is VCSEL, second is micro fabricated alkali vapor cell. So we have already initiated, and fair amount of success has been achieved in these. And I would like to end the future of the technology will undoubtedly be shaped by ongoing evolution and impact of compound semiconductor, as they can do things which cannot be done with silicon. Thank you very much.
Thank you very much for the very enlightening talk, and it makes us very optimistic to see all the technologies that we have developed, and we will see it translating into production, like you have mentioned right from the beginning. Anything you'd like to add?
Yeah. Thank you, Dr. Rawal, for giving this insightful journey of the SSPL. And of course, as Dr. Rawal has said, compound semiconductors are very important because they are one of the best things about compound semiconductors is that you don't have to really go down to a very low, very small channel length. You can work on the long channel devices also, which is very useful. And they are into manufacturing a lot of devices, and as he has mentioned, the chips they are coming up. So I wish all the best. Thank you.
I think I covered. Thank you. And it's very heartening to see that we are developing all these technologies and looking forward to our quantum also going ahead. And there were some startups who are claiming that they can do or handle quantum through silicon itself. I have asked for the presentation from them subsequently. We will see that. Thank you very much. And I would now like to invite Armed Forces Requirements Trial Services Technology.
The chair, panelists, dignitaries, and DG CENJOWS, SA to CISC, industry, partners, officers, ladies and gentlemen. Good morning and Jai Hind. At the outset, I'd like to express my gratitude for having given me an opportunity to express our views on the requirements of the armed forces in semiconductors. You know, when this topic was given to me, I was actually thinking that should I take on this topic or not? Because when we talk of armed forces, our requirements, we don't buy semiconductors. We buy the complete equipment. We buy a system. We buy a platform, or say a weapon system, but not the semiconductors as such. And that too, when one interacts with the ecosystem of semiconductor, there's a vast difference in the terminologies and in whatever I've heard even in this last about half an hour, 45 minutes. It's just gone, half of them have gone above my head. Because here, the industry, the semiconductor ecosystem talks in terms of nanometers, fabrication nodes, wafer yields and all. Whereas we in service, we talk about our operational requirements. We want the reliability under fire. We want the zero tolerance for failure. So I thought that these two are quite different, I would say two extremes. But then I also take it as an opportunity to bridge this technical communication gap. And that is where I think I stand here as a soldier. And when I look back from when one started my career about more than 35 years back, we had Vision tanks with radio sets in that, which was called as VRC 353 or radio set 123M, which came in T-72 tanks. They were all wall-based. So big walls, obviously the size, the power requirements were higher, is to get heated up, manual tuning and all. And from there, now we have come to these small, these nanometer-based, the semiconductors, which are giving rise to the industry in terms of, or say to the applications in terms of drones, satellite communications, or satellite technologies and semiconductors, and AI-enabled targeting. Now, in all this, if you see, the character of warfare actually has fundamentally changed. Earlier, combat effectiveness was actually largely determined by the number of platforms, number of tanks, artillery systems, and like that. But today, the real differentiator in the technology is the technology embedded within these platforms. And at the heart of that technology lies the semiconductor. Well, these semiconductors have actually transformed the warfare from being platform-centric to being information-centric, or I'll say even decision-centric. So today's battlefield is defined by the ability of that how much information can we collect, how faster can we process it, and how faster can we act on it better than the adversary. So if we see that from my perspective as a soldier, I will say that semiconductor have become as critical as ammunition, fuel, or logistics. And chips are not just components; they are the nervous system of this entire modern military power. So therefore, what becomes critical is that if these chips are not trusted, they are not available when we need them, or they're not under our sovereign control, then our combat capability itself becomes vulnerable. Hence, it's an operational and rather strategic imperative. At every stage of our operational cycle, semiconductors play a central role. They power the sensors such as radars and infrared systems, enabling us to detect threats. They process massive volumes of data using advanced processors and artificial intelligence, helping commanders make sense of complex situations. They also enable secure and resilient communication networks, ensuring that information flows seamlessly across the battlefield. But in military terms, this is about compressing the OODA loop. That's observe, orient, decide, and act. And in the terms of semiconductors, try to call it as sense, process, network, and strike. Semiconductors are the invisible engine that drives this entire loop, making them central to modern warfighting. Now we see that our dependence on semiconductors is both deep and all-encompassing. Across the three services, I'll say that there is virtually no operational system today that does not rely on semiconductors. So in the army, even a soldier, forget the other say weapon systems or the platforms. Even a soldier at the technical level, he is using radio, navigation systems, sensors, all which he is carrying on himself, which are dependent on chips. So what is important to understand is that this dependence is not static. It is growing day by day. And as we move towards the network-centric warfare, the autonomous systems, the AI-enabled operations, the density and importance of semiconductors in our systems will only grow further. So therefore, this makes our reliance not just significant, but strategically critical. So from an operational perspective, our requirement spans multiple categories, and each supporting a different layer of capability. We require processors and systems on chips that act as the brains of our systems, ranging from simple microcontrollers to high-performance computing units. We need radio frequency semiconductors, particularly based on gallium nitride and gallium arsenide, which are essential for radars, electronic warfare systems, and communication networks. We also depend on networking and communication integrated circuits to enable secure and high-speed data exchange across platforms and formations. Power electronics, including the MOSFETs and IGBTs, they're critical for energy management in platforms and systems. In addition, sensors and mixed signal components, such as analog to digital converter and digital to analog converters, they allow us to interface with the physical world. So memory systems, both volatile and non-volatile, are required for data storage and processing. And finally, the hardware security elements, including secure boot and cryptographic modules, are essential to ensure trust and integrity in all systems. So each of these categories is almost indispensable, and together they form the backbone of the modern military capability. So let's see what are the specific semiconductor needs of the Indian Army. Let me get specific. Now, for the Indian Army, our requirements are actually shaped by the need to operate across diverse and extreme terrains, while ranging right from, say, the deserts to the extreme cold. That means anything from -40, -50 degree to +55 degrees centigrade. And apart from the other challenges of the humidity and the other aspects of the wind speed and icing and all that. Okay. So let me translate these under 5 domains or applications. The first one is the communications and network. We rely heavily on semiconductors for battlefield management systems, which provide commanders with real-time situational awareness. So the modern battlefield is a network when every soldier, every vehicle, every sensor, every commander, they must be connected in real time under adversarial real electronic warfare conditions. And this demands ruggedized, low power, and high frequency semiconductors, specifically for software-defined radios, mesh networks, and jam-resistant communication systems. So today, most of our, I think, the SDR systems, they are the chipsets for them are imported, while the software may be Indian, but the silicon is not. So that's is something which we need to address. Second one, the electronic warfare. The electromagnetic spectrum is a battlefield in itself. Now, our electronic warfare systems, they depend on high performance chips to detect, analyze, and counter the enemy missions. Thus, we need the chips that can detect, classify the frequencies, and jam adversarial frequencies in milliseconds. And these are high-speed signal processing chips, maybe SX and FPGAs, designed specifically for EW applications. So this domain, again, I think demands domestic development, while we have heard good inputs from the previous two speakers, what all is being already done. The third one is the surveillance and reconnaissance. We require semiconductors for ground-based radars and fire control systems, which are essential for surveillance and targeting. From satellites to UAVs to ground-based sensors, surveillance is chip-intensive. The image processors, the edge AI chips, the navigation systems on chips. These are the engines of our intelligence picture. We are beginning to field, we are getting, say, so much of these Indian aerial systems and unmanned aerial systems, vehicle platforms. But the sensor payloads, the onboard processors, I think we are heavily dependent on imports. So therefore, we need these indigenous ISR grade chip solutions. Fourth one, precision munitions and guidance systems. Now, modern guided munitions, whether it be say in terms of Pinaka rockets or Astra missiles or the anti-tank guided missiles, they all rely on inertial navigation chips or seeker head processors and guidance control units. So the guidance chip, let's say in a smart munition, can be as consequential as the warhead. Because a compromised chip in a guidance system is actually worse than no chip at all. So therefore, we need zero trust semiconductor supply chains for every munition we field. And fifth one is the artificial intelligence at the edge. So this is perhaps the most transformative requirement. We are moving towards AI-enabled battle space management in terms of predictive logistics, autonomous surveillance, AI-assisted targeting, and real-time translation of adversary communications. Now, all of this requires AI chips that can run neural networks in power-constrained and bandwidth-limited battlefield conditions. Now, increasingly, we are also integrating chips into soldier systems, like I mentioned earlier, including wearable devices, navigation tools, and communication equipments. So thus, our operational environment, we see right from the high altitude areas to deserts, they impose additional requirements. Chips must be rugged, energy efficient, and capable of functioning reliably under extreme temperatures and conditions. So this makes our requirements both demanding and unique so far as the military requirements are concerned. So to summarize, I'll say that the operational superiority dictates three imperatives: performance in terms of high frequency and edge AI processing chips, ruggedization in terms of radiation hardened, corrosion resistant, temperature resilient chips, security in terms of zero trust supply chains, and untempered guidance. So this military effectiveness is no longer just about the platform. It is fundamentally constrained by the performance, durability, and security of the underlying silicon. So how imperative it is to have this silicon sovereignty? And can we have it, or are we moving really towards it? Well, I think the answer to this lies in another question. Do we really need cutting-edge semiconductor nodes for all defense applications? May not be. It is important to understand that not all defense applications require the most advanced semiconductor nodes. Many systems can function effectively on even say 28 nanometers, 45 nanometers, or 65 nanometers technologies, which are generally mature. So there is a significant advantage in this case for India. This will allow us to focus on building capabilities in these nodes without immediately competing with the global leaders in cutting edge fabrication. And at the same time, we can selectively invest in advanced technologies for critical applications. This approach will also, provide us a practical and phased pathway towards the semiconductor self-reliance, balancing ambition with feasibility. Now, from an army perspective, I see that Bharat Secure Chip is something I think which we can really we need to capitalize on. And I see it being integrated across multiple layers of our operational architecture. And the true strength, I'll not talk about this Bharat Secure Chip. I'm sure the August audience is all aware about it. The true strength of this actually lies in its ability to provide a common secure hardware foundation across the Indian Army, Indian Navy, and the Indian Air Force. And by standardizing on a common family of chips, we can significantly improve interoperability between services, which is critical for joint operations and integrated theater commands. It also simplifies certification, reduces costs, and enables the development of shared software ecosystem. And from a strategic perspective, if we see, the Bharat Secure Chip actually supports the transition to multi-domain operations, where land, sea, air, cyber, and space capabilities are integrated seamlessly. So it is therefore not just a technological solution, but an enabler of joint war fighting. And this layered approach ensures that we have a common, secure, and scalable computing backbone across all levels of operation. Apart from this, it also simplifies integration, enhancing the interoperability, and strengthens cybersecurity. So I think the Bharat Security Chip initiative needs to be optimally exploited towards achieving military technological sovereignty in semiconductors. And finally, my recommendation. I think armed forces, are the users of the final product and therefore seek the most efficient constituent technologies, semiconductor being one of the most important ones amongst them. So we must capitalize on the India semiconductor mission by having representation from the three services. We must be one of the stakeholders in semiconductor mission of the government of India, so with a view to convey our requirements in an intrinsic manner. And finally, to summarize, to conclude, I'll say the armed forces will fight with whatever they have at that moment when they're required to fight. But I think it's our responsibility, joint responsibility of everyone in the ecosystem to ensure that the systems that the armed forces rely on are built on trusted, secure, and indigenous technology. While the semiconductor is very small, like I mentioned initially, but sometimes smaller than a human cell, but it carries within it the sum total of our technological ambition. It carries the future of our communications, our weapons, our surveillance, and our decisions. So hence, the indispensable requirement of strategic autonomy in this field. With that, I would like to end and once again thank everyone. Thank you.
Thank you, Man. Very well put across. And the requirements are quite clear in the industry, and all the players are here. You could not have put it across better as to why we need this to kill this dependency of semiconductors across the entire chain, not just the end product or something in the middle. And yes, it is the heart of everything that is going to happen. And we have already reached, like we heard, certain technological achievements as far as up to 28 nanometer is concerned. But if you want to short circuit, jump, go ahead of the curve, use whichever term you want. For AI, edge, and quantum, we need to get into 5 to 3 nanometers. And that's the way we are going. Thank you once again.
So very insightful talk given by Major General Mohan, and of course, and as we all of us know that nowadays the wars are all technology based. But he has also very rightly put that for everything we don't need a cutting edge node. We can depend upon the bigger nodes also, and that is where the requirement is that it should be in partnership between the industry, as sir has said that industry people are here, the R&D sector is here, DRDO is doing a good job. NAVIC came because of the requirements from the armed forces only, from ISRO. So we would like to see many more such things coming with your requirements. Very well put up. Thank you, sir.
Well, thank you. Now I invite, I think, our final speaker for this session to please come and speak on. Yeah.
Jai Hind, sir. I thought it's the perfect forum to show my heartful and humble salute to the esteemed forces who had and having phenomenal contribution in the prevailing scenario, and we are happy to serve and quench the technological thirst. A well-deserved round of applause for all of you, sir. Distinguished dignitaries on the stage and off the stage, I'm just here to share some of my knowledge and my views on resilient computational resource for defense applications. Of course, Major General Mann has given a fantastic path for me to take it forward. It has eased most of my task, so we know what is exactly the requirement. But as we all know, the semiconductor technology is revolutionizing various sectors, starting from commercial to defense and space. Before we get into that, we would like to, I would like to just say a couple of requirements which is essential specifically for defense and space. Of course, defense is entering into space era also. With this, and this is my story, semiconductor applications, a glimpse, and prominent design challenges specific to design applications, defense applications. Case study, how we solve one of the challenge which we faced in space products, a glimpse of it, and efforts to build a resilient semiconductor hardware for the prevailing environment. Inputs to evolve an ecosystem, because as the previous speakers were mentioning, ecosystem in a semiconductor is essential, and it is the most important part to develop the indigenous chips and to build a resilience hardware for defense applications. I'm just giving a glimpse courtesy Google, so you can see the various sectors of semiconductor applications. You can name anything. It has a semiconductor in the form of field programmable gate arrays, application specific integrated circuits, microcontrollers, whatnot. It is all there. And for defense, similarly, most of the, all the electronics or all the weapons or the warfare equipments comprises of mission computer, you say, or an onboard computer or a processor or any applications uh, which gives a precision, guidance, control, and execution at the point where it is required. Well, so moving forward, as the previous speakers have very clearly told, it is a network centric layer we are considering now. There's no more individual decisions. It's a kind of integrated decisions where we use various layers to take a decision: effect layer, info layer, and satellite layers. And today, the precision depends mostly on the network centric based systems. When we move forward, what kind of challenges we face specifically for defense, and what is making us to move towards the indigenous or the homegrown chips, which is the need of the hour. The first figure shows, anyhow, the adversaries we are categorizing, which is above us, and other one is the same layer where we are. So above us, if you see the radiation, which is a kind of energy or the effects which is coming from outer space. We don't have to worry much about the figure because even NASA doesn't know where it is coming, but it is continuously bombarding the earth, where the chips or the semiconductor, what a general commercial equipment uses, will not be working at more than an altitude of 20 kilometers, but now it is even prevailing more at the ground because of this technology scaling. So what happens? The bombardment happens on the chip. Now I am just giving a glimpse as a researcher. When it bombards, it translates the data stored, whether it is, if you stored 0, it becomes flips to 1, and if data stored as 0, if it is 1, it becomes 0. Ultimately, the computational platform, what it uses the data, it is now changed. So the basic architecture to mitigate the effect is by using radiation hardening, which is not available, and it is again strategic based. So this brings in the semiconductor in-house development, where we are going to build some kind of algorithms and to protect it from the gamma rays or the cosmic radiation. The second challenge is hardware security. As we all know, the system on chip or an ASIC or any of the computational platform which is being used, the fabrication, of course, it's outside the country. So when it comes back to us, is it only working for the program what it is being done, or it is doing any additional work? That's a big question, and it's a big challenge also. It's not easy to identify or separate the kind of functionalities which is inbuilt. So again, this calls for an indigenous development, where we can see various kinds of adversaries which has been ported. Now, making this or keeping an eye on these two challenges, definitely we require an indigenous initiative. In case of space radiation or the kind of cosmic radiation effects mitigation, we would just walk through a quick glimpse on how we are trying to tackle, and subsequently we want to give a path towards building an resilience hardware for the defense products. So transistor miniaturization or the scaling, it imparts new challenges on signal integrity, timing, and leakage of power, especially faults which we say due to space radiation. Radiation hardened processor technology is expensive and very it's export controlled. As I told you, effects of radiation is prevalent even at the ground level. It has been detected. The miniaturization or the scaling, it has made it to happen even at the ground due to its feature dimension. So we can ask, this is not the first time we are talking. Now the space is launching satellites and things like that, but how it is getting done? So radiation hardening techniques, traditional techniques, hardened processor, which is export control, will not be available for defense or specific applications. Only for societal things is available. Shielding, we use tantalum to shield. Of course, it takes a hit on the actual payload. So that's how the shielding is not highly recommended. And also, it has some dosage on the environment, so which is prevalent again. So approaches what has been available, an adaptive design using genetic based approach we have seen, and selective modular redundancy based multi-objective optimization and partial reconfiguration. This is one of the specific techniques which is used in kind of FPGAs, where we call field programmable gate arrays. And we have measured the rate using Weibull and exponential with log normal precisions. Prediction, we have used single event error rate. We used rectangular parallel pipe method, where again it's all available in the literatures, where this is one of the efficient technique which says on how to predict the single event effects. Some of our research and adopted methods, we used Weibull, where we can see we had an area of divides based on dimensions, and with using Weibull curves, we were able to emulate the fault, and we have used adaptive GA for healing. So primarily, when an bombardment happens, when an fault occurs, it tries to heal by itself, and MMO based selective TMR as a design approach, and partial reconfiguration for self-healing. So what is the kind of outcomes we've seen? Resilient architecture for COTS for space electronics, and a kind of ecosystem we have built with academia and startups, where now we are moving forward to scale it up for the other systems also, where the space, other than space, we have commercial sectors also, which has been very essential, like banking and certain sectors where they are working with us. So moving forward, what kind of possible methodologies which will give more constructive meaning to develop the resilient architecture for the defense? So we have different phases and challenges, possible ways to mitigate, and possible technologies or process can be envisaged or agencies. Electronic hardware system design comprises of basic components, active, passive, intelligent components, microcontrollers, processors, SOCs, and programmable ASICs, subsystem integrated with indigenous design. So the challenge here is, when a system is being given to us, is the system is really from the OEM, or is the system is trusted? Is the system does only the job what is being required? So the component-wise screening, sufficient mechanisms in place, as we have quality and reliability inspection methods, which can really take good approaches. It is at organizational level. So the basic components are active passive, which is having intelligent components. So the crux, I mean, the important here is intelligent components, originality, and the trusted source. A hardware software based tool using wire or wireless technology may be beneficial, identifies the originality. Like there are technologies based boot sequence, JTAG, checksums, QRs, digital signatures. So this can be taken up at national, international level. The device systems, applications to be developed with OEM. This can be used by designers, developing agencies, and users. Subsystems, really the originality, integrity, and trust. So indigenous design approaches where it will enhance the trust, where we are looking into the fact. Some encryption mechanisms for protection also we are trying to bring in, where real Atmanirbharta approach, that is indigenous multi-layer protection using algorithms, polynomials, evolutionary methods, and stochastic methods also can be seen, which is coming up worldwide. So the phase 2 is design and verification, where IP design trust. We get a lot of IPs and how to go about trust on that. Extensive validation using EDA tools. Even EDA tools are coming up with some kind of layers where we are unable to predict. So specialized testing approaches where SSPL and other agencies have been involved. Validation and verification practices. This can be taken up at the national level, and specialized training schemes and approaches to be evolved. This can be a skill development through organizations and academia with NSMs. Deployment. At the user level, validate the originality, trust, and integrity in the application to functionality. That is basically the user needs this tools and systems, hardware to be developed in-house with OEM. In-house production design methods, definitely it solves the problem. Possible technologies, hardware intelligence, BIST, boot, JTAG, checksums, various digital signatures combines with reinforcement learning, deep learning, or data science of AI, machine learning models can be used. This can be done with national level, OEMs, users and developers, and academia. So at the crux, to enhance the hardware security, which is a challenge too, it's a shared responsibility, vigilant by all. Designers to developers to users, as we are telling one of the approach. Technology for technology. So basically, you have to use the technology to get the good effects or to back out the bad effects. Let's connect, collaborate, and contribute. With this, thanks to you all. Thanks for the opportunity.
Thank you, Doctor, and for enlightening talk and as to what are the problems and a sample of how we can ensure resilient chip systems for the defense. And there are complicated issues which we face, and you have highlighted a few of them for us. I'm sure the audience will benefit from it, and I think you'd like to answer.
Thank you, Dr. Bala Subramaniam from RCI. So he touched upon very important aspects, the radiation hardening effects and the encryption. So both of them are very important issues for defense sector. So good they're working, and as you said that the three says the connect, the collaborate, and thank. So these are the three C's are very important. Thank you.
Thank you, Air Marshal Vora, for moderating this part of the session so well. May I request the chair, the co-chair, and the panelists to join for a group photograph. May I now request our esteemed session chair to kindly step down from the stage and join us at the center in front of the stage for the presentation of mementos to esteemed co-chair and the distinguished panelist. May I now request Dr. Parimal Kumar to present a token of appreciation to our chair, Air Marshal Praveen Keshav Vora. We will now move on to the second part of the first session. The distinguished speakers of the second part of the session are Mr. Asghar Mohammed, who started his career as a RF design engineer and has worked with GETEC DRDO. With over 30 years of experience in radio frequency semiconductor industry, he's played a key role in RF design and innovation. Mr. Sunil Khatana, CTO and co-founder of Cloud Photonics Private Limited. He's a technology and engineering executive with over 25 years of experience in optical communication and sensors. Professor S. Sundar Kumar Iyer, who's a professor in the Department of Electrical Engineering at the Indian Institute of Technology, Kanpur. Currently at IIT Kanpur, he along with his team is developing printed solar cells on paper substrates for commercial applications. Professor Manan Suri, who leads the Neuromorphic Hardware Research Group at IIT Delhi and is the founder of Chiron AI Solutions. He was selected by MIT Technology Review, United States, as one of the world's top 35 innovators under the age of 35. Professor Suri has successfully led the development and deployment of multiple indigenized deep technologies. Dr. Ulupi Bora, Distinguished Fellow at CENJOWS, holds expertise on the Indo-Pacific, focusing on Japan's security policies, maritime security, and the ecosystem of critical and emerging technologies, especially semiconductors. Mr. Sunil G. Acharya, Director, Semiconductor Future Accelerator Lab, has been advising the Karnataka Digital Economy Mission and several other companies foraying in the semiconductor industry in India. He's an entrepreneur, investor, and mentor to several IT and semiconductor startups. Dr. Abhinav Mathur, who's currently serving as the advisor to the board at Etero Recycling. He's a technology strategist and policy advisor with over 3 decades of leadership experience spanning government, industry, entrepreneurship, and social sector. May I request all the speakers to please take their seats on the stage. May I request the speakers to deliver their views and share their content in the order they were called. Thank you.
Hello, everyone, distinguished dignitaries and delegates. I represent a company called Agnet Semiconductors. It is the only startup in India which is working on the gallium nitride technology. And the objective of establishing this company in the startup sector was, because this gallium nitride comes under ITAR restrictions, you cannot get the devices freely available, even if you want to pay for it. I will tell you an example. Before starting our X-band project, we want to have some X-band device from MACOM, and we ordered the device. We paid the money for them, and then Operation Sindoor started. They kept the money for 6 months, and then they returned the money, saying that we cannot give this device to India. So these the restrictions what we face in the semiconductor ecosystem when we depend upon the foreign semiconductor companies. So the objective of this company was, to be self-reliant in ITAR restricted technologies, and by designing and developing high-power modules for defense and space sectors, and to establish a secure domestic supply chain, so that this will ensure the availability of these critical components during geopolitical tensions or conflicts. This is a Section 8 company. It's a spin-off from IISc Bangalore, founded in 2021. We have got some 30 employees who are experts in their own domains, like modeling sector is there, reliability section is there, and the design section is there. It's a vertically integrated company from development of epitaxial wafers till the delivery of the power modules and RF devices. We have got 17 years of GAN research from at IISc Bangalore. We have got professors who are our founders, who are the pioneers in their own device modeling, device physics, and material science. So as I told, we make our own GAN wafers, GAN epitaxial wafers, okay, and then we work with the customers in solving their problems. Why we have selected GAN? Because there are many technologies, gas is there, silicon carbide is there, gallium indium phosphide is there. But why we selected GAN? Because GAN comes across as a compact, efficient, high power efficiency, and high reliability. They have got a very good thermal dissipation, and high power handling capabilities. We can have the recent example of Virupaksha radars, in which all the 24 TRMs are being replaced from gas to GAN. And also this Uttam radar, ASA radar, in which we are this being upgraded to GAN technologies. So we have got a clean room there in-house, and which caters to this wafer and device capabilities for a reliability section, for for fabrication sector, lithography and all this. So this I want to concentrate on it. We have started in 2021. Then it was a COVID affected time. Slowly we are getting into the groove, and so but within 2 to 3 years timeline, we had developed all these products to strategic sector, as well the private industries who are working for the defense forces and the space sector. IM FET S-band, it is called as internally matched FET, wherein totally matching can be in an internal package. So that we have developed for the first time in India in the private sector, IM FETs. 2 MFETs have been delivered, and the UHF we are targeting, and for this all these radars, walkie-talkies, drones, jammers, and telecom for the application side. And the projects in pipeline, what we are discussing with the customers are S-band for jammers, X-band 200 watt radars, UHF 500 watt for radars again, and different radars for the strategic sectors. When the customer comes to us, we discuss with their operating frequency, output power, input supply voltage, and efficiency, and then we conduct our technical element with the customer. We co-opt the customer from the design to the delivery stage. So you can, for any further discussion, we have got a stall here. Stall number is 8. You can come and discuss with us. Thank you.
Cloud photonics.
Hello, everybody. It's an honor to be here. Thank you for inviting me to speak. It's a little bit nostalgic and emotional for me. In my third generation, I'm the only one who didn't wear off green. That includes my wife's family. So, people in uniform, thank you for your service. Really mean it. So, I'm here to introduce Cloud Photonics. We are design and manufacturing company. We make photonics a signal processing company. Photonics is the key element of the new generation technology. It's a new frontier. I know we talk a lot about semiconductor and the progress that industry have made, but photonics is really the next frontier. We're primarily focusing on communication and sensing. Just the very nature of photonics, it's 1,000 times more capable than any known RF frequency, just by the very nature of where it lies in the spectrum, in terms of its capability to resolve things, resolve objects, in terms of the communication bandwidth it provides. So this is something we absolutely cannot ignore. This is where the next next pronus will come in technology. Cloud Photonics is founded by people who've been experienced in the industry for about 30 years, and we bring basically different aspects of the technology in terms of manufacturing, in terms of signal processing, in terms of the semiconductor, compound semiconductors, in terms of the RFICs that are needed to make the whole thing work. We're based in Noida and Bangalore, and you're welcome to visit our booth here as well. So as I said, the two key areas that we're focusing on is communication and sensing. We make transceivers that go from 1 gigabit all the way to 400 gigabit transmission, up to 600 kilometers now, and we're working on to extend that to 2,000 kilometers. We design transceivers, so we control what goes inside them, so we can make them secure. We can make special encryptions that are needed for particular applications by defense or for security reasons. We specialize in lasers detectors that are actually used inside and develop signal processing that's used to make them for communication purpose. We also hold key technologies in sensing, especially for 3D sensing that's used in LiDARs, and that's beyond time of flight LiDARs. We also do FMCW LiDARs. These are used for ranging and detection. That use plethora of devices in terms of SPAD, SIPM, APDs, edge-emitting lasers, VCSELs, fiber lasers, and solid-state lasers. And the thing I want to say here is in terms of how fiber optics plays into it. If you see in Ukraine today, you'll see in the farmlands just spaghetti of fiber optic cables. It's not that they're growing cables. That cable is used to control the drone because that's the only anti-jamming you can actually have to not have anybody intercept your drones. Another thing a bold statement I want to make is radar, which we have known since World War II, is not the right technology for detecting drones. As you know, 3 U.S. airmen lost their lives very early in skirmish with Iran. It's not because they could not shoot down the drone. It's because they didn't see it, even if when it was there right in their premises. There are other techniques that are there which are much more powerful, enabled by photonics, that actually enable to detect UAVs much more effectively than the radar technology. If anybody wants to discuss why radar is not, I'm happy to discuss that. It's a very, very hot field, and it's a technology that many countries are after right now. So this is our R&D lab in Noida. We design there, we manufacture there, we test there. These are tested to very high standards. Some of them are MIL standards, some of them are Telcordia standards, depending on what the actual application is. These are some of the reliability testing we do in-house on each of the products that we produce. And I want to maybe leave here with with the founding team that's there. I'm not going to go through the profile, but each one of us came from very specific area, bring in very specific skills in terms of the technology, different aspect of it, in terms of commercialization, in terms of its manufacturing, in terms of its process development, spanning from RF to photonics to calibration to signal processing. So again, we're an Indian company. All IP is owned by the Indian company. We design and manufacture here. We do custom design. So if you have ideas on things that you want to implement it and you're worried about about security, we are very happy to talk to you. Thank you very much, and Jai Hind.
Good afternoon and Jai Hind. It's really an honor to be here, and I really thank Major General Ashok Kumar for inviting me for participating in this, and of course Dr. Ulupi, who managed all the logistics and helped me come here. So thank you. So at the very start, I guess what I'm going to show, I can always pass it, and you can always get a lot of the things. In fact, much more in the on the websites. But I do feel that all the basic ingredients needed for making semiconductors happen is already here. But the main thing is about putting them together. And as has always happened, and it has happened in other countries too, probably the armed forces, and that's where I really admire what CENJOWS and others are doing, they can streamline what is needed and give a purpose to make it happen. So in the academic front, I'll try to show where that is, I'm talking about IIT Kanpur, and I know it's true in many other institutes as well. All the basic ingredients are here. So what is semiconductor manufacturing ecosystem? So I have split it up this way, although I know that there can be many other ways in which one can split it up. Okay, doesn't matter. So first, if you look at it, the top row is mostly software driven and mostly intellectual, and maybe that also requires a lot of investment. And luckily for us, the MeitY, Sunitaji was here earlier. They have actually championed a lot of those, TCAD and other stuff. So design modeling, device modeling, and integrated circuit, we have a very strong base in India. The second part, actually, I would include materials, physics, chemistry people, and also the process integration. In this materials and process also, I feel a lot of stuff is there. Probably where we need to focus would be process integration, but sometimes you need a lot more resources for that. But at the same time, that's something that is something you have to watch out for. And chip packaging. This is something, it's an afterthought, but honestly speaking, this is another thing that India should get in, especially for making systems which can be really cutting edge. And today there are smart systems that are possible thanks to chip packaging. In all these areas, there is expertise that exists at IIT Kanpur. If you look at it another way, what does the academic part of the ecosystem, what it will provide? We have academic courses on par with what is there all over the world. Abe-san was mentioning earlier that there are lots of Indians in Japan. So, and clearly it's not a surprise, not just Japan, all over the world. So the training part that is available, and anybody who wants to know more, courses and other things can be organized. Lab process training also is there, and not just IIT Kanpur, I know in many academic systems in India it is there. And then prototype development. I didn't want to emphasize on this today because of the time, but that's something that will give a purpose. So whatever you are doing, if you can do it towards that prototype development and eventually what the industry needs. And it is in the last two part where I feel CENJOWS and others can play a very important role. So IIT Kanpur has all the expertise. Ecosystem at the institute addresses all aspects. We do work with a lot of industries. In fact, we have DIA COE. Dr. Mangal is here. They actually have set up this facility, and not just in all the academic institutes. So that is one channel through which a lot of work can be done. And then clear target is all that is needed. People from the industry and from the armed forces, if you have a clear target, something needs to be done, backed by resources, of course, I'm sure it can, a lot of things can be achieved. Whatever can be done anywhere in the world. So now I will go through the various parts in a quick manner, because I think we can spend a whole day discussing what is there at IIT Kanpur. And similarly, I would assume in all the other institutes as well. So these are the people who are primarily involved in device compact modeling. Gallium nitride we are hearing, Yogesh Chauhan has been leading that effort. So essentially, this is the basic these are the various aspects of compact modeling. You measure the device, and based on that, you develop models which can quickly predict. Now, what is important, and then you compare it with the measured data, and then you try to finally get the compact models which industry can use. Now, they have lots of projects that are happening, not just in India, but from around the world. But the critical point here is India will need to build in-house models. Right now, they are working with industries around the world. So these in-house models will help us tune better and cater to the needs of the country. Then I would like to talk about IC design. As in many parts of the country, certainly IIT Kanpur is a very strong circuit design group. So these are the different people who are involved. And not just that, it's not just about designing and teaching in class. These are all chips that have been designed in-house, and these are actual images of chips that are designed and made on silicon. As was pointed out, many times you have to have it fabricated outside. But the IP, 70% of it, as was told, is what is the value of the chip. And we can actually design things that are unique for India. Of course, we have to see how to protect it when we send it out for fabrication, but there are ways of doing that. The key highlights, they have done quite a few projects. Of course, academically accomplished, my colleagues are really done very well, and significant amount of funding as well. So just to flash, these are the various projects they have taken up and taken to conclusion. And these are the aspects where they feel they can contribute to the defense, and other ideas are also welcome. Best would be, of course, to visit us. We'll be very happy to host you, and you can get to know what is needed. So these are the various topics where they have ongoing projects, they have demonstrated things, and they feel something can be done. In fact, recently we did propose something to DIA COE also. Hopefully that also will come through. So that's a very good project. Next, I'll go to device fabrication. This part, I think across the country is sort of scattered, although it has sort of come together in some of the bigger institutes where more funding has gone in. MAITI has supported INUP and certain other programs where they train people. But in this device fabrication, it is a small subset. It's spread out across various departments. Physics department, material science also, they do a lot of fabrication. Others, I have emphasized mostly what is there in electrical engineering in this particular case. And they are also looking at some of the latest devices, neuromorphic computing and quantum devices also they are looking at, spintronics. So these are the various expertise. And as far as fabrication is concerned, there are two aspects to it, unit process and integration. Unit process also, we have the expertise in some of the areas where we can collaborate with the best in the world as is required, and whatever industry needs, we can help in developing those processes. And prototype development, I think, is one of the important things. This is increasingly emphasized by all funding agencies. There should be a purpose why one is doing it. So we have quite a few centers, and one of the centers is National Center for Flexible Electronics. DIA COE is also has just started last 2-3 years. There a lot of projects are coming up. It's with trying to build complete systems. So I've given a snapshot of some of the people involved. And some of the things are very simple. Actually, if I may indulge one small thing, two of the people who were in the armed forces who gave talk earlier, we found that both of them emphasized the need for small things as well. There was a mention about ant getting into a trunk of an elephant or want of a nail. And then also was told that existing technologies need not be cutting edge. And that is so very true. Okay, Rahiman Baden dekh se laguna dijiye dari. Jahan kaam aave sui, kaha kare talwari. So sui and talwar are both are important. I'm not saying sui is superior to talwar, but what we need is we have lots of low-hanging fruits, and it is possible to take them to products. So I'll require CENJOWS to also the two parts. Strategically, of course, we should look for future, but tactically, I think we should harvest all the low-hanging fruits. So core expertise is there. So these are all products. Some of them we are working with the defense as well. Heater jacket is something we are trying to, Central Command has contacted us, and we are trying to pass that idea so that it's robust, and minus 35 degrees when soldiers will be able to wear it and go around. So we have also some basic facilities for prototype as well as almost quasi product development. That's a roll-to-roll printer. And there are certain aspects of electronics which we can do in-house, all the way from materials to final products. So semiconductor packaging, as I said, this is an afterthought, but honestly speaking, we have expertise in India. Nilesh Badwe has worked in Intel for some 7 years or 8 years. He's come back. He's created a center for training on packaging. That's low-end training, but this is what you need for industry. But what is more important is he's also working on system in a package, and this is the future. Low performance things, when you bring them together in a synergistic way, it can outperform what may be done by complicated circuits. So this is one area I feel strategically we should look at, especially in the context of armed forces, because you have dedicated requirements. So in that sense, this is something very interesting, and you are welcome to come and meet meet us at our institute. So I would dare say Indian academia has all that it takes to make a semiconductor ecosystem. Money was an issue. No longer I think money is an issue. Maybe the culture and decision-making aspects is something we have to streamline, which is happening. We need to go forward. IIT Kanpur, to my best of my understanding, and support all the basic components that are there. We have wherewithal. Similar is the case in all the other IITs and all the big universities which have been there for around for some time. And a clear directed target is there. Then that's why I'm excited to participate. And when I was told to come, I came. If you can give direction, we will be there. Thank you.
Good afternoon, everyone. Leadership of CENJOWS, distinguished officers, fellow attendees, co-panelists, Dr. Ulupi, thank you for the coordination. So I would like to share some perspectives on the topic based on some of the areas that we have been working on or we have been doing R&D, both in the lab and as well in general at IIT Delhi. And then how, what is the relevance specifically when defense is beginning to think about semiconductors. So I've just tried to outline it in this way. I'll cover 3 different technical aspects, that is storage, compute, security, and then end with making some recommendations. So first thing that we need to be aware of, if we look at the semiconductor revenue split, and this is pan-industry global split, what you will notice here is a very interesting trend. The total market is about 792 billion USD. This is 2025. And 40% of it comes from compute, 30% of it comes from storage. And if you do a deeper dive, you will notice that the trends for storage increase for defense and security. So what is that telling us? That as far as the defense and security is concerned, storage, semiconductor storage technology or memory technology takes very prime importance. And while at the face of it, we fight wars with equipment, with sensors. So there is an overwhelming importance given to sensors when it comes to semiconductor platforms, sensing platforms. But the real priority, where I think, at least in my opinion, should be is on the storage systems. And if you go further from that, you will see that what are the estimates of data that is being generated globally. So 2025, the amount of data, quantum of information generated in a single year is around 165 zettabytes. So that is 10 raised to 21. The unit is 10 raised to 21. So just imagine how large that value is. And the one of the biggest contributor to this source is again DNI, or defense and security, or defense and intelligence, which is contributing to this, all this humongous data generation, right? All the sensors, all the streams, or whether it is the drones or equipment, whatever is collecting data, space-based, aerospace, underwater, ultimately all that data has to rest somewhere. Unless it doesn't rest, unless it is not stored somewhere, the processing or making insights from it doesn't even start. So that makes the storage vertical extremely critical. Now, what does the future of the storage vertical entail? Traditional semiconductor storage has been driven by two primary concepts: the good old magnetic tape drives, the HDDs, and the incumbent flash or the charge-based storage, which is the SSDs. But there is a lot which lies ahead. There is a long road ahead with many different other technical interventions. There are things like resistive memory, magnetoresistive memory, conductive bridge RAM, and so on. And the difference is that the material changes, the underlying physics changes, and very interestingly, from leaving aside the industrial economics or the industrial performance, each of these materials, they bring in very unique properties which can help for defense use cases. Some of these materials, some of these storage technologies are intrinsically radiation hard. Some of these devices, some of technologies are intrinsically stable at high temperatures. Some of them are intrinsically more, secure against EM interference. So this tells us that there is a lot of scope for the defense users, for many low-hanging fruits, to do small interventions, even till we reach the full envisioned scope of domestic semiconductor manufacturing ecosystem. Even much before that, if we choose some very specific niche materials or entities, there is the scope of getting defense ROI on the defense use case of semiconductors, especially in the storage domain. Next thing, I'll come across to the compute. Many speakers before also have highlighted compute. Again, this is a civilian domain stat which tells you that if you normalize the CO2 dissipation for different actions, one flight, 3 to 4 hour or 5 hour flight from the East Coast to West Coast in the US, if its normalized CO2 emission is 2 or 1x, training a state-of-the-art AI model would go up to more than 600x. So all the AI that we are talking about, that we wish to adopt, that we wish to drive PAN services, both its training as well as its adoption, if it has to really be sustainable, we have to look at low power compute. So low power, and even from services point of view, all the new warfare equipment, whether it is your drones, PGMs, UGVs, everything is backed by battery. And if you want to make it, if you want to have a higher endurance, then the dissipation of processing needs to cut down. So that leads us to specialized architectures, going away from CPUs and GPUs to ASICs, application specific ICs or FPGAs. And all of this is already becoming mainstream, even on the civilian sector. So here also, I would urge the defense users to, rather than waiting for the entire ecosystem to be established, we feel there are many small low-hanging fruits where for very specific use cases, the ROI can already be seen from the state where the current domestic capability is. And you can think of these platforms as an analogy to moving from a general purpose civilian aircraft. You can think of a CPU as a civil transport aircraft, which can ferry both soldiers and men, a very general purpose thing, to the ASIC as a very application-specific launch vehicle, which is extremely performance optimized for its goal, but it can just do one task. And the things like, your GPUs are nothing but your heavy lift aircrafts, and the FPGAs are your reconfigurable or your amphibious assets. So the interesting thing here is General Mann also mentioned that we are moving from a platform-centric to information-centric warfare, and look at who are the champions of information-centric landscape. The entities that you see on this slide are essentially the flag bearers of the information-centric ecosystem. And why I'm showing these entities on this slide is a very interesting point, that all of them have dedicated investments in hardware, low power hardware compute. So this should tell us that where to look forward, because they are operating with data at the scale at which we aspire to be maybe in 5 or 10 years from now, or where we will inadvertently end up with. So there are things like neuromorphic computing, in-memory computing, topics on which we also work in our lab. And the core essence over there is to reduce the power. Now, the last aspect is obviously the security aspect. So we have worked closely with MIT's NSM on developing some hardware security interventions, whether it is hardware-rooted crypto primitives, or whether it is doing assessment of vulnerabilities in hardware. So this can be linked to things like side channel attacks or fault injection attacks, where we do deep analysis of what can be some hardware level vulnerabilities. So that is the more direct relation with the concerns of the defense users. And you may have heard of Trojans, or the pager incidents or supply chain compromises. So all of that is being addressed at some level. And last point that I want to make is what defense should also keep in mind, that whatever point we are entering this race, the future for semiconductors is 3D. And all these, whether it is storage, sensor, compute, all the chips are getting integrated in a 3D layer. Even your photonics or your quantum devices. So we have to, from a long-term perspective, we have to keep some problem statements or some thoughts even for the 3D space, because also just think from a vulnerability point of view, a 2D vulnerability versus finding a vulnerability in 3 dimensions is again a more humongous task. So now I'll just end with one couple of points or recommendations that I want to make. Is, and this is specifically for the defense thought process, if you look at the entire semiconductor value chain, I feel there is an overemphasis from the defense side to think of it as a final platform or a final product or a final thing which does an operational requirement. But at all these boxes, whether it is the IP or the design layer, whether it is the packaging layer, the fab or the chip layer, EDA, materials, testing, and post-silicon, at each of these layers, the defense users can benefit from. And when they are investing, or when they are trying to come up with roadmaps for absorption of semiconductor or semiconductor related effort, my request would be to earmark it in a complementary way for each of these buckets. So while fab, chip, and testing and post-silicon would require you to have a real device in an operational field, a real system or a real circuit, but let me tell you, the investment that defense does on EDA or IP or design, specifically the EDA layer, which means the tools which are used to do semiconductor design, that may not directly give you a product in hand, but that will give you extreme awareness of the capability of your adversaries. The chips or the ICs or the circuits that your adversary has, or what is its platform's capability, that you will reach through the EDA layers. So yeah, with that, I'll end. I'll be happy if there are any questions. Thanks.
First of all, I would like to thank everyone, all our speakers, booth exhibitors, and all the participants for making this event happen. So I'll be speaking on aggregating the semiconductor technologies from the friendly countries, where I'll be covering 4 countries mostly, Japan, South Korea, Taiwan, and the US. But I would be a little bit more specific with Japan because I have been researching on it for a couple of years, and while interacting with some of the most significant government officials and the representatives of the Japanese companies, I would like to highlight on some of the critical aspects. So when we talk about Japan, Japan's dominance in this sector remains since 1980s, where its global contribution was 50% in terms of DRAM. But currently, if we see, it has declined to 10%. Nonetheless, in the morning, we have had Abe-san, who spoke immensely about how the Japanese government is taking initiative on strengthening this industry. So here I would like to highlight certain areas specifically where Japan has its strength. First, I would like to speak on photoresist. Photoresist is extremely important when we talk about the small feature of a chip. Also, when we talk about the compound semiconductors, which is extremely significant for the military application. So Japan's contribution in this aspect is 80 to 90%, and the Japanese companies Shin-Etsu and TOK are today leading. Not just this, Japan also has there are other 70 advanced materials where Japan's contribution is 60% to the world market. So overall 56% to the semiconductor materials, 32% to the production equipment, and so Tokyo Electron is one of the third largest in the world today when we talk about the semiconductor equipment. Not just this, Japan also is leading today when we talk about the back-end processes and ATMPs. One significant aspect about Japan which I want to focus on is the rare earth-based semiconductor materials. In a significant interaction with some of the Japanese companies, especially Toho, Koki, and Fujimi, they mentioned their critical role which they are playing in terms of this CMP slurries and CMP pads, which are significantly important in semiconductors, manufacturing semiconductors. In fact, China is reliant on these companies, so they are way ahead and they are leading in these areas. The important part here is that these companies are also in producing the CMPs, pads, and slurries. They need the cerium, the rare earth. So here we see where we can connect India is that India has the world's third largest reserves, but at the same time, we really need to scale up when it comes to refining, mining, processing, and we do not have those technologies. And we also have huge reserves of cerium in India. But because of this lack of technologies, we really need to scale up. And here we see that Japan has this kind of cutting edge technologies when we talk about separation, refining, processing, etc. So this is one area which I would want to highlight where India, Japan can collaborate, and we can reduce our reliance on China, especially by creating a joint venture where we can produce critical chip making materials within India. Some of the Japanese companies are already here working with us, Rapidus, Tokyo Electron, Denso, etc. Another important part which our Indian government representatives in Japan and state representatives, including the Chief Minister of Assam during his visit to Japan, ensured that he meets the prefecture representatives. Because when we talk about this industry, it is not always about Tokyo. Japan's prefecture-driven semiconductor powerhouse is immense. Here I have shown in the slide, there are various prefectures including Kumamoto, Aichi, Nagano, Shizuoka, Kanagawa. So Kumamoto, we see that already TSMC has started its facilities including Sony. And this is one area where we could focus our industries, our SMEs could collaborate with their prefectures. One of the interesting prefecture is the Mie prefecture, where I have already spoken about Toho Koki. They are into CMP slurries and CMP pads. They are very much connected with the Mie University. In fact, this prefecture has a kind of a industry academia integration deeply happening. Here we see the deep SME ecosystem actually happening. So something like this we can actually have in India also, where the prefecture, where academia is also involved, where industry is also involved, and MIE University is offering doing a good amount of research in terms of the CMP slurries and CMP pads. Collaboration at university level, again in Japan, the US investment is seen, especially in Hiroshima University. Huge investment is happening there. Although in India and the Indian IIT Hyderabad and Renaissance has some level of collaboration, but it needs to scale up. COTS technology, which was already spoken by one of our previous speakers, this is one area where India, Japan can collaborate. So slightly, I would touch on South Korea also. We know South Korea's dominance in memory. So South Korea's highlight could be on high bandwidth memory, which it is leading today, especially companies like SK Hynix and Samsung. South Korea also have integrated hubs like the Yongin model. And not just the Korean firms, but Lam Research, ASML, and Tokyo Electrons are also investing there. And equipment and materials wise also, they are quite doing good. CHIPS Act, I don't have that kind of time. We can see what the Korean government policies are also initiative. Huge amount of incentives have been offered to push up their farms. And they are also trying to create a belt where they want to connect these models like Yongin, Hwaseong, Icheon, etc. A policy-driven synergy can happen between India and Japan, India's ISM and K-CHIPS Act, where we focus on joint R&D and industry engagement. Way forward is like we could co-develop HBM mostly to cater to the needs of the defense military application. India, since we are working on ATMP facilities, we could also be a backup for the Korean farms. And we could replicate the Yongin model of Korea. Taiwan, also we know Taiwan is known for its advanced nodes. Now they are going towards 2nm also producing 2nm nodes. Their manufacturing TSMC dominates at least 64.9% of the share of the global market. TSMC and Tata Electronics are working in collaboration along with HCL and Foxconn. And so there, they also have something like IIT, which we have ITRI. They are working in close collaboration with TSMC and UMC. These are certain recommendations which I have made where India's Taiwan Semiconductor Desk can happen under METI. PLI, DLI schemes could be leveraged so that we can attract more Taiwanese firms. And CoOS is one of the most important areas, which is an advanced level of packaging, which Taiwan is initiating. And this is one area we can collaborate mostly for military application. And now it is a time that there could be some policy shift from commercial to defense-centric strategies. Shortly, I would just speak on US. US, we know it, the dominance is in design. Out of the 10, 6 top companies are American. Then its leadership in fabless leadership is 62% of the global fabless revenues. When it comes to IDM, it is 51%. These are some of the companies, American, NVIDIA, AMD, Qualcomm, and I have just highlighted their strength. Micron Technology has already invested in Gujarat, where our Prime Minister has recently inaugurated it. This shows that India's entry into the global semiconductor value chain has happened. Very quickly, these are the 3 recommendations I put where we can co-develop maybe with NVIDIA, and we should ensure that partial IP ownership remains with us rather than pure outsourcing. And at the end, I would just say that while collaborating with Micron Technology, let's not just limit ourselves with ATMPs, but move beyond that, where they have strength in HBM, mostly for defense-related applications. Thank you.
Good afternoon. Thank you, CENJOWS, for having me here, and soldiers and officers, a privilege to come and speak in front of you. So I'm part of the Semiconductor Future Accelerator Lab Foundation. I'm not going to talk about technology before lunch. I'm going to talk about what can we do to actually energize this defense semiconductor ecosystem, and that will be the primary focus of my talk. This will be the structure, so I won't waste too much time with catching up. So in simple terms, this is the semiconductor value chain. And what we are going to talk about is design. The focus of my sharing will be primarily around design, why it is important and how we can leverage our strength in design to actually energize this defense semiconductor ecosystem. That would be the focus. When we talk about fabless, what do we mean by fabless? Essentially, it means focusing on design and outsourcing the manufacturing. This has been a model which has been quite successful over the last couple of years. In fact, from a business standpoint, if you look at the largest companies, it is not TSMC, it is NVIDIA. It is a fabless company. So the business of semiconductors is in the design space. We heard from our previous speakers in the morning, Major General Mann was talking about how we should own the product and not just the platform level. At the end of the day, what makes sense is the fabless space. And that is why it is really important. And subsequently, in my following slides, you will see why we need to focus on this space. Look at some of the keywords. Don't they all relate to what you need in defense? Whether you talk about optimal speed, all of these have been proven to work in the fabless model. We've always heard we need to have manufacturing capability. Of course, we need that from a strategic standpoint. But where does all the value addition happen? Majority of the value addition happens in design. So if you look at defense system, we had Major General Mann talk about, and all the soldiers, of course, they have to be operationally compliant, they have to be rugged, etc., etc. I think all of us know that. But what is the challenge that happens? When you look at, I think Dr. Ulupi just referred to comparing Japan, comparing Korea. We're talking about building strength outwards. What happens about building strengths inwards? Why not use our own capabilities to strengthen and energize our defense ecosystem? What are some of the challenges? Typically, because defense has specific requirements such as ruggedness and resilience and all of those things that were talked about this morning, they take longer cycle times to develop. And there are low volumes in terms of the quantities, which make it challenging for business. Now, let me kind of foray into the business side. Which are the world's most successful defense forces as far as semiconductors are concerned? US, you can talk about China, Israel. So what's different from the way they are operating and the way we are operating? First of all, they are learning to harvest from the private sector technologies that they can apply in defense, not the other way around. We are in India, a government-led, DRDO-led design system. Whereas if you look at globally, if you look at the US and China today, they are led to a large extent by what is happening on the commercial side. So if something does not make business sense, it is unlikely that it will survive in terms of the commercial aspect of business. So what happens there? Speed is important. Accuracy, all of the good things that you're looking for in defense is actually there on the commercial side. Are we saying 100% of the defense requirements will be met by the commercial world? No. But we talked about reliability, etc. But we are having asymmetric warfare. Actually, threats do not come at the speed of procurement. Threats are going to come at a very fast pace. And you can't rely on traditional procurement processes to actually make this happen or spend years trying to develop technologies. I want to let you know that the commercial world understands the requirement of the defense sector. It is not that we don't understand. I come from the commercial world. We do understand, but at the same time, the commercial world has a lot of technologies to offer defense. So it cannot always be initiated or controlled by DRDO, for example. There are times when the commercial world also creates multiple innovations which can be applied in the defense world. Now, the other new googly which has come up is AI. What used to take years to design can be now designed in months and in some cases in days. Now, bad actors are not going to wait for process. The focus, there has to be a fine balance between process and outcomes. It cannot be a never-ending process which takes years to come out with a product. AI is revolutionizing how we are designing itself. Like I said, it can take 2 to 3 days sometimes, and I think this afternoon there'll be someone who's going to speak. it's a professor who has been designing chips forever, then surprised to see that, some could be turned around in terms of design in a couple of weeks. So what I'm trying to say is speed is important. Conflicts will evolve faster than procurement cycles, right? And it is going to be true that whoever can design faster, it's not just about, having the best chip. It's about how fast you can get it from design to product. That is going to become critical. And the commercial world knows this very well. They have been doing it in and out. Major General Mann put the mobile phone on the right, for those of you who are here in the morning. But the reality is threats are moving at that speed. You can't wait for years for a chip to come out. So you can't wait for decades. And advantage will go to the side who can design, validate, and deploy silicon faster. Let me talk about how the whole ecosystem is evolving and where India is. The way we look at it, it is in an emerging or nascent phase as far as, let us say, semiconductor design is concerned. We have a lot of designers, but overall as an industry, when we look at it, even MeitY, I think, will agree. And I won't go into the details. We are the organization which we believe have moved the design needle to a certain extent, but it is a long way to go where self-sustaining is. So who is at self-sustaining? Countries like America, China, Israel. Israel is probably at mature. If you look at the number this morning, I think Sunita Verma madam said 24 companies fabless we have. Look at the other end when we talk of thousands. Where are the thousands? We are at 24. We need to get to thousands. So it's a long way. So we need to do something fundamentally different. And I think just look at some of our strengths. Look at this is from basically BCG. Talks about, I think all of us have heard this story, 20+% of the global chip designers are in India. A lot of them are in my city, so I know that they are there. Very talented people. So what is the problem? I mean, why are we not able to harness this capability? 20+%. I think if you look at it, other than maybe mainland China and the US, I don't think anybody has this human capital. That is part A. Part B, we've all heard about this AI mission. So we have the 20% of the chip designers and many of the global AI chip guys, just general AI guys. We have a huge amount of talent. I think it is time for us to take advantage of our advantage. We need to recognize that. So what can we do different, which is about energizing defense semiconductor design? Basically, this morning, I think Major General Mann mentioned about working closely with MeitY. I think it's an absolutely essential item. In fact, we suggest that, or my recommendation would be to have defense semiconductor design almost as a national mission, something that requires a lot of focus. And also have a roadmap to say, okay, today we have so many indigenous chips in our defense system. We'll take a goal next 5, 10, whatever number of years to take it from. Maybe today it's expected to be about 20 to 30%. Maybe take it to 50 to 60% over 5 years. So it has to be specific outcome based. Can't be general feel good talks, which actually don't result in terms of outcomes, because outcomes are really important, both operationally as well as in terms of results. Other recommendation is to scale private sector participation. Like I said, if you look at China, if you look at the American model, a lot of indigenous design that happens there is coming in from the private industry. And here our model has been predominantly designs are controlled by DRDO. Maybe it's a good thing, but it will not result in speed of innovation. The second part is participation. Today we have about 5 startups which have come from our organization, which is Semiconductor Fabless Accelerator Lab. We have Chip Spirit. Some of the DLI selected companies have come from our organization. So we know what we are talking about. We have brought up those organizations and they are today supporting defense. We are practitioners. We make things happen. So I'm not trying to boast, but it is the difference from what you see in academia. We're a commercial incubator which makes products come out. And I think that is the focus that is necessary, and it's working in other places, right? Something to look at. We've also got, in terms of, somebody was just mentioning there was a whole list this morning from MeitY, which talked about so many different items that we are working on. Where is the strategy? What are we actually working on for defense electronics? So something to seriously think about whether we have a structured outcome-based approach to actually get results for defense. So who we are, let me come to this. We are an industry-led, government-supported organization for semiconductor technology innovation. We do those three things: advanced IP research, accelerating growth, and catalyzing semiconductor workforce. We've done that for almost now 8 years. We have touched more than 93 plus companies. We have 43 companies in our pipeline. Many of the companies who have generated revenues and investments have come from this particular organization. And the focus, of course, these are all some of the companies. Many of these you saw today, and some of them will speak this afternoon too. Morphing machines, adaptable processor, Chip Spirit was here today. They are exhibiting. They are doing secure communications, Lightspeed AI photonics. We've got several. Y Electric is going to speak this afternoon on 6G. We've got LFC who is here. They'll be talking about EMI suppression. So we have the capabilities. Caligo has developed the world's first POSIT-based chip, which can be used for missile guidance. So we have these capabilities. I think the connection between the defense semiconductor design segment and the industry needs to be stronger. This is a sample of how we go about doing things. The entire ecosystem is built to enable the commercial enterprise. So basically, what can we do together? We are offering ourselves up. If there is a program, we are happy to participate on a focused defense semiconductor design outcome-based program where we can provide our inputs and our experience from the industry to help catalyze and energize this ecosystem. Thank you. And if anyone needs to speak to me, I'll be happy to talk to them. Thank you.
Good afternoon. I'm Abhinav. I represent an organization called Keynote, and I'll be speaking about a certain different topic. I'll be talking about materials, and I'll be talking about recycling. We have heard some extremely exciting stuff about the various technologies that are getting developed, but we need to acknowledge the fact that the materials which are required to make these technologies real are extremely important, and they're very, very I would say concentrated with certain countries which might not be working in our favor. And we have seen the geopolitics, in various areas, and this is something that we need to be very cognizant of, and we need to sort of figure out how can we structure our efforts so that we don't get stuck because of the lack of materials which are there. So we have already, this is something that I'm sure each one of you is aware of. There is a significant dominance by China and a few other countries in the area of technology as well as in the area of materials. And, we talk about rare earth magnets, we talk about semiconductor technologies, we talk about renewables. Everything is largely getting processed in China, and which is making the whole world a little vulnerable. And people are now raising up to the occasions and trying to figure out how do they make resilient supply chains. And that is broadly what I'm going to talk about. So India, and I will be, taking the recycling route, which we believe, basis the various reports which have been published and the studies which have been undertaken, that close to 20 to 30% minimally of India's requirements of materials can be very easily fulfilled using recycling, and therefore it should be looked at from a very strategic lens. And India is at this point in time generating close to 6 million tons of electronic waste. This was reported by Niti Aayog in a very recent report. And 99% of this waste, unfortunately, is getting recycled in the informal sector, which is not using scientific methods, and they're not able to extract a lot of materials. I'm sure each one of you would be aware here in this particular room that there are close to 60 elements of the periodic table, which are there in the electrical, electronics, rare earth, renewables kind of waste, which is getting generated, but they are not getting re-extracted so that they can be put back into manufacturing, which is something extremely, extremely important. In fact, the Indian defense sector itself accounts for 100,000 to 120,000 tons of electronic waste. And this is also not going back into scientific recycling. In fact, it is going to the informal sector, and the informal sector, the way it is structured, they take out whatever they can, and the rest, which is actually containing the critical materials, the rare earths, they are going back into countries like Korea, China, and where they're getting refined and they're brought back into the country, which is leading to a lot of issues with our own manufacturing sector. And as we focus more and more towards manufacturing, both in defense and civil applications, we will see that these materials, which are now becoming more and more important as we try to optimize the products much more, we will see that this will become a major issue from, how do we actually scale these things up. So critical bearing, sort of waste should not be pictured as waste alone, should not be thought from a compliance standpoint or an environmental standpoint alone. It should be looked at a strategic resource, as a urban mine from which you can get this material, and this material will be, very, very concentrated, so easier to get it out. Although there are complexities there, but technologies have been developed by various organizations which can now make it very efficient to extract these materials out. Now, if you look at from a defense manufacturing standpoint, so if you look at radar systems, guidance actuators, whether you want to look at UAVs, comms, backup power, you name any product, the kind of materials which are required inside of each of these products are very, very specialized. And unfortunately, we don't have the basic source in India, or we don't even have the mines. And processing definitely is something, the midstream processing is something that is still being sort of developed. And there are lots of schemes which have been put up by the government of India. I'm sure each one of you would have heard of the National Critical Minerals Mission, the Rare Earth Permanent Magnet Scheme, which is being launched. In fact, I apologize that I was a little late. There was a stakeholder consultation at the Ministry of Heavy Industries where we were having a consultation on the Rare Earth Permanent Magnet Scheme, and I got a little late coming here. But what the point which I'm trying to make is there's a global supply chain which is providing these materials to our manufacturing sector, but this global supply chain is dominated by players which may not always be in favor of whatever we are doing, and they have shown their muscle to the largest forces or largest countries in the world and the most powerful countries in the world. We definitely will be not always preferred if we are not sort of trying to make ourselves self-reliant. There is a high import dependence on most of these materials which I've spoken about. Defense platforms are materially intensive. The kind of performance that finally a defense application requires comes from the usage of certain specialized, although they in very, very small quantities, but these come through the use of these specialized materials. And the supply chains, like I've already said, are fragile and geopolitically weaponized. So what has happened till now, as per my understanding, so there have been a couple of workshops which have been organized a couple of years back, which were looking more from a sustainability standpoint rather than from a more strategic standpoint. And in this consultative workshop, there were members of various defense forces, and we had a opportunity to explain our viewpoint. At that point, the critical materials were not that important, given the fact that geopolitics was still not played out as it has now. And we continued to sort of deliberate and discuss with the defense forces of the opportunity that exists, that we could do if we can get recycling in a right shape. Because right now what is happening is most of the material which the defense has and which may have very, very high quality, they are also auctioned off in the MSTC portal or through Government of India processes. And unfortunately, the norms which are there are very, very loose. And that allows these materials, which are otherwise containing extremely important material, to go to the informal sector, which uses extremely, I would say, primitive methods to actually extract these materials. They're able to extract only iron, copper, aluminum, and maybe a little of gold. And they use very harmful methods to actually extract that. And the rest of the material, if they have attempted to actually extract gold, is still in the form of a acid bath in which all the close to 50 odd elements will be there, and they throw it back into the rivers and they throw it back into the ground. So groundwater contamination, there are social issues, there is a lot of pollution which happens because of this. That's one thing. And those which are not even attempting, they will sort of export it back to the countries like Korea and China. So we actually visited a COD, which is COD Agra, and we spent a whole day trying to understand the situation. What we understood was there is a lot of time which gets wasted, first of all. So the moment there is something obsolete, right, to the time when it is given to a recycler, there's a lot of time which gets, first of all, wasted. And during this time, the value of the material is actually lowering because of, sort of contamination, because of rusting and so on and so forth. So that's one problem. The second problem is that there are coteries of these, sort of recyclers, which basically come in and they try to lower the value. So the army is not even getting the right value for the material, because each time they don't sort of bid for the material, the next time you have to open the bid, you have to bid at a lower level. So what we were informed by the person who was heading the COD Agra was that at the end of the day, they are able to extract only 30% of the estimated value that they had estimated initially, because there is a whole cartelization of the recycling industry. So, and then the material which is getting recycled, like, what we understood, very high quality, very high grade, say, material, which could have been used into manufacturing of defense applications, which finally goes and makes vessels in Moradabad and other places, rather than putting it back into the use which it should be. So the highest value use case for which the material can be used is not getting, the material is not getting repackaged for that. And I've already spoken about the collection problem. The collection happens by the informal sector, and once it goes into the informal sector, to get it back into scientific recycling is near about impossible. And so therefore there is an issue which comes around national security. There is an economic issue because taxes are not getting paid. There is a strategic loss of critical material. There is an environmental and social impact, and there is obviously industry policy which is weakening the recycling ecosystem which is required. Atero as a company has been in existence since 2008. We have started as an e-waste recycler, but we now do lithium-ion battery recycling. We do rare earth permanent magnet recycling, solar panel recycling, and we have now technology where we can do 22 plus metals extraction from the around 60 elements from the various waste resources which we are, and we want to hone that further. I will not talk about too much about Atero's, sort of USPs, and we are the largest in the country. We do 300,000 tons of electronic waste recycling every year. This is close to, I would say, 35% of India's formal recycling capability, and we are trying to double that this year. And just wanted to show the kind of products that we have and the kind of purity that we are able to ascertain. So there are four, sort of ways in which you can evaluate a recycler. How many elements of the periodic table are you able to extract? We are able to extract 22. Nowhere in the world people are able to extract more than 12. So that's one. The second is, what is the extraction efficiency? In the sense, if there is 100 grams of material, are you able to extract 100 grams, or are you able to extract only 50? We are able to extract always above 98%. And then finally, what is the purity at which you are able to extract? We are able to extract more than 99.5% purity, and to certain elements, we can go up to 99.98% purity as well. In certain cases of the military, probably that is lower, but we would like to work with you and see if we can extract it at higher purities, which could be used directly in certain applications where higher purity is required. And finally, the environmental impact. We have made studies and we figured out, and there are third-party studies as well by the United Nations Framework for Climate Change and Control, that the work that we have put in and the kind of energy that we utilize is less than 99%, or rather it's 99% less than what is required in a urban mine in certain cases. So therefore, there is multiple benefits that recycling can bring in, and the material which is once coming into the country can be redeployed into the highest value use cases if we are able to focus on that. So we have a suggestion that we could do a joint venture with certain, sort of PSUs. I would very strongly suggest that you get out of the MSTC process and at least put very stringent measures with regards to what is it that a recycler should be able to, or the capability that the recycler should have, so that the materials can be re-extracted and put back into the manufacturing of high quality applications rather than putting it in the low quality applications. One more request that I have is, and that is something that we have been discussing, is that a lot of households which are there as a part of your, sort of establishments would have also a lot of electronic waste which is getting recycled. At least the defense should be cognizant of the fact that there is a huge social as well as an environmental issue here and a materials issue over here. And if you can, you should look at responsible recyclers and partner with them and ensure that the material is going to them. We have an initiative where we collect directly from the households. We would be willing to partner with you, and so that we can take it and ensure that all the materials which are there in electronic waste can be put back into manufacturing. That's one. And, but otherwise, of course, there is a huge outcome and the benefits which can come to the armed forces. You would have financial impact where you could have 75% of the value recovery which is happening. There are no delays rather than waiting in a COD and putting there. If we can have a, direct going to a recycler, the time which gets saved, the whole cycle can actually improve. There is greater material recovery. there is lower environmental impact, greater operational efficiency will come out. There is a huge strategic impact, because if your import dependence lowers, then that is something that we can really use to our advantage. And finally, of course, resource optimization is there. So double the processing, less space will be required. There is greater reliance on domestic sources itself. The supply chain becomes secure. There is employment which is getting generated, and unnecessary employment which is there because you just need to oversee that particular COD is not going to be there. That is something that could be there. And finally, we would love to partner, and we would love to see if we can do something more collaboratively and benefit the nation. With that, I would like to close and would be very happy to answer any questions. Thanks.
Thank you to all our speakers for the engaging and insightful presentations. May I request the speakers to join for a group photograph? May I now request our speakers to kindly step down from the stage and join us at the center that is in front of the stage to receive their mementos. May I now request Mr. Abe Noriaki to present a token of appreciation to our speakers. Thank you, sir. I request everyone to move for lunch break. I request everyone to be back by 2:10 max so we can begin the next session on time. The location for lunch is main hall. Ladies and gentlemen, you're requested to take your seats and put your devices on silent mode. Ladies and gentlemen, we'll now move on to session 2 on building of semiconductor ecosystem through Indian industries and R&D institutions. It is my privilege to introduce our chair for this session, Dr. Parimal Kumar, outstanding scientist and scientific advisor to the Chief of Integrated Defense Staff to Chairman Chief of Staff Committee. The co-chair for this session is Dr. Vipin C. Shukla, who is currently serving as Scientist G and the head of various funding schemes and United Nations APCTT matters in the Department of Scientific and Industrial Research, Ministry of Science and Technology, Government of India. I request both the chair and co-chair to come on the stage. This session will be conducted in two parts. For the first part of this session, we honor to have with us a distinguished panel of experts. May I now request our esteemed panelists to join us on the stage. Shri Utpal Shah, Vice President Tata Electronics. He's a seasoned semiconductor industry leader with over 25 years of experience across technology development, high volume manufacturing, product design, and foundry services. Dr. G. Sai Sarvanan, outstanding scientist, Scientist H, joined DRDO in the year 1991 in Solid States Physics Laboratory, Delhi. Initially worked in the fabrication and bonding of microwave and millimeter wave devices and circuits like GUN. Dr. S. Selvaraj, he's presently heading MEMS Design Department at Stark, Bangalore. He's also leading the team for development of drone acoustic detector for detecting unauthorized entry of drones. Dr. Kamaljeet Singh, he joined ISRO as RF designer and worked in various capacities at URSC, dealing with multiple spacecraft projects in various capacities. Presently, he is heading Semiconductor Laboratory as Director General. I request the panelists to please take their seats. Sensing the enthusiasm, I now hand over the conduct to the panel chair.
Thank you for a nice introduction. And we have a distinguished panel, and without wasting time, we will start the session. So I'll invite the first speaker, but before that, I have a request from all the distinguished panelists that please adhere to the time, and the time allocated is 15 minutes for each of the speakers. We do not have question answer session, but in case you are able to sum up well in time between 10 to 12 minutes, then we may have questions. Otherwise, we'll go without question and answer session, and we can have question answer session on sidelines. So our first speaker is Sri Utpal Shah, Senior Vice President, Tata Electronics. Sir, I request you to do the honors.
Good afternoon, ladies and gentlemen. At the outset, I would like to express my sincere gratitude to the Office of the Chief of Integrated Defense Staff for giving us this opportunity to address this distinguished gathering. It is a privilege for me to represent Tata Electronics in this forum for the second time and share our perspective while learning about the defense semiconductor requirements and roadmaps. In this session of building of semiconductor ecosystem through Indian industries and R&D institutions, I will share the industry perspectives on the semiconductor requirements especially for intermeshing of semiconductor requirements in the defense systems, the pathway to indigenization, and how Tata Electronics can contribute to this national mission of our Prime Minister, Honorable Prime Minister Narendra Modi's vision of Vikshit Bharat. My name is Utpal Shah. I am part of Tata Electronics. I lead strategy and business development at Tata Electronics. I joined Tata Electronics about 2.5 years ago. Before that, I spent about 22 years at Intel Corporation in Santa Clara, California, in Silicon Valley. In that capacity, while at Intel, I also dealt with the US government and some of the defense programs that they had running with Intel Corporation at that time. Today, I'm going to talk about three things. Firstly, why semiconductors have become an integral part of the defense system. Secondly, what is needed as we look at the Indian landscape comparing to the global standards, what is required in terms of developing the semiconductor infrastructure for defense in India. And thirdly, I'll talk about what Tata Electronics is bringing to the table as far as semiconductors is concerned from the defense perspective. So beginning with this chart, I think our Prime Minister, Sri Narendra Modi, has already called out chips as the digital diamonds. Semiconductors were previously referred to as the new oil. And with the designation given by our Honorable Minister, now chips are called digital diamonds. And indeed, they are the digital diamonds. If you look at the substantial consumption that is happening in India and globally, but particularly in India, you can see, look at this chart where today in 2026, we are roughly sitting at about $64 billion of semiconductor consumption domestically. This is projected to go in less than 5 years to as much as 3x of that 64 billion to about 160 billion by the end of this decade. So this is a tremendous growth of semiconductor consumption happening across India. This is stemming from the fact that India is globally #1 when it comes to digital infrastructure. There are roughly 20 billion transactions, digital transactions happening on a monthly basis in this country. And when you look at the 900 million digital users that we have in India, it is unprecedented across any country in the planet. So when you look at this growth of 2021 to 2030, from 27 billion to 160 billion, it is growing at a CAGR of 22%. And therefore, a semiconductor has become a very important asset in the country from the economics standpoint, because it provides that needed, the necessary push to the GDP. But I'll also talk about how it is becoming very critical in terms of the defense and national security for the country. The good news is that the country, India as a country, is already supporting the mobilization of the semiconductor industry through very aggressive policies. And I have to thank the India Semiconductor Mission, which is the nodal agency residing in MITI, for coming up with very favorable policies on the semiconductor. We have 18.5 billion currently invested in the country through the policy. These are approved projects that make up the 18.5 billion. And it is going to create a tremendous momentum in India. It has already started a tremendous momentum in India for establishing semiconductor manufacturing, and this is just the beginning. So the key message here is that semiconductor is not just a critical asset for a country like India to have from the economic prosperity standpoint, but also from the national security standpoint. If you look at the defense requirements, there are many defense applications now across land, ocean, air, and cyber and space. But from a semiconductor design, chip design and manufacturing standpoint, we like to break this down into 4 major categories. The first one is navigation. When you have these defense platforms, they are essentially navigating terrains and different geographies. So you need very capable navigation chips. The second category is the sensing, because as you're navigating through terrains, you need to be able to sense what is in front of you, what intelligence can you gather from that. So sensing chips that are related to sensing are extremely critical. The third category is that now you're navigating and sensing, you need to be able to crunch that data. So the third category is compute. You need to be able to compute and generate meaningful outcome from that computation. And then the last category is what we call communications category, secure communications, where whatever you are crunching, computing, you need to send those signals back to the defense platforms like these unmanned aerial vehicles or missiles or satellites. And so communications, secure communications becomes the fourth category. So you look at navigation, sensing, compute, and communications. These are the four categories in which we need chip design and manufacturing capabilities indigenously in India. When you put it all together, you need now, with the advent of AI, you can put an artificial intelligence on the data you are gathering from navigation, sensing, compute, and communications to infer more intelligent outcomes that can tremendously advance the defense intelligence. So AI integration plays a very key role. And imagine that you have this data coming from different different branches of military, right? So you have data information coming from land, you have it coming from ocean, from air, from cyberspace, and from space. And you need to be able to make sure that this data is talking to each other, that it is completely interoperable, completely integrated, so that AI application can be done in a meaningful way. And if you do it this way, I think some of the leading modern defense systems are taking advantage of the AI application and integrating, having a very high interoperability and integration between what they see from land, sea, ocean, air, space, and cyber. So this is the stack that we are talking about in terms of chip electronics. And the last thing, if when you have this integrated stack, it needs to be, I mean, one of the first and foremost requirement for defense is that the solutions have to be reliable. They have to operate in a very harsh conditions. So today's chips, if you look at commercial chips, they are not manufactured or designed from that perspective. So first thing we need to do as a collective industry is make sure the chips that the semiconductor solutions are reliable from the defense standpoint. That means a particular set of requirements have to be pursued, and they have to tolerate certain conditions. Second thing is that they have to be traceable. So you need to have systems in place within the semiconductor solution so that you can trace at a minute level. And the last thing is the trust, making sure that these chips have multiple layers of trusted defense, so that breaking into that is nearly impossible. So in India, I think we have started the journey of semiconductor manufacturing. The first thing would be to make sure that all our semiconductor solutions are defense grade, which means we have to align on the defense related requirements in our semiconductor roadmap. Once we cross that threshold, we can then look at the intermeshing, interoperability, integration across different domains, and getting to the next level of defense roadmap. I'll switch to now talking about what is the from the semiconductor solution space, what do we have? So if you look at the top layer here, these are all the end applications for defense. These are just a short list. There are many, many more, but you can see there is, drones, satellites, communication systems, surveillance systems. If you go one layer below that to see what type of semiconductor technology are used, again, I go back to those four categories of compute, navigation, communications, and sensing. And you'll see chips along those lines like edge AI inference chips, power management chips, power amplifier chips, microwave monolithic chips, MEMS and CMOS sensors. And you go one level below that to see what technologies are needed to support these chips. The good news here is that majority of these chips are using 28 nanometer and above technologies. I think somebody else mentioned this earlier in the program, that these are mature technologies. So Tata Electronics in our portfolio, we do have 28 nanometer and above technologies. So it can definitely be leveraged from the defense standpoint. Whether our technologies are defense ready or not, that's another question, but we do have 28 and above technologies. Then there is compound semiconductors where we don't have that capability in Tata Electronics, but other companies have gotten approval from ISM to get into gallium nitride and silicon carbide chips. Then there is advanced packaging, which we have on our roadmap. We are currently producing traditional packaging, and we have a roadmap to go to advanced packaging. And then lastly, MEMS and image sensors and radiation hardening. This is where I think establishment like SEL can come very handy. We are collaborating with them as well, and I'll talk about that briefly. So learning from the time spent in US, US has always been on the forefront in terms of driving the semiconductor roadmap. These are some examples of how they have collaborated with universities and industries to deliver leading innovations. For example, the first VLSI came actually from defense, and then it was commercialized. Similarly, the GPS system was also invented in defense, and then it was commercialized. Power electronics is also the same way. If you compare the US system with what we are trying to do in India, I think the first thing is that today our defense roadmap leverages what is available in India from the semiconductor technology standpoint. We should flip that. Defense should drive the semiconductor roadmap. What are the requirements from the leading edge defense standpoint that we can incorporate in our semiconductor roadmap? And there should be a conscious effort to make sure that the semiconductor roadmap for the country is influenced by what is needed in terms of our defense roadmap. Procurement, there can be made in India mandate for some of the chips to be procured domestically. We should have provision for trusted access. In all the fabs that the country is creating, there should be some dedicated line for defense. This concept is quite prevalent in countries like US, where fabs have dedicated corridors for trusted manufacturing of defense-related solutions. And then lastly, strong collaboration with stakeholders, policymakers. I'll talk about that some more on this slide. So essentially, one of the thoughts that we've had at Tata Electronics, and this is just a suggestion, not anything other than just a suggestion, which is to have a nodal agency that is completely dedicated for defense-related semiconductor roadmap. ISM, India Semiconductor Mission, which is the nodal agency for the commercial use of semiconductors, has done a fantastic job over the last 4 or 5 years, where they've come up with policies, they've approved projects. Many of the projects are now in implementation phase. And there is a lot to learn from what we did there to see, can we replicate some of that in the defense space to create a dedicated nodal agency that will focus on defense. Then there can be a close collaboration between the defense institutions like DRDO, the policymakers like this nodal agency, the industries and startups like us, Tata Electronics, and academia to work on a defense-focused semiconductor roadmap. I'll now quickly cover what we have to offer from Tata Electronics standpoint. Tata Electronics was founded about 5.5 years ago. We have an end-to-end vision to provide electronics manufacturing solution from the design to manufacturing the chips, which is our foundry business, to packaging the chips, which is our OSAT business, and finally putting it all together in a system, which is our system manufacturing business, also called EMS. On the fab side, we have made a tremendous progress. You can see in the pictures, our fab construction is going on. It's coming up rapidly. It will be a state-of-the-art 12-inch fab with 50,000 wafer starts per month capacity. At the end of completion of construction, it will look like the image on the right-hand side. It will have 28 nanometer, 40 nanometer, 55, 90, all the way to 180 nanometer technologies. And it's a total $11 billion investment. The size of the clean room is 32,000 square meters, which is the size of about 5 football fields. And we are partnering with our technology partner from Taiwan called Power Chip Semiconductors. So we have a very good high confidence roadmap to constructing this fab and transferring technology from Power Chip and getting into manufacturing in this fab rather quickly. Similarly, we have an OSAT plant that is getting built in Assam. You can see the picture on the right-hand side. We have an operational smaller scale facility already in manufacturing in Vamegal, Bangalore, which is shown on the left-hand side. We are scaling that to a very high scale manufacturing plant in Assam. And this will go in production in a few months. We also have partners that we have struck partnership with to bring these solutions to fruition. We have, on the design side, we have partnership with Synopsys, Dassault, Smart SoC, and CDAT. We are also partnering with equipment and material companies. We have 2 partners on the government side. We have Bharat Electronics that we have signed an MOU with. We support their chip-related needs that go into defense and aerospace. And we have also partnered with the Semiconductor Lab. And academia, we have partnerships with IIT Gandhinagar and IISc for making sure that we have sustained supply of talent coming to our projects. Regarding the 2 government relationships that we have in the defense space, the first one is with Bharat Electronics. So here we are looking across our offerings of fab, OSAT, and EMS, and we are supporting requirements for Bharat Electronics from chips like MCUs, SoCs, power amplifiers, and supporting them both from fabrication and packaging standpoint. And for SEL modernization project, as was announced with the bid package 1, we have gotten that. We are going to be upgrading their facility in Mohali to bring the capacity from 700 to 1500 wafer starts per month. And we are very much looking forward to that partnership as well.
I request to expedite.
This is my last slide. So this is the offering that we have from Tata Electronics. We have technologies both from fab and packaging standpoint. And again, just to summarize, we are on a good track in terms of creating our fab and packaging capabilities. Defense can really drive that innovation in the semiconductor roadmap by establishing a dedicated nodal agency. And the collaboration will be critical between defense, industry players, startups, and academia. And again, from Tata Electronics standpoint, we look forward to partnering and strengthening India's defense roadmap. Thank you.
Thank you. We've completed almost in time and very informative and enlightening talk. Now I'll request my co-chair to summarize, please.
Thank you. Thank you, Mr. Upal Shah, for enriching the learned audience with your vast experience in Intel as well as the present experience in Tata Electronics. And you rightly, whatever takeaways you have given in the end are perfectly supported with the data and facts which you have presented in the beginning. And you started with that indigenous efforts should be focused. And as rightly said by our Honorable Prime Minister also that this is, chips are basically now you can treat as diamond. So you supported with the data 3x growth possible in 5 to 6 years time. And that's why this area is important for not only for economic growth of the country, but also for national security.
You beautifully covered all stages: navigation, sensing, compute, then communication. All these things are well supported with your talk. And at the last, I would say that you have given technology portfolio also, which is available with you as well as with the country. And we are very hopeful that after the culmination of this event, definitely there will be some fruitful engagements among the different stakeholders, and strong stakeholder engagement is the must at this present time for this area. So we wish you the best for your future endeavors. Thank you.
So now we have our next speaker, Dr. G. Sai Sarvanan, outstanding scientist and CEO GATEC. Sir, please.
Good afternoon. Thank Dr. Parimal for inviting us. I'll keep my talk very brief because already Director FSPL, Dr. Rawal has given all the background information about the compound semiconductor need. I'll keep it very, very brief, only about some of the applications that we have done. And I would like to inform the audience here that GATEC is our own homegrown indigenous government-owned, DRDO-owned foundry that is completely compound semiconductor foundry. And this is the first Indian foundry which is focusing only on compound semiconductors. There was nothing earlier, and this needs a mention here that we have been heavily supplying to space and defense applications. And we primarily focus on gallium arsenide because that has gone up to the production level. And gallium nitride, as Dr. Rawal said, is at an advanced stage of production, I mean the developmental stage. So we'll be soon moving into higher levels of production in gallium nitride. And we also carry out some work in indium phosphide. That's why it's a compound semiconductor fab. As far as the evolution of GATEC is concerned, it was a very unusual thought process from a person who did not belong to semiconductor field. It was Dr. V.S. Arunachalam somewhere in the late 80s, who was the then scientific advisor to Raksha Mantri. It was his brainchild that he wanted a foundry to be established somewhere in the country for developing MMICs. And nobody really knows why he had this vision of establishing something for MMICs, but this was his idea and this was his vision. And with this vision, he approached the defense minister and the Minister of State for Defense at that time, and they gave him the go-ahead. And with that, he had visited a couple of foundries in the world, the main one being the Plessey in the UK. And based on that kind of a blueprint, he had his vision, and he, with the help of Dr. Kalam, he created this facility next to RCA, that is Dr. Kalam's laboratory. Next to that, he created GATEC. So when he created that, the problem was getting technology, and the problem was somebody told in the morning that there was a heavy embargo because of the missile regime at the time. And whatever happens in the country, one of the first labs to be affected by the embargo was SSPL Delhi, because SSPL was never involved directly in any of those activities, but that was the first lab to get affected. We will not get raw materials, we will not get equipment, and forget about technology. So that was somewhere in the early 90s when me and Dr. Rawal joined SSPL. We had to do everything from scratch. The problem was getting even gallium arsenide samples. We were hardly getting a 1 inch and 2 inch diameter samples with which we had to develop technology. So doing R&D and publishing papers was a distant dream and distant goal. We could never focus on that, but somebody has to stand up to the challenge and fabricate devices to tell the country that we are developing this capability. So that was when this idea was accepted by Dr. Arunachalam, and then he told that we should be ready with our technology. And then GATEC, by the time we had handed it over to the then SCL to build the infrastructure, and it was our money, and SCL was asked to build this as a camouflage activity so that we don't come under the embargo, so that we can get the equipment and all the raw materials, and that's how SCL took the lead to build the foundry there. And our first technology implementation was the 0.7 micron MESFET technology. MESFET is the basic workhorse of gallium arsenide transistor, and that was our first and the most important device based on which the MMICs were developed. And these were so rugged devices that they have found applications straight away into the space program. And we are really thankful to SAC Ahmedabad, the team there, both the quality control team as well as the payload team. They, I would say that they discovered us. In fact, they had come down heavily and forced us to, sweat it out every day and night. They used to sit there and then guide us, propel us instead of we, sitting and doing it ourselves and then trying to achieve it. It was the team from SAC Ahmedabad. It was a very good synergy between GATEC and that team, QC team. Interestingly, it's the QC team which took the lead, and these were the three teams which sat together and then developed this technology and made it space worthy. So because of that, as early as 2001-2, we started the space qualification program, and we successfully completed in 2 years, 2 to 2.5 years. And 2005, GATEC was awarded the space qualification certificate by SAC Ahmedabad, which paved the way for many MMICs to be flown. And morning, I don't know, somebody was mentioning about the surveillance. So one of the earliest surveillance satellites, I think, TES and subsequently the Cartosat, and followed by many other satellites, all of them were having at least one GATEC made module. And all those chips were all completely developed in-house, fabricated, RF tested, reliability qualified, module level tested, screened, and then supplied to SAC Ahmedabad. And that is how we grew up to X-band, that is up to 10 gigahertz. And subsequently, when the user laboratories demanded further increase in the operational frequency, we had to move forward. So we collaborated with a couple of known agencies across the world, and we brought in our 40 gigahertz PHEMT process. PHEMT is the next workhorse of gallium arsenide material. So pseudomorphic HEMT, this material uses indium gallium arsenide as the channel material, and this indium gallium arsenide has the highest mobility of electrons. And as a result, the state-of-the-art 0.13 micron gate length PHEMT, or let us say 130 nanometer PHEMT device, has a cutoff frequency as high as 110 gigahertz. So using a PHEMT device of about 100 gigahertz cutoff frequency, we were able to easily move into moving into high power amplifiers, mainly the low noise amplifiers, wideband amplifiers, because wideband amplifiers are required for EW applications, high power amplifiers, all those became possible. And then the whole place was upgraded. And thus GATEC is has the state-of-the-art 0.13 micron or 0.1 micron gate length technology, which is at par with any of the foundries in the world today. So to give you a glimpse of the product, one of the earliest ones that we are given were practically about 20 to 30,000 MMICs that were given as early as 2005 to 2007. And as a result, the first RISAT-1 satellite was filled with our MMICs, all of them space qualified, reliability tested, and then ensured that they were all fail safe, and all of them are flown in RISAT-1. And going by the news that we see every day in the newspapers, you may be aware of all the surveillance activity happening in the border. And we are really proud to say that this satellite RISAT-1 was the one which enabled the border surveillance, and when people went to do the surgical strike, those kind of activities were enabled by our MMICs. The SAR, the full radar contained GATEC made MMICs. And notwithstanding that, the first Cartosat had got 128 MMIC modules. Then we have all the series of RISAT-1. This RISAT-1 is a C-band satellite. The full entire series carries our devices even till today. All the new orders are also based on our C-band devices. RISAT-2 series is based on the X-band configuration, so that contains PHEMT. So all these devices were made from our MESFET-based technology. And here it will be interesting to see that the MESFETs which were originally packaged in individual packages like this, all were made into smaller LTCC modules. So this is how this became a new trendsetter. And this X-band high power amplifier is part of every satellite that is flown by ISRO. The next one being the 40 gigahertz technology. Some typical examples I'm showing here. The RSR2 series, as I said, contains plenty of X-band MMICs, which are all again in-house fabricated, in-house designed, in-house fabricated, quality control checked and given to ISRO. And there are several examples: the C-band core chip, the C-band KU-band, C2 KU-band wideband core chip, and there are plenty of other examples for DRDO labs, like that, the transceivers for ARDE, bidirectional amplifier for DLRL. These are a few, and the KU-band core chip is for DLRL. These are all based on 0.13 micron gate technology, which is the state-of-the-art technology. And the recent development is the terahertz Schottky barrier diode, which is again an application driven by astronomical requirements from SAC Ahmedabad. And also there is a requirement coming from Samir for use in very high frequencies, somewhere in the W band and even beyond that. So this is even more one step ahead. The material also is grown inside GATEC. The fabrication is done, design is done. Even up to the qualification level, we have done everything in-house at GATEC, and this is having a cutoff frequency of about 4 to 4.5 terahertz, which means we can use this device either in MMIC form or in a beamlit form, well into 330 gigahertz applications can directly find an use there. So what are the capabilities GATEC can offer? It's a vertically integrated fab, where we have the in-house design. We have our own fab, which, as I said, is 0.1 micron capable, and we have all the in-house assembly practices. Either we can give the users in a bare die form, or we can put it in some commercially available cheaper economical packages like QFN packages. Then we can go for a reliability ensured metal ceramic packages, or in multi-chip models. This is again one more innovation that GATEC had embarked on about 10-15 years back. When this concept was very new, GATEC had already gone into multi-chip modules, and many of our modules which are flying, even in Chandrayaan or in many of those places, are all multi-chip modules. So these all can be given. So the challenges that we find today is that this is a very, very niche domain where there are no players around in the country. But the problem is that we need support. Otherwise, this is a very, very difficult job to carry forward. There are practically no commercial applications for this. These are entirely strategic application oriented. It has to be serving only the strategic sector, and this is the only space qualified foundry in the Asia till date. There is no other space qualified foundry, even though there are other foundries which are being used by the space industry, but they have not openly qualified them. But ours on paper is the only space qualified foundry, thanks to ISRO. So being the first and the only space qualified foundry and indigenous compound semiconductor foundry, it is important to sustain this, as we have a trained manpower of 3 decades, which you don't find across the country anywhere, only in compound semiconductor fabrication, design, packaging, reliability, and all the activities surrounding to production level. So being a limited series production fab, it is important that our country and all the armed forces should support us. Thank you.
Yeah, thank you, Dr. Saravanan, for your presentation. And as GATEC is the first and only indigenous compound semiconductor foundry facility in the country. And as you also mentioned that MMIC is still having its space in niche area, strategic area. We need to focus on commercial applications also, and that will be true justice for you as well as industry also. So we look forward for some more collaborative efforts, and hopefully this our other stakeholders will look into that. So we wish you all the best for that. Thank you.
Good afternoon. First of all, I thank the organizer for giving us an opportunity to share our experience in the field of semiconductors. Today, our CEO, Dr. Meduri Ravi, could not participate in this workshop, so I am presenting the details about our work. The topic of my presentation is on achievements and challenges in fabrication of indigenous semiconductor products. So first, I'm happy to inform that we received IET Corporate Award for performance in electronic components in the year 2023. STAR-C is basically a unit of CITAR, which is under DRDO, and it is an integrated device manufacturing foundry catering to DRDO, defense and other government customers, basically strategic requirements. So it has a land of about 23 acres in its campus, and we have built around 16,000 square feet clean room in our area. STAR-C is basically a pilot plant that can be used for prototyping, small or medium volume production, packaging. We are doing the packaging and mill qualifications also. So STAR-C has to meet the high mix, low volume production requirement of DRDO. Basically here, high mix, low volume means multiple products has to be realized, but small volumes has to be productionized. That is our mandate. And we have symbiotic relationship with SSPL. Basically, SSPL will give the designs and basic technologies. We will be doing the production activities for SSPL. Okay. Coming to the roots of STAR-C. STAR-C was originally a CMOS fab. It was the CMOS fab was originally established as VLSI unit in ITI Bangalore. It was started as a National Center of Excellence with 1 micron CMOS technology. The TOT was obtained from Atmel, France in the year around the 1990s. The main aim was to cater to the defense and the strategic requirements. So the middle box is telling about the various features of the ASIC technology that we were working earlier. Basically, it's a cell-based design. The die size is maximum 15 mm by 15 mm, and number of transistors there, IC was around 1 lakh transistors, and we were processing the silicon wafer in class 10 area. It was 1 micron CMOS technology. We were using 2 metals for interconnections and 1 polysilicon electrode as the gate electrode, and the maximum frequency was of 50 megahertz. The fab was basically a 6-inch wafer processing. Fab turnaround time was around 6 weeks after receiving the masks. Here the challenge is we always outsource the mask fabrication to other countries, so the lead time is also increasing. Also, because of the absence of local vendors for silicon wafers, the lead time was also very high. Another major challenge at the time was sanction.
So the technology was sanctioned at that time, mainly because of, I think, Pokhran explosion. So that is why DRDO funded, and the facility was established in ITI, which is basically a communication industry. In that sense, they took the technology from France. So these are some of the products that we have realized in VLSI Foundry. I will be giving details of important products. CAM is basically content addressable memory, which is used by BEL in electronic warfare applications. And CML is complex multiplier used by DLRL. Anusama is basically time tag chip. Basically, it was used for accessing satellite data at regular or specified intervals. Energizing is a digital frequency synthesizer. It is used by NSTL Visakhapatnam. Even now they are using our devices, which is delivered long back. And the RNG is basically random number generator. Basically, it is used for encryption and security, secure communications. And bolometer we have fabricated 32 by 32 initially. Now the size is bigger. Multi-chip analyzer was fabricated for BARC. It is basically used for spectroscopic data collections. And IMS module is ion mobility spectrometer module we developed. ANIO is basically analogic input-output devices that is again used by the BARC. And optical waveguide is used for measuring the acceleration. And depletion mode MOSFET transistors are supplied to NPOL for hydrophone applications. And error detection and correction chip and glue logic were used by security applications. So these are some of the DD MOSFET is dual dielectric MOSFET. It is also used by BARC for spectroscopic data collections. Silicon photomultiplier also was used by BARC. Numerically controlled oscillator. Time interval control is used in T90 tank as a range finder. Basically, the range was around 9,000 meters. And RISC processor Anupama, it was the first processor which is fabricated in India by Sitar, Starcy. And apart from bolometers, and we have developed Z-axis accelerometer and micro thruster for RCI. We have developed piezoresistive accelerometers for RCI and delay line switch for OLF Dehradun and bolometer for SSPL. ICP sensor is intracranial pressure sensor used for medical electronics. And we have developed technology for 3-stack accelerometer and hash generator. So coming to the strengths of Starcy, Starcy has more than 2 decades of experience in VLSI and MEMS devices. We have very well trained manpower in semiconductor manufacturing. Our engineers can do the process technology right from the unit process development, process integration, short loop experiments, and mature the process to reach a final technology for fabricating various MEMS devices. And we had first established the male qualified fab, VLSI fab. Then we established a MEMS production fab at Starcy. We have the capability to deliver customized package development using LTCC and GTM sealed methods. Our team is capable of handling the clean rooms. Variety of clean rooms are handled like class 10, class 100, and class 1000. We have the capacity to handle the hazardous chemicals, toxic gases, which is regularly used in semiconductor fabrication unit. And we have the capability to do front-end and back-end VLSI design. Using our assembly, packaging, testing facilities, we are able to make indigenous design for manufacturing facility. And this slide gives the supporting integrated circuit supply chain. Basically, we have a design team, VLSI design team. The design data will be given or outsourced to other fabs like XFAB, Tower, TSMC, and SEL. Once the chip is received, we have the in-house facility for packaging, or we can outsource sometimes. And we do the chip programming for realizing a particular product development. And we do the PCB integration with the chip and to realize the finalized product. Now, the 1 micron technology which was established during 1990s became obsolete, and we were mandated to diversify into MEMS fabrication, micro electro mechanical system fabrication. Why we went is MEMS fabrication is basically similar to VLSI fabrication, but one distinction is In MEMS, one technology, one product, like that relation is there. Whereas in VLSI, one technology may be used to realize multiple functionality. So this is one challenge in MEMS foundry. Okay, and STARC has supplied an average of 1,000 milk qualified pressure transducers annually for various missile programs, using its expertise in customization. STARC is a trusted supplier of pressure transducers to DRDO, BDL, BL, and STARC is also developing various other MEMS sensors like accelerometers, G-switch devices, gyroscopes, etc. This slide shows a number of pressure transducers which has been designed, fabricated, assembled, tested in-house in CISC. It is a totally indigenous product, and various pressure transducers have been supplied to DRDO. STARC has successfully delivered nearly 97 distinct types of pressure transducers. The difference is, what are the differences between these is basically it is featuring various pressure ranges from 1 bar to 400, 500 bar we are having, and it can have variable multiple connectors as per the customer requirement, and voltage requirement also. Some customers may need 0 to 5 volt, some people may need minus 2.5 to plus 2.5. This type of various output requirement also is realized in our fab. Our pressure transducer has been successfully delivered, and it is used in critical programs like Agni, Prime, Shakti, Pralay, Nirbhay, and Divyastara. Our pressure transducers are also qualified to meet the aerospace qualification requirement. So we have developed, designed, fabricated, packaged and tested two ranges, that is 280 bar and 330 bar PTs for LCA requirement. So ATQT tests have been completed on engineering units, and the test reports have been given to ADA and Semilac for their certification. The major achievement in this PT is 280 bar PT is successfully qualified, including 1 million life cycle test and 1 lakh impulse test. This is one of the stringent requirement of ADA pressure transducer to meet the aerospace quality requirement. So our PT is meeting that requirement. Similarly, the 330 bar is required to meet 2 million cycle life test and 2 lakh cycle impulse test. So this is also successfully completed. Now we are waiting for the Semilac certification from very soon. And the pressure transducer that previously we explained is capable of meeting a temperature range up to 150 degrees Celsius in the higher side. Whereas there are some requirements from BrahMos, some pressure transducers to meet up to 300 degrees Celsius temperature requirement. So our team completely indigenously developed a total complete product.
Request to expedite.
Using the potentiometric principle. So it is not a MEMS device, it is purely a mechanical device. So this device has been completely qualified as per the mill requirement of the BrahMos. So it is meeting up to 300 degrees Celsius. Apart from that, we have developed a technology for fabricating the inertial G switches. There are two types of G switches. One is latching type, another is non-latching type. This latching type is used in safety and arming applications, and the non-latching is used in bunker blast explosion applications. Another requirement for TBRL Chandigarh is high G accelerometer for explosive detonation. So this again is designed totally from the scratch. It was done in STARC, from scratch, from the basic research to design, fabrication, packaging, testing, and finally delivering to DBRL. So this image shows the fabricated sensor die, and the bottom picture shows the sensor die assembled on a TO package. The final package is shown in the right hand side, and we have developed an electronics control unit for amplification of the signal. So the test data is shown there, and our devices have been delivered to TBRL, and it is successfully tested at TBRL up to 28,000 G. Further test using the rail track test method is going to happen in the month of June or July. We have developed process technology for fabricating the Coriolis resonator gyro for IASU, and we are going to integrate our dies with the discrete electronics which will be provided by IASU, and we will be qualifying the sensors and supplying to IASU. So annual requirement is around 200 numbers per year. we have established another facility, low temperature co-fired ceramic fab. This facility is used for developing customized packages for MEMS devices, RF packages for MMICs, and this LTCC substrate will be useful as a substrate, basically substrate for building the TR modules. We are working with RCI, LRDE, and SSPL for developing TR modules for AESA radars and missile seekers. The bottom picture shows a typical model. There is a LTCC substrate on which a TR module will be built. Our team has developed a technology for embedding cooling channels into the LTC substrate so that the heat developed by the high power devices can be removed using the channels. So this technology has been patented. And coming to the indigenous IR sensors for night vision and missile seekers, IR Tech was established with COT from SSPL in 2021. It is the only foundry for production of cryo-cooled IR FPA in our country. It has 95% indigenous content, so that complete ecosystem development is done in the country. So the picture with bumps is showing the semiconductor device fabricated at StarC. Basically, it is a PN junction developed on MCT wafer, mercury carbonate telluride wafer, and bumps are created by our team. And another wafer will be there where electronics will be there with bumps. Both will be flipped together to form a flip chip bonded device. The picture which is shown, this image is taken using the IR sensor that is developed at StarC. And our sensor has been integrated in DDCA, basically revar detector cooling assembly developed at StarC, and it is tested in missile seeker by RCI. That image shows the image captured at a distance of 5 kilometers using the sensor, IR sensor developed at StarC. And we are working with SSPL, GATEC, and StarC to develop indium gallium arsenide based shortwave IR sensor also. Basically, indium gallium arsenide wafer is processed at GATEC for realizing the diodes, and StarC is doing indium bumps, flip chip bonding, and wire bonding, finally for packaging. And we have also packaged the bolometer device, which is basically the design was done by SSPL and the fabrication is done at SEL. We have done the LTCC package development as shown in this picture. The right side picture shows the image captured by the bolometer device, which is packaged in our fab. So coming to the challenges in semiconductor manufacturing in industry, as we already discussed, we have to meet high mix, low volume production requirement. So the higher cost is the result. And underdeveloped supply chain or ecosystem, basically lack of strong local companies for wafers, specialty gases, ultra pure chemicals, high purity materials, and photo mask applications. These are all forcing us to depend on global vendors. So that is creating import related risks. And we have to fast upgradation we have to do for our equipment or facilities to cope up with the technology evolution. Unfortunately, sometimes funding issues are encountered, especially by StarC. And because of all these reasons, we are not able to have global competitions. Of course, the improvement is happening in the situations with initiatives of Government of India through India Semiconductor Mission. So there are countries they are not having VLSI foundry leadership. They have 65 nanometer technology or legacy node technology or 180 nanometer technology, which is sufficient for meeting the strategic requirement. We don't need to go to 5 nanometer or 14 nanometer technologies. So this technique of build around self strength is followed in some countries, and these technologies is enough for building ROICs for MEMS. So these are all the collaborators, academic and industry collaboration that we have. Thank you very much.
Thank you, Dr. Sai. Very informative for this. In the interest of time, I'll make just one line comment that the major problem which both GATEC and StarC are mentioning, this high mix, low volume production. So things are improving with India Semiconductor Mission creating the ecosystem in the commercial, and also the government's policy for export of military application products. So with that, I think you will get more requirements. With this, I'll request DG SCL to make its presentation.
Respected dignitaries on the dais, my dear friends, it's my honor and privilege to be part of this workshop on delivering the talk on the challenges and relevance of the self-reliance in the area of microelectronics, as was told by Utpalji also, that semiconductor is a very, very important part, a foundational element of any of the system or the subsystem. And the last 4 decades, SCL is doing a lot of things for the strategic sector. From the last 3 years, we have delivered more than 50,000 chips to the strategic sectors. The chip consists of digital ICs, analog ICs, mixed signal ICs, optoelectronics ICs, as well as sensors also. We are also working on the system domain also. It is a hallmark of SCL that from whatever we are delivering, there is not a single field failure till date. We are doing innovation, we are doing customization, we are doing lot of R&D, we are doing reliability, and that is the legacy and hallmark of SCL from the last 4 decades. This is something like the overview. I just give you that landscape, how the semiconductor is changing. Whatever you used to see 4 or 5 years back, I think a single chip is doing all the work. Now you can able to see your CPU, GPU, AI is a single chip itself. And that is why there is a concept of system on chip, where single system is making all these things seamlessly without any disruptions, and you are not able to notice it also. Now, what are the top 10 economies? You can able to see India has just crossed $4.3 trillion of GDP. We also see in the right-hand side, NVIDIA market cap value itself is $4.5 trillion. So you can see a chip company itself is overpassing the GDPs of a single country itself. So that is the power of a chip. You can always find out a lot of chip semiconductor ecosystems, lot of countries, because there is a full ecosystem. Some countries are fabless, some countries only use the designs. So it is a 4 and 5 countries which is holding all these things. And the moderns, you can see the modern supply chain, because it is all depend on the semiconductor chips, because if that chips are not there, not a single system can be fabricated. And that is why it is known as a digital diamond. It is the new oil. Going with the semiconductor, you all are well aware of the semiconductor. It is something, the interconnections between lot of things, chips and all, on a semiconductor substrate. But if you see in 2025, when the market is around $700 to $800 billion of this, the integrated circuit market is 80 to 90% overall market. It consists of digital IC as well as analog IC. Digital IC consists of 70% market. Analog market consists of 30% overall market, and mixed signal is also there, 5 to 10% of the market. Apart from the semiconductor, there are other things also which is in the overall system, that is known as sensors domain, optoelectronics domain, and discrete domain. And SCL is working in full plethora of these domains. We have initiated discrete domain also. And now whatever has been told also, this economy, world economy will touch in the semiconductor in 2020 around 1.6 trillion, and India is going to touch around 110 billion in 2030. So there is a lot of scope, because whatever we are making the system, it is all with the imported chips. Going with that, how the chips are the foundational elements. So you can find out from this plot, if I have a component, I make a board. From the board, I make a module. From the module, it goes to the system. So if you see overall the systems, earlier in 70s and all, when we are talking about in automobile sector, where 95% was mechanical, today autonomous vehicle have 95% of electronics, and chip play a very, very important role. In that itself, if you can see the chips, electromechanical chips are there, FPGAs, ASICs are there, active components are there, passive components are there. Now SOC is covering a lot of things, but if you see that how much financial implications will be there, the ASICs takes only 10%, but overall system, it makes 60% costlier. So that is there. You can find out from the plot itself, the material cost itself is 80%. In the material cost itself, the 50% cost goes to the electronics, and chip itself takes 50% of the cost. If you take memory also included, it becomes 60% of the overall cost. So what is the chip manufacturing? I am just giving you a brief overview before I will go to the SCL. The chip manufacturing consists of lot of steps. Either it is diffuse steps, either lithography step, either etching step, metallizing step. But in 180 nanometer, which at present in SCL, we are having more than 400 steps. If you go for advanced node, it is more 700 to 900 steps which you used to take. After the chip is get fabricated, it used to go to ATMP process, and whatever you are seeing, it comes out as a product, which in the bottom layer is traditional way, dice it, package it, assemble it, and it used to get delivered. Now there are different things, subsystems where are there in the chip manufacturing. Overall product, when it comes out, it starts with design. So in the design itself, you have a lot of EDA tools. We used to get a lot of companies which provide you IPs and all. Then in case of manufacturing, there are two types of manufacturing, front-end manufacturing and back-end manufacturing. there are a lot of equipment manufacturers used to give you, and these equipment manufacturers are semiconductor manufacturing equipments. There are also raw material suppliers and all also, which plays a very, very important role. You also used to import lot of lead frame packages and all. After that, it used to go for screening, it used to go for qualification, and it used to go for distribution. Now, what are the main things here itself? You used to have in any fab uninterrupted electricity. You used to have lot of raw materials, gases and chemicals. I will just brief you in SCL what we are using. And you also used to have some mechanism for toxic and hazardous, which are the gases or chemicals it has to get disposed of. Now, what is the technological advancement? What you are seeing is whatever in 70s and all, which we used to talk about some transistors in millions and all. Now we are talking about trillion of transistors in mm square and all. So what is the factor which is governing this? The governing factor is you used to have compact and faster chips should be there, and you used to have lower power consumption, and that is why you can see the codes which is written in Apollo 1 and which is written in self-driving vehicle itself. You can see there is 2 order increase in that. So when you are doing this type of things, when the trillion or transistor has to come inside 1 mm square and all, so what is the speed increase is too high. It goes to 50 gigahertz and all, but the critical dimension you can able to see we are touching around nanometer and all. When you are fabricating all these things, your various challenges which comes out, I will deal one minute on each challenges. But what is the concept of making from mature node to advanced node? There is a concept of scaling. So this concept of scaling, what it does is, it get density get increased, your clock speed get increased, your metal layer also get increases in that. Now what happens when you go for advanced node? So there is a comparative table. You can able to see that the clock speed is increasing, gate density is increasing. But what is happening in this case is you used to get lot of leakage current, and that is why you can able to see when I am going to 45 nanometer, my leakage current is drastically increased, 2 to 3 order increase in that. Number of masking layer is increases, and that is why here you have to counter, because lot of yield issue used to come when you are going to the lower node, and there is also a lot of reliability issues used to come out when you used to go for advanced node, and that is why the packaging and material consideration plays a very, very important role here, and that is why ATMP plants which are coming or heterogeneous type of packaging or high power packaging plays a very critical role here. Now, what is happening in the design? There are a lot of challenges because earlier the design was going in a horizontal way. Now, what is happening? Technology is shrinking. You are going for advanced node. So designer has to be told that you have to shrink your time. So designer has to do verification, DRC SAC, and everything he has to do in a shrinkage of time, because you are not changing the time of manufacturing, because layouting and IC manufacturing is not changing the time. So designer has to do, and that is why when you are going for lower node, the design complexity increases, as well as the cost of the design in 2 nanometer and 3 nanometer is very, very enormous. Going with that, another concept is if you are going for analog type of design, the analog is not shrinking. Only the shrinkage is coming in the digital thing, and you can able to find out when you shrink the technology, DSM effect starts there, and that is why analog becomes bigger and bigger when you go for lower and lower node, and that is why whatever the technology shrinkage advantage is coming, it is only coming in the digital domain. So what are the fab challenges? If you are running a fab, so it's a huge, huge investment. You can see one of the lithography, there are only 2 or 3 EUV, which is there. This equipment is there. Only 2 or 3 countries possesses that. Only one manufacturer is making that. It costs around 3,500 crores and all. So this is the cost of EUV, because there is 3 decades of research is involved. You need highest quality of raw material. You get 5 and 6 in purity of chemicals and all. You need lot of clean room class 1 and class 10 of operations. You need dedicated maintenance team, because it's very, very complex systems are there. You need lot of contamination control, and you need very intensive coordination, because if there is a failure, how this failure is erupted, how to take care. So that is why this becomes a huge, huge investment which is involved in that. Now, if you can manufacture is either you can test it also. So this is also very bigger question. And now when the Moore's law is going in deep and deep and going lower and lower, but testing is not scaling. And that is why the test cost is increasing, because pad size is not shrinking and all. And that is why you are able to get new type of techniques like wafer bonding and all, rather than going for the pad type of geometry and all. So what is the semiconductor value chain? So it is very, very challenging, because 70% of this value chain is concentrated only 3 or 4 countries which are governing that. And that is why in the case of pandemic, you got lot of interruptions in that, because these countries are only deciding what to be given, what to not to be given. And that is why this has to be overcome. And we have ISM mission from there itself. You have already got within 4 weeks itself, 2 plots got operationalized, and that is why I'll just give you the brief. There are decades where nothing happens, and there are weeks where decades can happen. So that is why it is happening in the case of India itself. India is growing, more 2 or 3 plants are coming, and in manufacturing also from 180 to 28. As far as India is concerned, I think Tata is coming with that. Now I'll come. India has a lot of advantage. India has a power. India has a talent pool. India has a domestic market. I think that can be leveraged with this type of ecosystem which has been created by the government. I will just give you within 2 or 3 minutes the SCL overview, because the challenges I have just briefed you. So SCL is an IDM, integrated device manufacturer. We used to take build to spec, build to print. More than 50,000 devices which we have given, and more than 1 lakh devices which we have given from last 10 years in 180 nanometer node. We do miniaturization and customization. We work in plethora of areas, and now we are doing a lot of things in skill development and all. We have a one-stop solutions. We have a vertical integrated facility. So this is a look of our facility. We are more than 70 equipments in 8-inch fab. We are more than 40 equipments in 6-inch fab. We are also running 1 compound semiconductor fab. Going with our clean room environment, you used to see a lot of things which we are using. We are using more than 25 of chemicals, 25 of gases and all. We have uninterrupted supply. We use a lot of monitors and all. We used to give a lot of emphasis on safety protocols and all. Going with the lab ready to market ready, we start from TRL level 1, we go up to TRL level 9, and a lot of our products, even each of the ISRO products, each of the ISRO mission is having our product, SCL products in that. And that is why whatever you are seeing in the Chandrayaan 3, when the Chandrayaan 3 was doing the descent, where it was autonomous operations, where chip was only governing it, where it has to do soft landing, the chip was given by SCL itself. So this was SCL which is giving chips not only for Chandrayaan, for Aditya, Mars, and now we are supplying regular chips for Gaganyaan also. Going with Indian Railways, we have given more than 1 lakh chips to the Indian Railways, and we have started making the same fit and form in the plastic also. We qualified this plastic line also, and we are providing them. Going with other devices in SCL, which I brief you, ISRO is taking from all their launches as well in satellite operations. We are giving 50% of our overall revenue or overall market to the ISRO itself. Going with international collaborations, because we are highly reliable fab, we are trusted and reliable partner. More than 1 lakh chips we have already given to Sun first experiment. We are giving more than 1,000 chips in the Sun second experimentation. We have also given more than 30,000 chips to FAIR, Germany. Now give miniaturizations. We are also doing a lot of things in the miniaturization. Already in ISRO, one of the board has been miniaturized 50%. We are now doing 90% of their miniaturizations. We are also working a lot of boards, assembly activities also. Here you can able to see from 180 nanometer, whatever is existing was reduced to 30% of the component count reduces, because the technology node is something like 180 nanometer from the legacy node itself. A lot of processors which we are developing with academia support, with ISRO support, as well as CDEC and all is also collaborating with us. This is also one of the things which we initiated recently is the chip forensic analysis, which we are doing it for lower node and all also. There is one more collaborative thing which we are able to see. 19 IPs have been made one SOC, and you can able to see this is successfully delivered. Within a year itself, we have not only designed, we fabricated, we tested and delivered it. It is academia partnership as well as industry partnership. We are also doing, I think it has already been covered, where ROIC for this bolometer has been developed successfully at SCL. Now we have full capability of cooled ROIC, uncooled ROIC, and now we are giving the vertical integrated detector with ROIC from 180 nanometer fab. Now this is one of the things which is, I am giving you the thought process where SSLV is using 50 of our chips from sensors to various ASICs for the launch vehicle itself. Now you can see in the BrahMos also, you have a lot of components, lot of payloads which are coming from navigation to flight computer, sensor and actuators, RF things and all. Now there should be synergy. There should be leveraging whatever SCL can give. I think what SSLV can use, what ISRO can use, the same qualification is happening. Will grade qualification we are doing space grade qualification. The same component should also go to the missile systems. So this is one of the thought process for this event, that whatever the chips we have developed for this strategic sector can be useful. Now I come to the last slide. There are a lot of issues which we are facing, like component is obsolete, components is counterfeit, there is gray market, there is a high cost. So there should be way forward. So there is a lot of things which we have to think beyond this. We have to do applied and service R&D, not basic R&D, because we have to think about the system itself. We have to forecast the complete value chain. The another thing is we have to trust it. Lot of things which are in the commercial market can be useful, can be screened and can be useful. For the military grade application, that has to be looked into. We have to be resilient. We have to go for geopolitical risks. We have to overcome that. We have to use local fabs more, OSATs and PCB and test facility. And the COTS uses for mill grade requirement should also be thought of. So soft power, we have seen in the recent war, no place. We need to build real hard raw power, and then only we can become a Viksit Rashtra. So Jai Hind and thank you.
Thank you, sir. We have not provisioned for the Q&A session, but I want to ask one question from you. No, please do. What is your views that for strategic applications, here you all are having fabs. What is your views about the fabless companies? I mean, for strategic things, we should go for fab-based things so that military has control, or we should go for fabless.
So it is always better that we should have a fab.
Economic.
And the question which comes to me is, I think whatever the defense and all is working or strategic sector is working, they don't need that advanced nodes. They can evenly go with the mature nodes also. And we can take the leverage of the mature node itself for the advanced node type of capabilities. There is architecture change. So whatever you are designing, first of all, you should have proto with the country itself, so that IP should be maintained in the country itself. The proto can be scaled to the lower node for different applications and all. But meanwhile, whatever study used to say, whatever the system we are using, whatever nodes we are having in the country, 180 nanometer, all the requirements can suffice for that.
Thank you.
Thank you, sir, for moderating this part of the session so effectively. May I request the chair, the co-chair, and the panelists to join for a group photograph. May I now request our esteemed session chair to kindly step down from the stage and join us at the center, that is the front of the stage, for the presentation of mementos to our distinguished panelists and the co-chair. May I now request Lieutenant General Atulya Solanki to present a token of appreciation to our chair, Dr. Parimal Kumar. Thank you, sir. We'll now move on to the second part of this session, and the distinguished speakers for this session are Mr. Jyotis Indrabai S., CEO Netra Semi, who brings 30 years of fabulous semiconductor experience from Intel, Hitachi, and multiple Silicon Valley startups, In 2020, he co-founded Netrasemi, a Kerala-based edge AI semiconductor company building AI-capable SoCs for secure surveillance, smart sensors, robotics, and mobility applications. Mr. Dilip Kumar S., who is currently the Vice President and Head of the Center of Excellence for Aero, Space, and Defense at SFO Technologies, Cochin. He was instrumental in setting up the R&D division of SFO Technologies and contributed to the design and development of hundreds of products in diverse domains. Mr. Lalit Ambasta was an esteemed IP attorney with over 18 years of experience in intellectual property ecosystem, particularly focusing on geographical indications and IP monetization. He is dedicated towards IP awareness and education, recognized as a speaker and faculty member under the Ministry of MSME, Government of India. Mr. Mohan Jindal, CEO of Chip Spirit, has an extensive and rich experience of 25 plus years in VLSI design, verification, and implementations. He has taped out for the first time Right Silicons and as project manager and taken responsibilities for 40 plus tape outs at multiple levels of execution. Mr. Ranga Raj, Director, Level 5, Cartronics Technology Private Limited. He's an engineer entrepreneur with deep roots in India's technology ecosystem, with over 3 decades of experience spanning IoT platforms, embedded systems, digital infrastructure, and semiconductor strategy. He's led the technology commercialization efforts across India and the United States. Dr. Sondor Lakshmipati. He's a highly accomplished professional with over 40 years of experience in cellular communications like 4G LTE, 5G, 5GA, and hardware software platforms like System on Chip, DSP, and GPUs. He is an expert on subjects of MIMO, space-time coding, and various signal processing areas. Currently, he is the CEO of Valedictory Labs India Private Limited. May I request the speakers to deliver their views and share their content in the order they were called. Thank you.
Good afternoon, everyone. This is Jyotis Indrapai, CEO and co-founder of Netrasemi. Thank you for having me here. So, before starting to explain what Netrasemi does, so let me just give a view of the latest technologies happening around the world and at how it affects the defense. So today we are in AI era, where AI is dictating almost all segments of human life, and defense is no different today. So everything that goes into civilian world is also applicable to defense. So in AI era, the strategy sector, the sovereignty of the country in strategy sector is dictated by how the country handles AI development, how ready it is with respect to AI and its indigenization. So in summary, in AI era, there is no strategic sovereignty for a country unless there is AI chip sovereignty. Why can't we just buy it from external countries? Because they may not sell it to you. There is a total export control around the world for AI chips, and there are not too many producers around the world. Only 2-3 countries hold the technology, and they will choose whom to sell those technologies. So that way, almost all countries are in disadvantage. India is no different. So our technology sovereignty and defense sovereignty will be dictated by how well we move on the AI chip building. So coming to this point, what Netrosemi does. So we are a chip company, especially for civilian applications. We are building AI chips, primarily targeted for on-chip, on-device computing. So we are getting into spaces like surveillance, CCTV, edge AI applications like smart gateways and things like that. And of course, these have very good significance when it comes to strategic domains. So going to the next, let me just talk about how these AI chips are different, how they are not like, for example, the gallium arsenide chips or silicon nitride chips, or for that matter, any simple system on chips. So AI chips have a totally different anatomy. They need a totally different processing architecture, hardware acceleration architecture, which was not common before. So if you look at the history of multiple decades of MCUs and microprocessors, you will see totally different type of algorithms being used for processing. AI chip demands hardware acceleration, huge amount of processing power, huge amount of data movement, huge amount of packaging requirements, thermal requirements. So that way, AI chips are totally different. They need hardware acceleration IPs, and especially comes to the strategic domain, they need extremely high security. Because today, if you look at the regular chip, like a civilian chip versus strategic electronics chips, there are threats like Trojan hardware, Trojan software, which sits in your chip for a very long time until it really wants to act. When the drone flies from India to Pakistan, that time the Trojan activates and your drone will be in trouble, right? So there are chip security is extremely big concern, and that will dictate what kind of processors you use. So I'm not going to the deep. I think it is there in the slide. So what Netrosemi does, I'll get to that. Netrosemi is the only chip company in the country today capable of building AI capable chips. So we have produced the first AI chip already. So it is there in the country already. It is produced at 12 nanometer TSMC, and it achieves 8 tera operations performance. So it is already done. And we are maturing it, and we are taking it to production by next year. And this is a civilian applications, and it is having like surveillance capabilities like video analytics, inbuilt CV algorithms capabilities, MIPI interfaces, and extremely good NPU neural processor accelerator inside. So we have raised like $15 million USD funding last year, and this is the highest semiconductor funding in the country. So we are all set for and we have 2 chips taped out already in TSMC 12 nanometer. And we look forward to creating strategic electronics chip for India's strategic needs. We are working with CDAC, and in fact, we are working with some of the strategic sector companies to transform this civilian application chip into defense-grade chip. So this is the full. We are talking about a full stack AI silicon. We build the complete IP inside. We build the chips. We are taking it all the way to production and making it ready for the country. So the 2 chips, the R1000 and A2000 are already taped out in 12 nanometer. And we are also building 2 more chips. And A4000 is an extremely server grade chip that is going to be ready in 2028. So this is the portfolio of silicon IPs we are building. And these are extremely secure. They enable full chain of trust, which is extremely important for the strategic sector. And this is one of the surveillance portfolio we are enabling with our 4-chip solution. And there are several applications we can enable in the country, like drones, autonomous robots, things like that, which are extremely critical for the segment. And we are looking forward to cooperate with the defense companies in the country. Thank you.
Good afternoon, and thank you very much, the organizers, for the opportunity to present our company here. SF4 Technologies is an old company. We started in 1990 as an export-oriented company in Cochin. And during the years, we have grown up to now 7,000 plus employees. Around this financial year just ended, more than 400 million USD turnover. And we are a totally vertically and horizontally integrated service provider. So you can see that we have pretty much everything that is required to realize a high technology product like PCB assembly, cable wire harness, sheet metal, plastics, stamping, tool making for the stamping, plastic and all, machining, fiber optics and photonics, magnetics and transformers, connectors and terminal, composite and box built, everything is there. And what you don't see here is a little bit smaller business, that is semiconductor packaging. We started in 1993 by packaging a piezoelectric sensor that included die bonding, wire bonding, and creating a package with a piezoelectric sensor. Then we moved into fiber optic transceivers sometime in 94, 95. And that time it was state of the art, like 155 Mbps communication links we started manufacturing. Then we moved into laser, semiconductor laser packaging. TOSA, ROSA, the sub-assembly packaging like that. That is a small business that is still running. There is a class 10,000 and class 1,000 clean rooms and all facilities for packaging. It's a small business, so it may not be their feature in this 400 million big business that we are doing. And we also, we started as an export company. Purely for export, because export processing units were not permitted to do domestic business that time, long time ago. Then when the policies have changed, we started working with, DRDO first. NPOL is our neighbor in Cochin, and we started working with them. Now we are a major partner to them. And other labs like CABS, LRDE, SSPL, CHESS, and other labs, CSCR labs like CGCRI, NAL, like that, we are a major partner to this on various programs. We are also doing manufacturing solutions now, that is for the test automation. Not into semiconductor yet, but we are looking forward to diversifying into that also, semiconductor testing. This, what we have right now is system level testing. And also end-to-end development we are providing, that is a build to spec services. We'll be quick. Our locations, we have a total 22 factories. There are 4 locations in Cochin itself where our headquarters is. There are one cluster in Bangalore, that is 4 individual facilities, one in Pune, and there is 2 in the US and 1 in Thailand. There's also smaller facilities in Trivandrum, and we are also expanding into Chennai and development center in Bangalore. Now, hardware design services, we have electronics. Any complexity of electronics is there. Power electronics is a major competency, center of excellence is there. And this center of excellence is actually now supplying power systems for many of the defense and aerospace programs, including the power system for AMCA, power system for the light transport aircraft CIRS Mark II, and we are also now trying to get into the drone programs with power systems. Photonics is another major capability area, fiber components, active, passive, including optoelectronics packaging, low power lasers, high power lasers, including the weapons grade lasers for the direct energy weapon program we are doing. And mechanical is part of all projects. And software, we have a major software facility, around 1,500 people. So all the products which we do, software is done by them. Also, they have their own businesses, including business applications. And vertically integrated manufacturing, we are pretty much the only company with this kind of wide spectrum of manufacturing services, including electronics, machining, tooling, optronics, optoelectronics, photonics, mechanical, plastic stamping, cable and wire harness, everything. So this one, we are supporting many verticals actually: healthcare, industrial, automotive, transportation, industrial, along with aerospace and defense. Aerospace and defense is a growing segment, and it's like currently probably the highest revenue earning, but most of it is actually export. Yeah, I'll summarize here. So our plus point is that this vertical and horizontal integration, all development and manufacturing facilities and capabilities are available for supporting. What you see here is airborne, but we are also underwater, on the surface water, on the ground. For all spectrum of systems, we are supporting both design, development, and manufacturing. And semiconductor is one of the areas, growth areas, which our company have a vision in. So we will be moving into that and partnering with both the private sector and public sector companies to get our capabilities and long-established credentials to help into growing the business. Thank you very much. Jai Hind.
Good afternoon and Jai Hind. So I'm IP attorney, so my perspective would be entirely different. We have seen since morning till this session also, we have done a fabulous job in semiconductor and this area. But our eye is mostly the patent database where we stand. So if you see the patent stats sometimes reflect the development of any country. So for your example, how many patent Pakistan is filing? Any idea? Any idea? 10,000, 20,000, 50,000? They are filing below 1,000. Below 1,000 in a year. So sometimes patent reflects the development of a country. So it's a good, India is filing more than 60,000 applications. So we are developing. So moving forward, mostly in this segment, the semiconductor aspect. So our eye is different. When we see our job is to strategize the entire ecosystem, how you will develop. So suppose aircraft, what is the meaning of aircraft? So fighter aircraft is a battle in the air, but we see here as a battle inside the chips. So who controls the battle now? Who owns the chips, right? So who is owning right now? So you are aware who is owning and how they are controlling the battle. So if you see, if we wish to develop, suppose the aircraft entire chip technology will be developed within 10 years. So whether we are focused, whether we are aware, what are the layers, what are the platform, how we will evolve. So these are the platforms. So sometimes it might possible we have a certain technology in intelligence, we have a certain technology in communication, but we do not owning the entire things. So until unless we will own entire thing, we will not have a control. And that is why whosoever is owning, they are controlling the entire game change, and there is a geopolitical aspect. So similar aspect in radar also. In the similar way, if you check any device, you have a platform, you have a layer. Like patent, we develop in a layer. So suppose you are filing a patent on device. This is a layer 1. If you are filing where device is communicating with another device, is a layer 2. When your entire system is thinking, then this is a layer 4. So whether how we are filing, it decides through how you are aiming. So trust me or not, we are not focusing in this way and we are not developing in this way, though we are filing. But if I say about semiconductor aspect, so if you see, these are the areas in the semiconductor aspect. So what is the stance of India? Any idea for each and every aspect? If you see, in power and control, we have hardly 20 to 40 patent we have filed. I'm talking about Indian. So it might be from government side, might be from corporate side. In the similar way, 50 to 100 in processing in the similar way. So in total, if you see, Though we have certain strong point in R&D, in SIC, we have a strong point in indigenous design in Sakti. There are various other aspects where we are lacking. So if you see the overall stats, so US is holding somewhere around 1 lakh patent plus in semiconductor, and in China holding 1.5. India is holding 400 plus 700 only. So these gaps are not the number gap. These gaps are control gap. So these are the control gaps. So we have to also think, though India is doing right job in terms of many other aspects like GAN is another aspect where we are holding the same position as US, China and Europe. But still we have a precision IP, but we are not holding IP in semiconductor. In the similar way, if you see, when we say the slogan Make in India, what is the meaning of Make in India? We are assembling. So what is the meaning of design in India? We are developing. What is the meaning of patent in India? We are protecting. And what is the meaning of owning in India? This is control. So currently we are Atmanirbhar Bharat, we are telling about Make in India only, right? We are not talking about design, patent and owning. So moving forward, this is the current, though in the global chip war, India is not late. It is uniquely positioned to build a secure, self-reliant ecosystem from the ground up. So thank you so much. Jai Hind.
Good afternoon, everybody. The distinguished guests on dais and off dais, Mr. Patania, sir, one of the esteemed customer we are working with for the Indian defense systems. So Mr. Lalit told about IPs. We have filed 16 IPs in last couple of years on the semiconductor design and developments. Thank you. So in terms of software versus hardware, on the encryption side, I think there was a presentation in the morning where we talked about the hardware-based security. So why it is important? I think this is the best forum to talk about it, because software, there are different layers on which there are vulnerabilities in every layer. Whether you take the application layer or the session layer or the operating system layer, Trojans, processor, instruction set also are being hacked these days. And there are not only the attackers who are adversary, state attackers are also there who want the control to your systems without your knowledge, with their full intention. While in the hardware-based systems, if you see backdoors, if you indigenize, you develop yourself within a sovereign technology among your own team and with under the control, as was mentioned in the previous session also. Previous speaker also mentioned. So if we do it ourselves, backdoors, Trojans, zero. Application is like only dedicated application. So what we have developed, I'll go to the solutions also over here, based on FPGA, where we are doing our own. The processor is also our own, like Shakti processor or other processors. Here we have developed, actually we have broken the processor also. I'll go to that in detail in the next slides. The key management, the memory management, all the access to the memories, the flash, all the SRAMs is fully controlled by our own controllers. So that is what we have developed. There are backdoors, Trojan loopholes in the procured material. The supply chain. Supply chain is okay. You understand the logistics from where it came. But within the design itself, if there are loopholes, what you will do with that? So there are the questions. There are questions I think have been asked since morning. Let me go to the next. So chip spirit into the chips is our target. That's what we are doing. Since Feb 2019, white papers, we are one of the DISC 1 winners IDEX this one winners Defense Senior Startup Challenge for secure hardware encryption device, whereby from the white papers, from the concept, single sheet with the VESI team in under the guidance of Commander Sharma at that time and Captain Wahi at that time. We developed the systems, full system. Feb 22, you see the kind of what this acrylic sheet material, then the display and the keypad, and then we have done different things. And 2U material. Abhed 1 is our device which is ready today. We have filed 10 patents are granted, 6 are pending in progress. That will happen. So we are already under under the leadership of our current defense forces. We are already executing a couple of orders, marching towards the vision of silicon and solution development. So this is the FPGA-based solution, and certainly we need FPGAs also. We have been talking about silicon. Silicon is very, very important, definitely, and FPGAs also have their own flexibility that they bring in. The flexibility of having your own algorithm, your own controllers, your own ways to control the keys, your own ways of protocol management. So those are the flexibilities which FPGAs also provide. While, of course, for the form factor and the power, you have to go to the scale of silicons. So here we have about 6 products that is under display, which are ready. The first one is the offline product, which is USB to USB, plain text to ciphertext. So I'll take maybe 2-3 more minutes. So no software. There is no operating system in the devices that we are developing. No software means their virus cannot reside. No core also. So even instruction set attacks not possible. No Microsoft, no Intel in that manner, from where you need an upgrade for your devices. When it is in your secure place, nobody comes to your secure place. You are full ownership, full control, in full ownership and control of the devices that you have developed with your own algorithms for encryption, your own algorithms for data transactions, your own algorithms, even the USB protocol. We have developed indigenized fully the full stack for the FAT32 read and write into the USB sticks is developed by Chipsplit only. So those are the patents that we have filed in terms of implementing everything into the hardware only. So that is the offline system, USB to USB data transactions. And then we have Ethernet, where we have a secure video conferencing available. We have stall at stall number 11. You can visit. USB copy over the internet. You plug in the USB in Delhi. There is a tunnel which is dedicated tunnel which is established from the Delhi to Bangalore, which is with hardware only system, no software again. Full tunnel is established. Sessions are managed. Keys are exchanged. Session is managed fully and tiered down also through our only algorithms that we have developed. And at the destination, you will get a USB copied in, let's say, in Bangalore or wherever you want, as per the destination programmed after your authentication, after your proper authentication of the normal user and dedicated administrator user also. There is a dedicated tamper also. If somebody opens the lid, everything will be erased within 3 seconds. And there is a dedicated battery. Even in cold storage, the device is active for the one tamper action and one tamper detection as well. Secure boot. Somebody was talking in one of the previous, I think, one of the presentations. So everything, all these, what you see in the tops, all are these features embedded in different devices as per the data sheet of those devices. And of course, their data diode is being used by CERTIN as well today. As on date, they are using the data diode in their premises, and they found but some of the issues in their own systems, because there was something which was going back on the previous data diode. So our data diode, when they established, they told it is not working fine, but it was working fine. Then we proved it with our own some of the software, but this is plug and play hardware based. If you see, this is a very small kind of half-U data diode which they're using in their own systems. Fully customizable. We own the bits and pieces, everything from the bit to bit and of the implementations, USB to USB or Ethernet to Ethernet. TRNG, of course, is proven and scalable platform for the next generations as well. A lot of use cases. I think data diode we talked about. We are 80+ team members in Bangalore. I'm Mohan Jindal. I worked with Intel for about 10 years and a couple of other companies, Broadcom, LSI, before starting Chip Spirit in 2018. Winners of IDEX, we are working with METI, we are working with CDOT also under TTDF scheme. We are winners of, we are working in 3 ministries as on date: Ministry of Defense, Ministry of Telecommunication, METI, and Ministry of Communication. So overall, we have got about $1 million worth of grants from different ministries. This was one of the best awards that we got. I mean, we are really proud to be working with our defense forces. Our whole team is very excited to. And when the men in uniform come to our office for the visits, our whole team is very proud to be actually interacting with them. Thank you.
Good afternoon. The topic of Atmanirbhar for a secure Bharat was talked about a lot from the morning, so I really want to emphasize in terms of what we really plan to do. My name is Rangaraj from a company called LFC. So a lot of you would have heard about different news about how the grids have been brought down, drones have been brought down, CCTVs have been hacked, and nuclear power plants, and so on and so forth. All of these are because of things like backdoor entry of hidden vulnerability. There's kill switches where you can bring down the entire infrastructure if required, side channel attacks, and then, of course, the supply chain vulnerabilities overall. A lot of, even though there are, you know, global certifications on security, we have seen Trojans actually hidden there for multiple years, decades nearly, and then suddenly being activated. So blindly trusting even global certifications for security is not necessarily something that we can believe in. The good part of it is that India has realized the need for critical infrastructure to be secured across multiple things, whether it's in energy, communication, surveillance, the commerce side of it, and so on and so forth. And it's important to really secure our critical infrastructure. The sad part of it is that all of these infrastructure is currently 100% controlled from a security perspective by imported chips. What that means really is that we are sitting ducks for any vulnerable attacks that you've seen earlier. So we really need to solve that problem. So as level 5 Cartronics, what we do is that we've been in the clock timing, interface, and power management chips. And what we realized in the discussions over the last year is there's a need for an integrated, sovereign, secure silicon trust platform that is required from the country perspective. So that's the other area that we're looking to build up. I want to talk to you about two specific areas. One, which is EMI issues, which a lot of you who have been in the electronics side really see. So we have an active EMI suppression technology, which we call CISC. The problem really is that when you start designing any circuit, then you go do the testing, and then you figure out you have EMI issues, and then you go back to the drawing board. It's a big problem. So what we really came up was that we designed this active EMI suppression using spectrum technology into our chips in the silicon, and so it's handled at the source. And I'll give you a couple of examples. In the automotive space, a couple of our customers saw that with the high-speed cameras for ADAS signals, they started seeing the lock of their low-orbit satellite navigation was having an issue because of the bleeding effects onto the 2 GHz spectrum. with the ability to just pin-to-pin replacement of the oscillator with our active EMI suppression, they were able to get a complete lock on their GPS signal. Similarly, with a drone company which do swarms where you launch from a truck, when they did a return to the truck, they found that there were multiple meters of accuracy of GPS issues. And again, when we started seeing EMI issues, when we used our technology, we were able to bring it down to a centimeter of accuracy. The other area that we are working on now is something which we call YODA, which is that we have to really look at a sovereign silicon platform, which will have the ability. So traditional platforms use SoC-based and software-based ones. So where we are really looking at is a horizontal technology where we have the PMICs for power, the oscillator, and active EMI, and then add the ability for a secure silicon all into one single package overall. And that way you do a single secure solution for multiple products and multiple applications across multiple verticals. This is, I think, probably the most important slide that the country needs to realize that traditional security is SoC based, and they have a lot of issues on security, as so is the case with even a secure element HSM. And with the advent of quantum computing, these two platform technologies really can be hacked in seconds. So essentially, we have to really look ahead, and that's the reason why we're going into the physical, unclonable function, which is the PUF architecture for silicon-based solutions for this whole thing, for the secure solution overall. So what this really matters for the defense, whether it is in UAV for precision timing power, as well as active EMI suppression, as well as security for ISR, for secure communications, and all of it, so that you can start looking at anti-jamming, a hardware trust, EMI, Indian origin, and a complete integrated, which is completely auditable right down from the design to the manufacturing. And we plan to use SEL as well from a. So overall, what we're really looking for from the defense industry is to see if we can potentially partner for pilot deployments using this technology, and then a preference because of 100% being imported. Can we start indigenizing a lot of these components with the Make in India one, and then build an ecosystem of solutions with multiple players in the ecosystem of Indian companies, and then overall look at it from a strategic partnership and grants from a funding perspective as well. So that's really what I had to say. Would love to have more discussions with the necessary stakeholders. Thank you.
Good afternoon to everyone. So I am the CEO and founder director of Valedictory Labs India Private Limited. And so what we build is a very actually recent startup. We have a big vision and a grand picture, and we have also been supported by SAFAL, Semiconductor Fabless Accelerator Program. And so we have both actually civilian and as well as the military side. And why actually we are focusing on this? You can see at the bottom, and I founded the MIMO Wireless in 2009 Indian Institute of Science. We built indigenous 4G LTE base stations and also the device side. and we licensed it to 14 companies around the world, including in US. So we got acquired with all our portfolio of IP and intellectual property, everything in 2019. And I was the CTO of Alif Semiconductor until 2023. And so I recently started this. I exited from the company, then I started my own. So we want actually own the complete military communication products and also launch our own satellites to support, air to air and a drone to UAV and to SATCOM mesh networks. So that is the way actually we want to go ahead. And it's okay. So here actually, we will be owning the complete IPR. When I say actually IPR, it is not simply the patents. The complete design of our own algorithms, the implementation. Example, when we actually in MIMO Wireless, when we were sold to a US company, our IPR, the code was subjected to 1 week, what to call, checking automation, through automation servers, whether our IPR was copied, lifted from somewhere or anything. After all this qualification only, it went for exit. They acquired. So it's very essential that we have to have proper indigenization when we build our products. It is not simply we borrow and copy and paste it, and later on the acquiring company can be in a great trouble. So this is actually our semiconductor system on chip ecosystem. And in a typical modem, you have an application layer, the operating system, then the digital front end, there is a chip interface, there is processors. One is the CPU, which does all the L2, L3, and the MAC layer kind of programs, and the DSP that runs actually the physical layer, the actual algorithms, the very critical algorithms it runs. Then the NPU actually, NPU is the neural processing unit. Now the upcoming actually, the current, and upcoming and the future devices and the base stations must and have the AI ML processing. Therefore, we need to have actually the NPU, neural processing unit. And so we have actually the system on chip, which can be customized by fusing certain cores. So we have I have shown you by the bottom that there is you have multiple CPUs. Some CPUs you can fuse based on the requirement. Example, right side actually I have shown you the 3 products which we are working on. One is NR plus modem, which does not require any SIM nor operator, but it works in the unlicensed band. Another is actually 6G NB-IoT based. This works on the terrestrial networks and also the SATCOM based. Then third is actually the drone, UAV and SATCOM mesh network. This is very, very critical actually, the third product, important, because of the given and the learning lessons actually the present and the past. These are actually 3 products from the SDR we are building. One is ground to ground, ground to air, and air to air. So when I say actually ground to ground or air to air, actually it could be even boat to boat. Even it could be applied for the naval applications also. So there could be thousands and thousands of devices of the drones that will be communicating, and with you can see actually here they'll be communicating with the central nodes, 1 or 2 or many more. As the central nodes vanish or they due to some reason they will have self-healing and self-conferring capabilities. So then they'll point to point and point to multi-point and point to the ground to air, and all these communication products will be building. The entire products, including the SoC and everything, will be owned by Valedictory company, Valedictory Labs. And these are the some specs actually of the modems, which are not exhaustive, very high level specs which I gave, which will be building our products are based on this. So thank you very much. I think I'm running out of time. The bell is getting repeatedly blown. Thank you.
Thank you to our speakers for the engaging and insightful presentations. May I request the speakers to join for a group photograph? May I now request our esteemed speakers to kindly step down from the stage and join us at the center that is in front of the stage to receive the mementos. May I now request Rear Admiral T.S. Patania, Fisher Seva Medal, DG, WESER, to present a token of appreciation to our speakers. Thank you, sir. We now move forward to session 3 on policy interventions required for self-reliance in semiconductors for military applications. It is my privilege to introduce the chair of this session, Ms. Sheena Rani R., who is a distinguished scientist and Director General for Microelectronic Devices, Computational Systems, and Cybersecurity. Previously, she served as Program Director, Agni, and Associate Director for Advanced Systems Laboratory, APJ Abdul Kalam Missile Complex, DRDO, Hyderabad. May I request the chair to please join us on the stage? The co-chair for this session is Dr. D.S. Raval, Outstanding Scientist and Officiating Director. Dr. D.S. Raval is presently Officiating Director and Outstanding Scientist H at Solid State Physics Laboratory, DRDO. May I request the co-chair to please join us on the stage? The distinguished panel for this session are Rear Admiral D.S. Patania, Vishesh Seva Medal, who assumed the charge as Director General of Weapon Electronic System Engineering Establishment. Over a distinguished career spanning more than 3 decades, the Admiral has held a diverse range of operational staff and dockyard appointments. His sea tenures include service on board INS Amba, INS Nipat, INS Agre, INS Kirch, and INS Trishul. Dr. Ranjana Nallamalli, Outstanding Scientist, Director of Futuristic Technology Management, DRDO, has over 33 years' experience at working at DRDO in various spheres and spectrums. During her outstanding career, she contributed to various technology segments. She has brought out many policies and taken multiple initiatives to ease the R&D in defense and strengthen the defense R&D ecosystem in the country. Colonel Anurag Awasthi, retired, was a senior consultant to Government of Telangana and is presently a senior consultant with Semiconductor Future Accelerator Laboratory, Bangalore. He has provided inputs in creating semiconductor and fabless policies and providing inputs for various states in India. He is principal advisor and executive director of MEDEPC and CEO of Escape Velocity Media Works Private Limited. Now, I would request the chair to please conduct the session.
Good afternoon. Here we are going to discuss on the future pathway under ISM 2 for the self-reliance in semiconductor in military applications. So as part of the military application, there is a huge requirement for the semiconductor, which are the economic, not only economic enablers, but also the strategic assets, which are forming the backbone of the modern air warfare systems, including the radars, electronic warfare, secure communications, autonomous platforms, and space technologies. In this context, self-reliance in semiconductors is a national security imperative and necessitated by supply chain vulnerabilities, technology denial regimes, and risks associated with untrusted hardware. So now our government has initiated the India Semiconductor Mission 2, which will be a decisive shift in India's semiconductor strategy from establishing the fabrication capabilities under ISM 1 and to building a comprehensive end-to-end and self-reliant ecosystem encompassing design, materials, manufacturing, and supply chains. The mission also places a strong emphasis on indigenous chip design, ecosystem development, that is the materials, chemicals, the equipments, the test facilities, and the talent creation through industry and academia partnerships, positioning India for global competitiveness in semiconductors. So coming to today's topic, government has already initiated this ISM 2.0, so it should adopt a security-centric and mission mode approach, ensuring we have to ensure trusted supply chains, then the indigenous capability development, and also assured procurement support for the defense systems. This should be complemented by selective international partnerships with strategic safeguards, enabling technology transfer, co-development, and IP sharing while protecting the national interests. Further, the regulatory and the institutional reforms, the long-term policy stability, and the rigorous monitoring mechanisms are essential to ensure effective implementation and optimal utilization of the resources. So this provides a robust framework for achieving technological sovereignty in semiconductors, which is really critical for enforcing the defense preparedness and operational security and strategic economy. So this section is expected to deliberate on the actionable pathways, collaborative models, and policy interventions required to realize this vision and to position India as a leader in semiconductor-enabled defense technologies. So not only the semiconductor fabrication, also the corresponding ecosystem what is required, including the tools and all the test facilities and all those things also has to be taken care. And the software required, that is where I think academia and industry can play a major role, where the government is establishing the facilities, but these areas, I think I am looking forward to academia and the industry to come forward and take up those unique requirements and give us solutions, which will be becoming a part of the total ecosystem. So I would like to hand over now to the next person so that you can, I think we are starting with the next topic is on whole nation approach for achieving self-reliance in semiconductors for military applications. Rear Admiral D.S. Patania, VSM. Thank you.
Hello. Yes.
Every radar contact we track, every sonar signal we process, and every secure message we transmit depends on one critical element, and that is the semiconductors. In modern naval warfare, it is no longer the platform that defines the capability, but the silicon that powers it. And that is the context in which I will present my today's perspective. Distinguished Chair, distinguished panelists, colleagues and friends, ladies and gentlemen, good afternoon. India is navigating one of the most consequential technology transitions of this century. The semiconductor, a component smaller than a human fingernail, is now the fulcrum on which modern military powers rely. This presentation sets out what India already has, what is coming, and critically what the armed forces and the DRDO must do right to ensure that the emerging commercial semiconductor ecosystem also serves our defense requirements. The semiconductor is a new steel. Whoever controls this production controls the battlefield or the future. My talk will be covered in the broad headings as flashed on the screen. Let me put 4 numbers on the table that frame why we are here. First, supply chain vulnerability. Today, more than 70% of defense semiconductors are sourced from Taiwan, South Korea, and China. This concentration itself is a strategic risk. Secondly, operational readiness. From radars and missiles to propulsion and communication systems, our critical platforms depend on imported chips. Any disruption, whether due to sanctions, export restrictions, or supply chain shocks, can directly impact our combat capability. Thirdly, the technological denial. Access to advanced chips, especially those used in radiation-hardened or electronic warfare applications, continues to be restricted under global export control regimes. And fourthly, the widening gap. China has already invested heavily in building its semiconductor ecosystem. The real challenge is not what they are today, but where they will be in a decade from now. If you look across key domains, uncrewed systems, communications, radar technologies, and the underwater domain, semiconductors form the core of every capability. Access to each of these areas, performance, reliability, and survivability are all directly linked to the quality and availability of semiconductor components. I'll be quickly flashing the products in these niche technological areas. Firstly, the uncrewed systems, which is there on the slide. Networks and communication systems. Radars and surveillance systems. Underwater systems. This dependence is not theoretical. It exists across systems already in service. In combat systems, the processors used in radars, missile seekers, and munitions are largely imported. In platforms, mission computers, fire control systems, and propulsion controllers remain dependent on foreign components. In C4ISR and electronic warfare, we rely on imported FPGAs and ASICs. And in cyber systems, even the secure hardware that underpins our networks is not domestically produced. Every one of these areas represents not just a capability gap, but a potential vulnerability. Every quadrant on this slide is an adversary's opportunity and our vulnerability across all the 3 services and in every theater. Eliminating this vulnerability is our mission. At the same time, it is important to recognize that India is not starting from zero. We already have a foundational ecosystem, particularly in the defense domain. The Gallium Arsenide Enabling Technology Center in Hyderabad serves as a primary compound semiconductor fabrication facility, producing devices in radar and electronic warfare systems, and now moving into gallium nitride capability. Supporting this is the solid-state physics laboratory in Delhi, which acts as a research backbone. It has demonstrated significant progress in high-power gallium nitride devices and microwave integrated circuits, which are essential for modern defense systems. It has also developed indigenous silicon carbide substrates, which are critical for high-power applications. In addition, institutes like SARC contribute through CMOS prototyping and RF component development. while the semiconductor laboratory provides radiation-tolerant chip design capability. These are sovereign capabilities that already exist and support our systems. Expanding and integrating them offers the fastest path to strengthening our self-reliance. India is now witnessing a major push in semiconductor manufacturing. Significant investments are being made with projects spanning fabrication, packaging, and microcontroller production. However, from a defense perspective, critical gaps remain. We do not yet have radiation-hardened fabrication capability, scale production of gallium nitride and gallium arsenide devices, or a trusted foundry framework. In addition, defense qualification timelines remain longer than commercial cycles. This means that while the ecosystem is growing, it is not yet fully aligned with the defense requirements. The commercial fab wave in India is once in a generation infrastructure gift to the defense. Our job is to ensure that it does not sail past without a dedicated defense berth. Addressing this challenge requires more than isolated efforts. No single organization can solve this alone. What is needed is a coordinated whole-of-nation approach where all stakeholders operate as part of an integrated system. At the center must be a defense semiconductor ecosystem anchored on the combined demand of the three services. Around this, government, academia, industry, defense R&D, international partners, and startups must all contribute in a coordinated manner. These are not independent efforts. They must be integrated through governance, contracts, and a shared long-term demand vision. Without that integration, we will have capability in parts, but not a capability in effect. Self-reliance is not a procurement strategy. It is a national systems integration challenge, and the armed forces led by DRDO must be its integrator. To translate this into action, 5 key pillars are essential. We must begin by aggregating demand through a long-term tri-service forecast, providing a clear signal to the industry. We must invest in indigenous design by establishing dedicated centers focused on defense chip development. We must ensure that defense requirements are built into our fabrication ecosystem, including the creation of a trusted foundry pathways. We must leverage international partnerships for targeted technology absorption. And finally, we must build talent, creating a strong pipeline of engineers focused on semiconductor technologies. Together, these pillars will convert intent into execution. Within this framework, the armed forces have a critical role to play. By acting as a unified demand anchor, we can provide the scale and certainty required to make domestic manufacturing viable. We can define common specifications, streamline qualification processes, and accelerate development. These three immediate steps that can enable by establishing a defense semiconductor cell, launching a defense chip challenge, and initiating a technology acceleration program with industry. For this effort to succeed, a clear governance structure is essential. A multi-tiered framework can align national policy, defense requirements, and industrial execution. At the core, coordination between the services, DRDO, and national semiconductor initiatives will be critical. Equally important is integration with upcoming fabrication facilities, including the development of defense-specific design frameworks that allow our systems to be built on Indian fabs. The path to self-reliance can be seen in phases. We begin by establishing the foundation, creating institutions, defining demand, and initiating design efforts. We then move to delivery with the development of initial chips and prototypes. This is followed by scaling, where dedicated production capabilities come online. And ultimately, we reach a stage where a significant portion of our requirements is met domestically with the potential to emerge as an exporter. And in the final phase, we achieve true self-reliance with the majority of defense ICs produced domestically and India emerging as an exporter. There will be challenges, skill gaps, long development cycles, and economic constraints. However, each of these has a clear mitigation. Talent can be built through focused programs, timelines can be reduced through parallel pathways, and scale can be achieved through aggregated demand. The key point is that these challenges are manageable with sustained and coordinated effort. I will conclude with a few key recommendations. First, establish a defense semiconductor cell to act as a central coordinating body. Second, publish a joint 10-year demand forecast to guide industry and R&D. Third, commit dedicated funding for indigenous chip design and launch a focused defense chip challenge to accelerate innovation. Fourth, secure a defense dedicated fabrication pathway within national semiconductor initiatives. And finally, mandate a defined level of indigenous semiconductor content in future acquisitions to create a strong demand signal. Ladies and gentlemen, semiconductors today are what steel was to India decades ago. The foundation, and this is the foundation of our, this was the foundation of our strategic ability. We now have the ecosystem emerging, the policy support in place, and proven scientific capability. What is required is a clear direction and sustained commitment, because semiconductors self-reliance is not just a technology objective, it is a sovereignty imperative, and it begins with the decisions we take today. In the end, I will conclude by saying that self-reliance in semiconductors is not just a technology goal, it is a sovereignty imperative. Thank you.
Components imported. So your points are right. Are at DRDO also working towards whatever points some of them have already been taken care of, and we are in the process of scaling up the production of gallium arsenide, gallium nitride, and focused approach is very, very critical, which you have very rightly put in right perspective, and your phased roadmap to achieve self-reliance in 4 phases is well taken. And we are also very seriously looking into increasing the indigenous component in the technologies or components which we are developing. Thank you very much.
May I start, ma'am? Yeah.
Please go ahead.
Okay. So, good evening, ladies and gentlemen. Madam Sheena Rani, my colleague for many, many years. Rawalji, I think every second day I'll disturb him. And Rear Admiral Pathania, General Ashok Kumar, and other colleagues, very well-known faces around. The conference is second conference on ecosystem. So my request to organizers would be that where we have come from the first conference to the second conference, gap analysis is very important. And then only we can have a rein in into the ecosystem that where we are going. The ISM 1 through ISM 2 is just closing. A lot of development has happened in the country for last 2 years. And I think everybody is doing their bit, and we are in a good direction, I would say. The ecosystem that we are talking about in our country, probably from the defense side, SSPL has been leading the pack, and under their aegis, GATEC and StarC have been doing phenomenal job. And with their help, we are trying to develop a similar kind of expertise in the academia. So for me, as a Director of Futuristic Technology Management, we have 15 DRCOE, which is DRDO Industry Academia Centers of Excellence. And through these 15 centers of excellence, we are trying to make an ecosystem that we can one of the the targets which they have said, we should have adequate number of expertise or the HR required for semiconductor design development in the country. And semiconductor projects are really, really liberal. We are very liberal with all the kind of manpower required under the projects, and we insist that we can make as many experts as possible through these projects. Having said that, these are the also the projects where we are working with the help of IISc, IIT Madras, IIT Delhi, where there are R&D fabs which have been established over a couple of years, not couple of years, I would say couple of decades, slow and steady. And they have certain kind of technologies and professors who are very good at all these designs, packaging, and recently we have launched a photonics packaging facility at the ISC, which is DRDO sponsored facility. So there are multiple activities going on. The thing here, what ecosystem require is the kind of utilization of this entire facilities available as R&D, proving them in the field or functionally and then in the field, and then going for the manufacturing. And very good to know that many of the manufacturings were tuned to 180 nanometers so that SCL can pitch in, which is indigenous kind of technology for the fab. When you come to the other side of it, where the cutting edge requires 65 nanometer or 28 nanometers, we have been doing the outsourcing to either Global Foundry, TSMC, or any of these equivalent fabs. Nevertheless, the IP is being generated in the country. And some of them are so cutting edge, which is kind of neuromorphic dot product engine, which will actually accelerate our AI kind of systems. So these are some of our very, very recent initiatives, continual initiatives. Not only that, with the help of SSPL, Meena Mishra and the team which is present here, we have been taking a lot of initiatives which are required for the quantum research also, quantum dots and the quantum computation and quantum communication, quantum sources, detectors, terahertz sources, detectors. So these are some very ambitious activities taken with the help of academia and DRDO. So DRDO and academia have started working integratedly to make these innovations in the country. And what we have gone ahead and said, and we are exercising it in other fields, yet to activate that in the semiconductor zone is, moment the project or the product is stable, tested, simulated, and it is meeting the functionality, we are going in for TOT to the industry immediately. Some of the cases, even the packaging testing, we are taking industry on board, where industry is acting like a co-principal investigator. We call these academia as principal investigators, PI in the short form. We are asking industry to become co-PI with the academia along with DRDO functioning, so that the complete triad brings out the technology, and there is a we shorten the gap from the lab to the industry, and immediately if it is proven, the TOT is done to the industry, so that that can be commercialized if it is of dual use nature, or if it is required for defense or DRDO designs, it will be immediately manufactured to the need of the defense. So this is some of the ecosystem level activities that we have taken very proactively. Some of things are very, very difficult to negotiate between the various collaborators, the work shares that we are defining, and the figures of merit we are defining for each one of them. These are not easy, and these are very deep, technically very deep, very difficult to assess at times. And I think one person cannot even assess all the aspects of it. But yet we are trying to make sure that there is a serious collaboration between the collaborators, and we achieve, at least we near the goals, so that we achieve something which we have set out for. So this is something which is happening apart from the HR and the kind of work generation. In fact, a major metrology lab which is required for validation of every design at ISC is also partly funded by DRDO and is being operated and is open to everybody through the ISC portal for the usage. So my
submission or my kind of takeaway is that, I mean, everybody has talked about why it is required and why we are talking about 28 nanometers or 65 or 180 nanometers. I think enough morning onwards, enough has been conspired between all the people, but these are our 2 cents that we are trying to bring the things together. And in fact, I just wanted to say that we have a lot of verticals, and we have a dedicated vertical in compound semiconductors, sensors, which are partly semiconductors. Other than that, they are sensing using the semiconductor designs. We have seeker and homing technologies dedicated, wherein the semiconductor designs are being encouraged. The micro and nano system science and technology. There are multiple activities being undertaken under this vertical also to do some IP design, which is required for the defense applications. Quantum phenomena and device technology is a vertical that we are nurturing. Quantum communication is another one. Biomechanical devices also require this semiconductor and IP generation. Applications of advanced technologies for desert warfare also has some of the semiconductor design projects. Electromagnetics for terahertz and millimeter wave technologies. Integrated RF as well as photonics chips are being designed. Cognitive technologies and cyber physical systems, some of the chips are being designed. And the remote area called hypersonic propulsion, there also certain sensors and certain materials and chips are being designed specific for the hypersonics. So these are the initiatives which are taken, and the fabless design and tape out read programs, which are as of going on, are under high performance ADC ASIC, which is so we do have a lot of discussions and negotiation before we finalize this. The professor will say that we want 65 nanometer, whereas we will request our teams to negotiate whether it can be done within the indigenous power, where SCL can pitch in with 180 nanometers. Some degradation of performance will be there, but later on it can be improved, but the IP can be generated. So some we go ahead because their performance is the utmost. Wherever the functionality is utmost, we go for the design or fab using this SCL Chandigarh fab. Then another thing which we are going is sub-Nyquist wideband frequency estimation ASIC, which is on 65 nanometers. Silicon photonic integrated circuits, we are taking a couple of them as projects for the LRDE application. Then electronic quantum random number generator is also on chip being designed. Piezoelectric transducers, then CMUT array design, optimization, process development and characterization, purely on the semiconductor side. Quid magnetometer systems also being designed. Pyroelectric IR sensor, the first prototypes have come, they are under testing and validation. Photovoltaic mini modules also being developed using these technologies. Then light source photonic chips, then hybrid classical quantum photonic transceivers, photonic bioidentifier chips. These are some of the activities which are ongoing as I speak under various institutes. And then some of the very high-end projects which are in pipeline is CMOS and neuromorphic image sensors. So we started with neuromorphic chip. Now we are going ahead with the neuromorphic image sensors. Chip scale atomic clocks we are working on, and we are hoping to get some indigenous efforts here as a breakthrough. True time delay MMIC for electronic warfare. So I think I have a couple of these kind of projects which are ongoing, and we will be soon launching these outcome of these projects for the industry to take it up to work together and quickly take up the production or the kind of fabrication, at least the limited series fabrication required for the defense. And we do invite industry to participate wholeheartedly in this program so that we close the triad of DRDO, industry, academia. There is much more activity which is ongoing. We would also request the stakeholders or the armed forces also to visit some of these initiatives and labs, so they can also bring out. So there is a list of lot of applications and the requirements that has been projected by Rear Admiral, that these are our wish list. So what is a chip? What is the specification? If we can zero it on, it can be taken up as an indigenous activity through this route. And apart from this, we are also doing some TRL 1-2 works with our ERIPR scheme. Also, the TDF scheme, if there is a direct industry activity and there is maturity in the industry, I think TDF can take up, we can initiate our TDF activity through the industry for doing these indigenization activities. So we are trying our best to energize this ecosystem, and we are looking forward to the Tatas and Kens and what all activities are happening for the fab in the country. And definitely, I think within 2 to 5 years, we are going to look at something magnificent happening in the country. Thank you.
Thank you, Madam, for summarizing and nicely putting all the efforts which DRDO headquarters is putting to cater for the future needs and address the issues which are very critical for at least next 5 to 10 years down the line. Some of them which you have mentioned are that the ecosystem creation is very, very critical. Then HR requirement, the pool of experts, and then IP generation in cutting edge technologies. And we are also leveraging the facilities or fabs which are available in IITs or any academic institutes. And then a lot of focus is being put on quantum research, which is one of the very, very critical area for coming up technologies. And one very important point which you mentioned that in the last, we have to take all these technologies for manufacturing or production. So we are taking industry right from the beginning in all the projects which we are now initiating. And then dedicated verticals are identified and research is being funded and supported for developing technologies in those areas. Some of them we have mentioned that advanced sensor development activities, photonic chips, and neuromorphic image sensor, chip scale atomic clocks. So these are the technologies of the future which will revolutionize the performance of the existing technologies in next 4 to 5 years. So thank you very much for summarizing and nicely putting up the efforts put on by DRDO for next 5-10 years.
Thank you, Dr. Ranjana. Now I'd like to invite the last speaker of the session, Colonel Anurag Awasthi, CEO, EVMPL.
Can you hear me at the back? Right. Respected Chair, Co-Chair, organizers in the Center of Joint Warfare Studies, ladies and gentlemen, I am the graveyard shift last man to speak in the evening, so I will stick to my time. I'll make sure you don't ring the bell. And I have no presentation to bore you. I will not get you into nanometer paradigm. A lot has been said since morning. And I will come directly to the main crunch points insofar as leveraging academia and industry collaborations is concerned, with passing reference to DRDO. Having said that, I will first give you the initial backdrop as to what it is. Thereafter, I will give you what are the semiconductors for defense applications. There's a huge amount of difference between the commercial applications of semiconductors and defense applications of semiconductors, which has to be very clearly understood if we get into the academia and industry collaborations. Thereafter, I'll give you the great academia, industry, and the defense establishment tangle. It's a triangle which needs to be balanced because the requirements are totally diverse, they are disparate. Thereafter, I'll come to the pain points. What are the pain points as I visualize them in my personal opinion? And of course, I'll give you some suggested measures, or I'll give you some recommendations which possibly somebody could take forward, make a note of, and if it's possible, it could be put into practice. So in the next 10 minutes, I will just finish up, wrap it up in this small little module and put my point across. Right. Firstly, starting from ISM 1.0 to ISM 2.0, when you look at it, it has ticked nearly all boxes. It has ticked the fabs, it has ticked OSATs, it has ticked silicon carbide, it has ticked discrete semiconductors, it has ticked 3DG glass, it has ticked various issues of the gallium nitride and silicon carbide. The only thing it has not been able to tick is display. India is a huge display market. So that is where there is a void which I am sure ISM 2.0 will fulfill. All of you must know this because we must know our strengths as well as our weaknesses. What have we achieved and what still remains to be achieved? Having said that, the most important thing in ISM 1.0 which has happened is the change of syllabus. The AICTE in 2023 has changed the entire syllabus, putting VLSI into the BTech curriculum. It is a massive change. A lot of people gloss over it, but let me tell you, it is one of the most enabling things which has happened in the system. Now, courtesy that, the entire hegemony of various government institutions which used to be running VLSI courses in a very small measure has increased, and so has the private universities which have embraced this kind of a curriculum. So while you may be growing at whatever economic pace and the kind of scale that you're moving into the ISM 1.0, 2.0, 3.0, if you don't have the talent, there's a problem. So that has been addressed. So insofar as leveraging academia and industry collaborations is concerned, the end user, which is the industry, and the academia, which is to produce this manpower, is now getting a little balanced. We have to understand that. However, there still remains one pain point: faculty development. Somebody has to teach. Where do they come from? Either they come from the industry or they come as veterans, or you import them. So it is a very, very major quagmire which a lot of policymakers need to understand. Having said that, there are 4 tiers that we are looking at. When you look at the academia, you are looking at the tiers of the technicians, which is at the ITI level or a diploma level. You're looking at the undergrad, postgrad, and doctoral. It's a pyramid. The base obviously consists of the technicians and the other people for which the syllabus still needs to be streamlined. There are various people who are doing a lot of work in that, but I'm sure a lot of work is going into it to streamline that syllabi. Undergrad, grad, and doctoral obviously are lower in number, but then that has been streamlined to a large extent. So that basically balances out a lot of things. Now, the most important part is that when you're looking at semiconductors for defense or for commercial applications, we have to understand that profit is not a bad word. It's simple. It has to be a business case. If it is a business case, it requires 2 things: scale and volume. If you can do that, you're good to go. If you can't, there will be roadblocks. That's the way the world works. It's as simple as that. I'm sorry I'm being so blunt about it. Right. So while we look at the semiconductors for defense applications, the defense semiconductors differ significantly from commercial chips. Please don't put the same template on both of them. You require extreme reliability, you require radiation hard, you require high temperature, long life cycle, ruggedization, various other things. Now, while you look at all of this domain, you are looking at a low volume but high mix. Now, that does not make business sense. Then there are issues of export controls, there are issues of security clearances, there are issues of IP sensitivity, which man just brought out. These issues make this system a little more complex. To top it all, since it is for the weapon systems, the development cycles are very, very long. They can start from whatever time today and they can end at whatever time. By that time, technology has jumped by teraflops. So that needs to be taken into account. And of course, it's as simple as that no single entity can do this alone. So you have to leverage academia, you have to leverage the industry, and you have to leverage the defense forces to do this. Now, there is a disparate issue insofar as these 3 things are concerned. Now, let's look at it very obliquely and objectively. Academia focuses on fundamental research, novel materials, device physics, and talent creation. This is what the academia does. Industry looks at manufacturability, standards, supply chains, testing, and system integration. And defense agencies and defense services provide mission requirements, certification, and assured demand. Look at the 3 diametrically opposite requirements.
all three. So how do you balance them? When you can't balance them, obviously there will be pain points. So what are the pain points? The first pain point is scale. That I can only make this much. So how does it make a business case for me? Which is a requirement. The second part is IPR management. If I make it, then do I give my IPR to the government of India, or do I give it to somebody else? Or if it is DRDO led, do I give it to DRDO? Can I cash on this IPR? So there are issues in that. Then, of course, there's restriction in proliferation of these technologies. Ma'am has just mentioned that, the industry is now being taken as co-principal investigator to move in as the, transfer of technology, etc., etc. But this itself has its own various issues, complexities. So this needs to be ironed out in some manner or the other, but this is a pain point. Now, the last pain point is that the industry asks you, or the academia will ask you, or will ask the end user, which is the armed forces or defense services, what is your problem statement? What do you want it for? You want it for RF applications, you want it for memory, you want it for this, that, and the other. So that is not being specified clearly. While the product is being specified clearly, the technology and the requirement is not being specified clearly. So there needs to be a case that these problem statements come out very clearly from the armed forces. And what are the types of technologies required? So my suggested measures are following. One is there could be a structured collaboration with a standalone funding. So anybody who says, I have a lot of people who speak with me about various schemes in which you say that, the government is putting in X number of crores to, possibly design a chip or whatever it is. That money is less. You can't start designing chips in a couple of crore rupees. It requires a huge amount of money. Mohan is here. He just mentioned they've raised $1 million in Chip Spirit. Haven't you, Mohan? So then there you go. It's all about money. That's one. The second part is in the US, in China, in Korea, there's a huge amount of emphasis on something called harvesting. So there are government agencies like the DRDO or anybody else who look at various small entities who are making commercial chips, designing commercial chips, wanting to do something in chips, and realize, can this be used for defense applications? That harvesting needs to be done here in India. The faster we do it, the better it is, because there are too many of them. Now, the next part is, when you're looking at PhDs, or you're looking at, proof of technologies which people want to do in academia, there are three ways people are doing PhDs: government funded, self-funded, industry funded. Why can't the armed forces fund these people? Send them abroad. The Chinese send the people abroad to do PhDs everywhere. Why can't you do that? We can do that. The last part is expanding available facilities for greater collaboration and identifying dual-use technologies. My last part before I end is Dr. Kamaljeet was here. He spoke about the semiconductor laboratory. The speakers here have spoken about semiconductor laboratory. Again, I'm not getting into the nanometer paradigm. But the problem here is that there is a small startup which has designed a chip today. He wants to go and tape it out in TSMC. I'm not talking about 65 or 28 or 45 or 180 or 5-inch or 6-inch. I'm not confusing you. Why does he want to go there? Because for taping out, there are two basic criteria. The first criterion is turnaround time. He wants it fast. And the second is competitive pricing. If SCL can't do both things, he will go out. And with that, I rest my case. Thank you very much. You didn't ring the bell.
Thank you very much. You have very rightly, clearly demarked the difference between semiconductors for defense and semiconductors for commercial applications. And what I understand is that the semiconductors for defense applications are performance driven. You have to worry about the performance rather than any other thing. And whereas in case of commercial, you have to worry about the cost also. And another important thing is that the scale and volume is very, very important. So whatever defense electronics or foundries we are working, the scale and volume is not that much at present. So that is why we are not at par with the world in terms of cost. So that needs to be scaled up. And you have very rightly pointed out the voids to fill in ISM 2. So whatever is required to be done, you have brought out very nicely. Then the critical thing is that you have to have a integrated effort involving academia, industry, and government organization. So it is an integrated effort is the need of the hour. Individually, it is very difficult to achieve what we are targeting. Then one term which you coined is harvesting. Harvesting is very, very important, and we leverage whatever expertise available in terms of this harvesting in small institutes or small startups. And then one idea which you have given forward is that armed forces funded PhDs. It is a very good idea, and this will cater for the dedicated research, we can focus this research on the technology gaps which we are having in our country, and to fill those gaps, we need to develop the experts, and then dual use technologies are the need of the hour. Thank you very much.
Thank you, ma'am, for moderating the panel. So many takeaways. May I request the chair, the co-chair, and the panelists to join for a group photograph. May I now request our esteemed session chair to kindly step down from the stage and join us at the center, that is in front of the stage, for the presentation of mementos to a distinguished panelist and co-chair. May I now request Air Vice Marshal D.S. Joshi, Assistant Chief of Integrated Defense Staff, ICT, to present a token of appreciation to our chair, Ms. Sheena Rani R. Thank you, sir. We now move on to our valedictory speech by Dr. Upendra Kumar Singh, who is a distinguished scientist currently holding charge of Director General for Soldier Support Systems at DRDO Headquarters, New Delhi. Prior to this assignment, he was director of two very prominent laboratories of DRDO, that is Center for Artificial Intelligence and Robotics, Bangalore, and Defense Bioengineering and Electromedical Laboratory, Bangalore. He's a pioneer in the development of computer simulation and mathematical models for weapon systems, robotics, and biomedical devices. May I request Dr. Upendra Kumar Singh to deliver the valedictory speech.
So very good afternoon, and thanks a lot to organizing committee to have invited in this function. I hope that since morning, all the subjects which are regarding the policy matters of semiconductor devices, Fab Lab, and the aspirations of India must have been covered with many speakers, renowned speakers, including some of our DRDO colleagues. I think India is now at a very momentous time and event where all the dots which were earlier not connected are getting connected with a lot of policy support and fiscal support from the government, as well as like this kind of forum where people are able to talk to each other, they are able to organize such events, including exhibitions, where they are able to know each other and able to connect each other. I think with the ISM 1 and ISM 2 mission, India Semiconductor Mission, we all have moved much more far, and all the gaps which were there is getting filled up. I think the major gaps which will remain even after this support will be certainly the training or the trained manpower, skilled manpower, which one of the speaker, I think, Commander or Colonel was talking about sponsoring the candidates and going outside. Instead of that, perhaps we can start in India itself, wherever the projects are being taken by the scholars, whether those projects are being taken only for the sake of taking projects, or they are really being taken with a proper outcome, where there is a proper roadmap where the person will get absorbed as he progresses along with his projects or the final thesis. At India level, we need to collaborate with this. Already we are having very good, strong design capabilities, but along with the design capabilities, particularly in the gallium nitride compound semiconductors, particularly for the defense applications, we need to work on all the aspects of material research. Like India has signed the PAC Silica agreements, which will be able to secure rare earth materials and the materials which are needed from some of the select countries which are basically friendly to us. Already country has moved along to provide the PLI, where the production linked incentives as well as design linked incentives are already in place. Similarly, they have already, Government of India is providing the fiscal support to the companies. I think we need to also ask some of the companies who are there in the field to narrate their story, what kind of support they need, and it is for all of us also to make it sure that those policy makers, whoever are there, are we ready to collaborate with the like-minded people? Are we able to already DRDO in fact has good collaboration with a lot of academia and industry partners. We are having 15 Center of Excellence, where a lot of funding is going on. But I think till now, academia has been, it will take, we have to have some kind of patience. Academia has been working on the paper publications. Now they have to move from paper publications to patent, or at least working on the TRL level 1, 2, 3, 4. And after that, perhaps industry and the DRDO can take further. Besides that, what is needed is basically coherence between all the stakeholders, those who are there in position to help those industries or the knowledge partners, or those who are having particularly seeking that kind of opening to allow them to work along with them. DRDO also has got a lot of project assurance capabilities where we take a lot of project assurance and make it sure that they are working for 6 months to 1 year based on whether it is BTech or MTech, whether they can be trained. We should also look particularly for material development as well as whatever is the special equipments which are coming from outside, like in the medical world when we were developing the medical devices, many of the devices still were coming. I'm very much sure that here also lot of semiconductor devices which are going to be utilized, they must be coming from outside. Somewhere they outside country, they should not be able to arm twist us. So people should look for making the equipment, looking into the raw materials, looking into the trained manpower and skilled manpower which can be utilized. With 10 numbers of already project sanctioned at the cost of more than 1.6 lakhs crore, we hope that these things should further multiply, and like software industry which has grown, we also become stable, we become much more robust mechanism gets placed in the semiconductor field also. Though all of you may be knowing, or this must have been deliberated, that Fairchild company, which was the predecessor of Intel, it came to India in 1960s. So somewhere we missed the bus, and the government of that time could not basically take up their suggestion to have it in India. Otherwise, today when we are talking about the assembly or packaging or marking, all these things was available with the Fairchild group company, which we did not take it, and finally it went and got settled in Malaysia. We had particularly defense and ISRO has been already, I hope Dr. Rawal must have told about these stories. SCL came long back in 1984, 76 I think, 1976. And they started producing in 1984, which we were there only one generation behind, and 3 years ahead we were there, Taiwan semiconductor companies. But somewhere, software people, I'm also from software, the people like Bill Gates and the people who were there in the higher level of management of various institutions, the kind of narrative which was given, like Bill Gates said once, that there is no use of hardware, software can do anything. So these kind of things can move people away from the hardware. I think today, after ISM 1.0, we have arrived for India and for the world. Reason is, it's very important that the balance of hardware and software is done. Today, most of the IIT rankers, they go only in the software field. You say that where are the first 100 rankers? They go only in the software industry, or basically doing the BTech with the software. And slowly academia also has moved away. Earlier there was equal seats for mechanical, electrical, aero and computers, only 30 seats. Today all the loopholes has been found to make it sure that electronics with software, physics with software, anything with the software has gone. So unless the whole ecosystem, if the ecosystem had to move, ecosystem for the manpower will be moving only when basic changes in the structure is made, where people are, if they are not equally distributed, at least they are not totally biased toward the software. We hope that the deliberation, whatever has happened here, will be reaching to some of the policymakers to make it sure that importance to the hardware, importance to the semiconductor, different aspects of the semiconductor will be given and made understood not only to the children who are going to the colleges, but to the parents also. Because one Google employee, once it comes that he is earning 1 crore rupees, they multiply by 100 and say that my son or daughter is earning 1 crore rupees. How much is the expenditure? Nobody says. So unless this whole structure and the mindset of the people is changed, we will be loser. And we hope that this goes to this audience and it goes further to our friend circle and others. Already, whatever is being set up in Dholera or Assam, 6 estates are presently being covered. We hope that further multiplication in other different states also are done beyond Orissa, beyond Mohali, beyond Dholera or Assam, so that others like software which has multiplied and where the people got totally oriented towards the software. Because I went once for giving one project to IIT Chennai, and it was an underwater autonomous vehicle, and we were more working on the wanted to work on the autonomous underwater vehicle. And after discussion, even the professor said that, sorry sir, we want to work only on the deep learning. I said that what is there in the deep learning? Nothing you to do it. Data had to be there, and data automatically extracts unless you are getting into the fine tuning of the model. So very important that we also, people who are there from the semiconductor part of the story, they make their own narrative, better narrative, a narrative which will change the course of India. And we are very much sure that with so much government push, things are going to happen in much better way, and slowly parents as well as children will be taking the course of semiconductor, RF, high power devices, discrete devices, and we will become the self-sufficient in time to come. The future war will not be only won by weapons, but by the chip which powers them. With this, I congratulate once again to Dr. Parimal and all the organizing committee and all of you to be sitting here till the last moment. Thanks a lot. Jai Hind.
Thank you, sir. May I request Dr. Parimal Kumar to present a token of appreciation to Dr. Upendra Kumar Singh.
Yeah.
Thank you, sir.
Thanks.
May I now request Major General Dr. Ashok Kumar to deliver the strategic summary.
Jai Hind, everybody. Actually, once you see this hall in the morning and now, you straightway reach the conclusion which we must have in life, that quality is always better than quantity. So the people who are sitting here, they are actually the crux of the our dream of future India, planning to develop by 2047. And of course, in the chip design we have to do a lot. Actually, we have lot. Actually, once you have heard so many speakers, we have lot with us. There is only one thing which is missing. Can anybody guess that? Just have a wild guess. what are we not having? No, we are not having time. India today doesn't have time for structural growth. Defense forces don't have time to grow up in a structural manner to look at only their own borders. We all have to look beyond the way the world is unfolding. So only thing which we lack is the time. And then how do we make up that? Can we make up time by arithmetic progression? Answer is clear no. Can we make up that by logarithmic progression? Answer again clearly is no. Can we make up some distance by geometric progression? Again, the answer is no, despite the geometric progression being an interesting term of growth. So what we have to do? We have to go in for the hyperbolic progression, at least to start with, gravitate towards the super exponential functions, and finally power towers of growth. Unless we, each one of us moves in the mission mode to do the changes, whatever is there within us, only then we can move to the our intended direction. You would have also noticed, while we have now taken up this kind of seminars discussing the semiconductor, otherwise defense forces were very happy to give their requirement of that we want this kind of radar, this kind of tank, this kind of aircraft and things like that. But why we are discussing this? Because what is needed, defense forces will continue to give their mission requirements and operational requirements. For example, they will say that create a system or give a system wherein the data coming from these two little eyes up to the satellite, all kind of sensors get fused in real time, and I can decipher the data from that quickly. Now it is this responsibility of our people at the headquarter IDS, the people in DRDO, to translate that, okay, in case I am going to have a compute system with 180 nanometer of chip, can that meet a requirement? Or we have to go to 18 nanometers, or we have to go to 3 nanometers? What is that hardware requirement which Dr. UK Singh has emphasized? So one of the suggestions which came actually from two speakers was that creation of a dedicated cell in headquarter IDS, where Dr. Parimal can play a pivotal role, that whatever be the forces operational requirements, as to how do we translate that in the chip language to be given to the DRDO as well as to the industry, to the academia, so that that can be aligned. While this kind of effort is doable, but it may also project a kind of idealistic situation which may be difficult to achieve to start with. Then what do we do? You would have heard the concept of graceful degradation. Suppose in your mobile where you are operating WhatsApp as well as the SMS, suppose the data goes off, there is no data either through the Wi-Fi or through the mobile data. So naturally you cannot send your WhatsApp messages. But whatever be the critical messages, what do? That you send that through SMS. Similarly, in this growth story of translation from the operational requirement to the chip value translation, in case we find there is a gap that, let's say, suppose you have deciphered that you require a 3 nanometer chip for a particular function, but you feel that, okay, that will not be possible to do it today or tomorrow. It will take 1 year, 2 years, 3 years by various routes, by TOT, by indigenous R&D, by collaboration and things like that. So then you have to develop an art with collaborator of DRDO's, industry and defense forces. Okay, if I am going to have only this much of a chip specification, how do I ensure that my critical functioning can continue? And we accept for that little time how the graceful degradation comes into play. And it is the responsibility of our learned scientists from DRDO, people from industry, whosoever is people from academia who are in the manufacturing or capacity creation domain in various segments, to create that ecosystem so that the period of graceful degradation is shortened. how happy you feel the moment your data which was missing suddenly gets restored, even whether it is somebody who has erroneously left his Wi-Fi password unprotected or by any mean whatsoever. So we have to all create the gap bridging so that this graceful degradation duration is reduced. Till the time it is there, the different doctrines, tactics and methods are used to do that gap completion. Now the last point, because it is my responsibility as part of the organizing committee to ensure that your agony of is not further enlarged, but we cannot repeat, we cannot do away with our responsibility, either as defense forces, our DRDO, our industry, our academia. We cannot have that system that it is his job or her job and they will do, and that is how things will develop. And again, I come back to my first point, gentlemen, we don't have time. In case we wait for time, it will not wait for us. You are seeing whatever is happening today. Operation Sindoor is already on. Pakistan is fighting with Afghanistan. Russia-Ukraine war, which has commenced between unequal partners, has now culminated. The Israel and its fight between around, as it was not adequate. Now Israel, US, Iran, everything has happened. Crude is undergoing a problem. People have started migrating from cities to the villages. So these kind of things and which are happening, world also is not having time. In any case, so we have to take our lessons well to ensure that we do those things and create conditions so the people who are younger to us can do a better performance, whether it is battle or in a business or in life. And of course, we have to take care of the future generation. And that will happen only once we respect time. With that note, I thank each one of you from my side and hand you over to the MC Babavi.
Thank you, sir. May I kindly request Shri S.S. Rana, Scientist E, Office of Scientific Advisor to Chief of Integrated Defense Staff to Chairman Chief of Staff Committee to deliver a vote of thanks.
Jai Hind. Respected Air Marshal Praveen Keshav Bohra, UISM, AVSM, VM, Deputy Chief of IDS, PP and FD, Dr. UK Singh, DS and DG SSS, Rear Admiral DS Pathania, DG Vesi, Dr. DS Rawal, OS and Officiating Director SSPL, Assessor, AVM DS Joshi, SIDS ICT, DG CENJOWS, other dignitaries, esteemed speakers, exhibitors, and fellow colleagues. As we conclude this productive workshop cum exhibition, I would like to take a moment to express our gratitude. I feel highly honored and privileged to propose the vote of thanks for this informative second workshop cum exhibition on energizing semiconductor ecosystem for defense applications. First and foremost, a huge thanks to our chief guest, Air Marshal Praveen Keshav Bohra, UISM, AVSM, VM, Deputy Chief of IDS, PP and FD, for gracing the occasion with their presence and sharing insightful views. I, on behalf of the organizing team, convey deep regards and heartfelt thanks to Mr. Ave Noriaki, Minister of Political Affairs from Embassy of Japan. I would like to thank all the honorable delegates who blessed us with their presence. A special thank to the organizing team and the volunteers who worked tirelessly behind the scene for days
to ensure everything ran smoothly. A heartfelt thanks to all the speakers whose constant guidance and support shaped the conference. A successful workshop relies heavily on its environment, and for that I thank Director Microsoft Center, who has provided us with an exceptional, comfortable, and state-of-the-art space. From the comfortable sitting arrangement to the seamless technical support for our audio-visual needs, everything was handled with great professionalism. Finally, thanks you to all the participants. Your active participation, thoughtful questions, and enthusiasm made this workshop a resounding success. Jai Hind.
Thank you, sir. May I request Major General Dr. Ashok Kumar to present a token of appreciation to Shri S.S. Rana. Thank you, sir. Ladies and gentlemen, thank you for your gracious presence and valuable engagement throughout today's deliberations. Your participation has truly enriched the depth and quality of this dialogue. We shall take the points emerged to the decision makers. We look forward to meeting you all in the next version of this deliberation. We now invite you to kindly join us for tea and refreshments. All volunteers are requested to come back after tea for certificate distribution and Team CENJOWS for a group photograph. Thank you. Jai Hind.